We'll start this exciting 3-day-long academic meeting by a short inaugural session now. It will be followed by three academic oral sessions today and one poster session. Tomorrow we'll have 4 oral sessions and 1 poster session. And on the last day, we have planned a shorter academic session so that an afternoon guests can visit the NISER campus in general and the SCS department in particular. We have lab visits and photo sessions on that day. So let's begin. For the inaugural session, may I request Professor Sudhakar Panda, Director NISER, Professor P.D. Naik, Officiating Vice Chancellor and Dean HBNI, Professor Dilip Kumar Maiti, Associate Dean HBNI, Professor A. Srinivasan, Dean of Faculty Affairs NISER, Dr. Sarnappa Nembena, HOD SCS and convener of this meeting, and Dr. Himangshu Biswal, SCS NISER, co-convener of this meeting, to please come on the dais. We welcome the dignitaries by a bouquet of flowers by our students. Come. We will commence this proceedings by lighting the lamp, followed by a Saraswati Bandhana by our students. May I request all the dignitaries to, on the dais, please go to the lamp and please light the lamp. Thank you, Juhi, Priya, Asutosh, and Siman for this beautiful rendition. May I now request Dr. Sharnapan Nembena, HOD SCS and convener of this meeting, to deliver his welcome address.
Professor Sudhakar Panda, Director NICER, Professor P.D. Nayak, Officiating Vice Chancellor and Dean HBNI, Professor Dilip Kumar Maiti, Associate Dean HBNI, Professor A. Srinivasan, Dean Faculty Affairs, NICER, Dr. Himanshu Biswal, my colleagues, visiting guests, students, staff, and other members of SCS and NICER. A very good morning and welcome to the first HBNI interaction meeting in chemical sciences. We are proud that HBNI had chosen NICER as the host for this historic first meeting, a 3-day program comprising one keynote lecture, 26 invited talks, and 2 poster sessions. The keynote lecture will be delivered by Professor Sundar Gopal Ghosh from IIT Madras. On behalf of the organizing committee, I thank Professor Ghosh for accepting our invitation. We are fortunate to have around 55 delegates from HBNI main office, BARC Mumbai, IGCAR Kalpakam, and SNP Kolkata, who agreed to come for this meeting in a short notice. We also have an overwhelming presence of students in this meeting in the form of 45 posters by them. We have arranged WebEx live streaming for the meeting, and I warmly welcome all the participants who joined virtually. The main objective of this meeting is to initiate several collaborative programs among the faculty, scientists, and students with expertise in different research areas within the DAE units. As far as our school is concerned, at NICER, the School of Chemical Sciences consists of 21 faculty members working on cutting-edge research areas such as medicinal chemistry, material chemistry, physical, organic, and inorganic synthesis, and many more. Our school strength is around 400 members that include faculty, non-teaching staff, and students. We have 3 academic programs: 5-year integrated MSc, integrated PhD, and PhD. Currently, 200 students in integrated MSc, 10 in integrated PhD, and 100 in the PhD are pursuing their degrees at School of Chemical Sciences. Our faculty members publish in high quality journals such as the Journal of American Chemical Society, Angawanta Chemi International Edition, ACS Catalysis, ACS Central Science, Chemical Science, and core organic, inorganic, and physical chemistry journals. I shall not take much time, but before I conclude, I must thank all the speakers and presenters for coming here and being part of this meeting. I hope this meeting will be a great success. Thank you, one and all. Thank you.
Thank you, Dr. Nebana. May I now request Professor Dr. Panda, Director NISER, to please address the gathering.
Thank you, Varindam. And I must thank the organizers to get me here into the dais. I start with Professor Naik. You already heard the introduction. I don't have to give always again the designations. And those are the architects of HBNI. Sir Grover, he is not here today, but started from there 2 years ago. Professor Basudev Rao, who was the ex-Vice Chancellor, and he is also here. I'm happy that he has come. Mr. Maiti, and my colleagues on the dais, my colleagues of the dais, and dignitaries who have come from HBNI units, what we call constituent units. And also I'm happy that we have at least one person from outside HBNI umbrella. Professor Ghosh is giving the keynote address. So that's the way it should go. We should not confine ourselves to one house. We should expand and let others know what we are doing, So before I start, a very hearty welcome to Niger and good morning to all of you. The point is, why are we here? Okay, you heard that we are having this introduction meeting under the umbrella of HBNI. I also thank the HBNI that chose Niger. I would have felt a bit ashamed of having this 2 years before, or 1 year before, because I still remember when, for one of the graduating ceremony, I had invited Professor Basudev Rao as chief guest. His beautiful auditorium was not there, was not ready, so we had to have in a lecture hall. Now I have a place for you. I hope you have been accommodated. The accommodation place is good, and let's see in the 3 days if the food is good, because for me that is most important. Okay, so 2 years ago, I think it was 2 years ago, in HBNI, we had a meeting, interaction meeting among all disciplines. And a very beautiful meeting and success. And there we itself thought about having these single disciplinary meetings in all the HBNI units. And I think the first on physical science was in SINP last year or earlier. Then RRK hosted the one on biological science. And this one, the third one, I guess it's in the chemical science. And I remember actually November, 18th November, I think I received an email from Professor Naik that we would like to have it there. I gladly accepted, and I mentioned the reasons that I would not have been happy to do it earlier, but now I could do that. Infrastructure is ready. Well, it's not that gladly accepted. I should admit that first I talked to the chairperson when he came and asked me, can we have it? And so I was asking that The depends on factors, everything else is there as far as the academic, who will fund it. And because everyone is now worried about toward the end of the financial year. And but we found a way of some support HBNI is giving. The rest is coming there, coming from Niger. So there's nothing like if the fund is available, we have accommodation, etc. So why should not we have this meeting? And another reason I would like to have such meetings in Niger is that not all my faculties, they are able to keep in touch with other faculties around the world, not only under HBNI or in our country. I like maximum benefit should go to the students. They can't travel here and there. Obvious reason again, fund comes into picture. They get a peanuts for their contingency from where they can use the money to travel. And that we cannot support many people to travel in that. So not only the PhD students, but I would like also the students who are doing integrated MSc for the last career, they will also understand. So the academic benefit goes to more number of people if we have such meetings here. And as I heard, there are quite number of um, sessions, oral presentations, as well as posters. And I request students and other members to be present at the posters. Just imagine if the person who has taken so much time to prepare the poster, and if you don't visit and interact with them, they will feel bad. That should not happen. And even if 5 minutes, 10 minutes we can afford, I hope that there are particular time marked for that. So don't run away. Especially I talk to my students, don't run away. Go to the poster sessions, have a look, ask the questions, what it is about. Okay. And I believe our initiative for having interaction meetings like this under the umbrella of HBNI will continue, and success will come to HBNI as well as all constituent units in future. So we should be carefully plan the things properly depending on what the weather, which area we should focus on, where we should have this meeting, etc. Do they have infrastructure and things like that? That will continue. And finally, I welcome all the people who are coming first time to Niger campus. Move around, see. We have a place called Meditation Center. And be careful if anyone is climbing to that center. But you are free to meditate during your free time, not during the lecture time. Yep. So, so that's all. Again, enjoy the meeting. I hope this 3 days meeting will be a great success, and that will give us more enthusiasm to plan for future meetings. Thank you very much.
Thank you, Professor Panda. Now may I request Professor P.D. Naik, officiating Vice Chancellor and Dean of HBNI, to say a few words.
Good morning, and on behalf of HBNI, I welcome all the participants who are physically present here, as well many are present online. We are happy here that with us Professor Sundar Gopal Ghosh from IIT Madras is the keynote address today. And on the dais, we have Director NISER and good friend of HBNI, who always has supported all the activities of HBNI. And today what you see in HBNI is because of the contributions made by directors of various CIs and OCC of HBNI. NISER is only OCC, off-campus center, others are CIs. In fact, we are very much benefited by the wisdom of Professor Sudhakar Panda. Always is, wherever you want to be critical, you very critical, but very supportive also. That is his nature, that's the thing. You'll not take anything just like that. If you want to be critical at some time, you just critical and nothing. And sir, that help us really. And we are with us, Saranappa, the convener. Thanks for taking over the charge and doing all this work. We have Professor Srinivasan from NICER, my good friend Biswal, then my colleague Professor D.K. Maiti, Associate Dean HBNI. And I'm happy that my BRC colleagues, Professor Kannan, Professor Ganti, Professor Patra, Professor Mahapatra, Professor Tapas Das, and Dean Academic IGCAR, Professor Varmanand Rao. I am very glad that all of you made it to be here. In fact, the genesis behind this type of meeting, team meeting, I think Professor Panda has covered most of it, and I'll just elaborate a little bit on that. Before that, I'll just mention about why HBNI is formed. What was the need? In fact, all of you know that academic programs were going on in BRC training school to train the engineers and postgraduate science graduates, before that graduate only, to carry out the mission-oriented research in nuclear science and engineering. And in the umbrella of HBNI, there are many other, apart from R&D centers like BRC, IGCAR, RRCAT, and VCG, there are many other aided institutes. There are also academic programs are going on. They also used to guide the PhD students, faculty at that positions. However, they were registered with various universities, nearby universities. Like SINP students were registered with either Calcutta University or Dharawat University. Students were from BRC registered with Bombay University, like with IGCAR with Madras University. So it is felt that it is better to bring all these academic programs to maintain the uniformity under the one umbrella. With that concept, HBNI was formed, and it got its recognition as a deemed to be university on 3rd June 2005. And academic programs were started from 2006 academic year. In fact, many of our faculty, some of those who are in R&D centers, they have the dual route. They are also working for the set departmental goals, the goals, as well as they are guiding the students. Others from aided institutes, they are guiding the students and doing extremely well. There was a little bit difference. Aided institutes having the very high basic research component. And R&D centers have basic research component, but as well as a technological component. So if you merge this, or synergize these two, basic research in aided institutes and technological advantage of the R&D centers, we can develop many technologies, not only for the nuclear energy and also for the societal benefits. I'm happy to say that many patents and many technology generated because it's close collaboration between the faculty of aided institutes as well as from the R&D centers. In fact, long way back in 2021 January, our former Vice Chancellor is present here, I'm happy, P.R. Vasudeva Rao, it felt that there is a need to do much more than that. Although there is interactions between R&D centers, they are in close collaboration like IGCAR and BRC, there is a very, very close programs are going on. But aided institutes, they are far away and they are having the only basic research component, other things. Their interaction with other R&D center, other things are not as strong as envisaged. And for that, it is possible only when there is an interaction meeting. And best time also there in 22. That was declared by UN as basic science for sustainable development. So we have, in April 2022, the first meeting of interaction meeting, covering the all aspects, all the disciplines, was held at the Convention Center at Anusakti Nagar. And that was very successful. I'm thankful to all the director of CIS. All of them attended physically that meeting. And it was felt that, yes, this type of meeting is very good, but a theme-based meeting, like chemical science faculty at various, as well as the other persons who are also doing the multidisciplinary type of research, also involved in cutting edge of the chemistry and other things, or biology or physics or mathematics. All them can come to a single platform and can discuss, and that will be better for their own academic programs as well for DE as well as for societal benefit. With this series, as Professor Panda also mentioned, first was held at SINP in June on the topic condensed matter physics. Second was held in November in RRCAT in life sciences. And this is the first meeting in chemical sciences. Now I am happy that it is held at NICER first, because if you see NICER faculty, their publications, the quality of research papers are one of the best in India. And I'm happy that first interaction meeting of HBNI, Professor Panda agreed to host here. Thanks for that, sir. HBNI, we have around 48 academic programs. PhD is our main programs. More than 50% of our students are doing either PhD or integrated PhD. And rest are at NICER only we have the undergraduate course, like integrated MSc. Otherwise, all our courses are postgraduate courses. MSc Physics at HRA recently started, 2017. And there are many skill-based MSc programs in the area of medical and health sciences at TMC. Some of them are MSc in public health and epidemiology, which is very important after COVID-19. MSc in hospital radiopharmacy, which is very important for helping the nuclear medicine professionals, medical professionals, into preparing the radiopharmaceutical drugs and other things. In fact, we are our chairman, AEC, and secretary is also our chairman, council management. He is always encouraging that there should be strong interactions between the various units of DE so that resources available at various CIS and OCC of HBNI, in bracket DE units, can be utilized fully, and something can be done for the, not only for DE, but also for the society. I thanks our chairman, council management, Sri K.N. Vyas, for that. And I thanks for all of you for coming over here to attend this first meeting on chemical sciences. In fact, I know holding such type of meeting is really quite tough job, and you all will agree that Professor Saranappa, Professor Srinivasan, Professor Biswa, and many faculties of and students of NICERS help us in this regard. And lastly, but not least, I thank all the participants who are physically present here as well as online for this event. Thank you all.
Thank you, Professor Naik. May I now request Professor Maiti, Associate Dean HBNI, to say a few words, please.
Good morning, Professor Panda, Professor Naik, Professor Basudev Rao, then Professor Ghosh, who is the keynote speaker, and my colleagues in the dais and my colleagues in the audience, and my dear friends, student friends. So you have heard that why this kind of meeting has been arranged just for the interaction of faculty and students from different CIs and just to know each other. And, so you can, if you need any help from other students from other CI also, you can approach them. And faculty also can interact among themselves. It has two purposes. One is resource sharing. At the same time, there are many overlap in the work in different CIs and different labs. So how to minimize that kind of overlap and whatever complementary work can be carried out by different groups, that should be taken up. And other part is that DA is seriously thinking to make high-end facilities central, to make it centralized. In that direction, already some kind of discussion is going on. And to start with, which is the simplest way, is high-performance computing. And DA has seriously taken that in Vizag, some kind of supercomputing facility will come, probably in different phase, and it can go up to 100 petaflop. As of now, I think BRC has a supercomputer which is about 1.4 or 1.6 petaflop. And of course, in Vizag, BRC has one supercomputer which is about 6 petaflop. So in a phased manner, that will be useful. And in fact, it's SINP, IPR, HRI, and NICER, they have shown the interest that they need this kind of high performance computing facility, and probably it will be the best one if it is handled and maintained centrally. So that is one aspect. Similarly, any high-end other instrument also, probably department is thinking that way, that it should be a central facility. Okay, so that is one kind of interaction. In fact, we are going to have a discussion and as what kind of requirement is there for the computation facility in say next 10 years for from different CI. We are going to have a meeting in that directions, and department also wants that HBNI should take care of that kind of facility at least centrally, so that all of its CI and OCC, the students can make use of it. That is one aspect. Okay, the meeting, when we decided to for this kind of interaction meeting in chemical sciences, is it was chemical sciences are done at 3 places, BRC, mainly in BRC, because major faculty members of chemical sciences is about 160 from BRC, and I think around 25 at IGCOR and 21 at present in NICER, and hardly 3, I think 3 faculties are there in SINP. So we are thinking of where to go, and then we are very happy that NICER agreed to hold it, and so that's how we are here. And we thought of it's a kind of a family affair. It's a small family meeting within HBNI family. Only that the meeting is. So interaction will be among our people, but at the same time, we'll invite one senior researcher who is performing, who is doing excellent research. So in that context, NICER has invited Professor Ghosh. We are very happy that he gladly accepted and he's here to give the keynote address. Otherwise, it has been decided that it will be kind of within the HBNI family interaction meeting. And number of speakers also we thought of in the meeting discussion that it should be proportional to the number of faculty members or different research area, so that all different aspects is covered in that particular research area in as a in the presentations to display their expertise and the resource whatever they have. So in that way only we have decided how many lectures will be there from BRC, IGCAR, or NICER and SINP. I request all the speakers to not only cover their own area, maybe they can say, because only few people are there, they are representing as a, in that kind of research from that institute, they should also touch upon what kind of other people are working, his colleagues in or her colleague in that institute, what other kind of work, probably they can also touch little so that people know exactly what kind of work is going on in different institutes. That is one aspect. And about students, this is a great opportunity. You should know each other's work. And I also announced that there are 5 best poster awards. So you should take enthusiastically explain, very carefully explain there are judges who will be moving around the posters. You should explain their queries and you don't know, you may be that out of that 5, you may be the one. So you should be careful about that. But at the same time, you should see other posters also so that you know what other people are working, and if any interest or kind of complementary area you think that will be helpful to you, you can approach to the students or the guide or in HBNI central office also, so that we can help to bridge among your interest. So that's all I wanted to tell about this, and I sincerely thank Professor Saranappa and his team to make this kind of, it is almost a kind of a big symposium. We thought of a family meeting, but they have arranged in a very formal way kind of symposium. So thank you all. Thank you for your participation. I hope it will be enjoyable.
Thank you, Professor Maiti. Now, may I request Professor Srinivasan to say a few words and conclude this session.
Good morning to all. Director NICER, Professor Sudhar Panta. Former Vice Chancellor, Professor Vasudeva Rao, HBNI. Professor P.D. Nayak, Officiating Vice Chancellor, Dean, HBNI. Professor Dilip Maiti, Dean, Associate Dean, HBNI. My dear colleagues, Professor Nambana, Convener and Chairperson of School of Chemical Sciences, and Professor Himanshu Biswal, co-convener of this program. And also we have Professor Kannan here, Professor P.K. Mahapatra here, and we have our registrar and finance officer. And my dear colleagues and students, good morning to all. And yes, before starting the things, I would like to start with the first HBN interaction meeting. It was held in somewhere in April 6 to 9, 6 to 8 in Convention Center, I rightly pointed out by our director. And during that meeting, which I have mentioned that that was the small request which I mentioned, that the integrated PhD program which we have submitted, the Board of Studies, and Board of Studies has agreed, approved the proposal, and also I mentioned that the file is now in HBNI. Hope that file will be approved shortly. If at all if it is taking longer time, it will be our director will not give the plan or non-plan budget for the school. So this is the condition which I put it back to the after the HBNI team, and of course they have approved the proposal, and finally we have started the program in June 2022, where the first integrated PhD program started. And I'm happy to inform you all that there are 9 students completed their first semester integrated PhD program. That is the one good news from HBNA point of view. And now I thank Professor Vasudeva Rao for this initiative arrangements, and make sure that things are in the right direction for that integrated PhD program. Now coming back to the plant project which I mentioned. For this, I would like to take this opportunity to thank Professor P.D. Nayak, because he was the chairman of the Vision Committee. We have prepared the plan proposal sometime 2017 or 2018 and send it to, of course, cleared by the BOG and send it to DAE for the approval. And of course, the proposal forward from PAC to Vision Committee, where Professor P.D. Nayak was the chairman of the committee. After reviewing the proposal, which they have put some comments. And some of the comments are simple and straightforward, which we are able to answer. Some of the comments are a bit more critical, where we have to convince the PAC, because Vision Committee, whatever the comments, whatever the answer we give, Vision Committee may agree the things. But the PAC we have to convince. Now, how to prepare for the answer for those comments? Then again, we called Professor P.D. Nayak. Sir, can you help us out? Then we thought that Professor Nayak was very busy. Of course, he is handling the BRC, work in BRC, and also taking care of the HBNI activities. We thought that he will be very busy and he may not be in a position to help us out. Then we called him immediately. He said, okay, you come sometime next week. Okay. Then accordingly we stayed, and then we had a interaction meeting with him, and then he also modified the proposal, something like this, and he also has given the answer for the comments what we have to present it in the PAC. And not only that, and he was there in the PAC as part of the PAC member, and finally make sure that the proposal has been accepted and approved by the PAC. Finally, we received the sanction order. And thank you, sir, for your comments. And because of the proposal which has been accepted, now that the same plan money is helpful to conduct this HBNI interaction, first HBNI interaction meeting in chemical sciences in NISA. Now, coming back to Professor Dilip Maiti. Thank you, Associate Dean, Professor Dilip Maiti, and also Professor Kannan here, Professor P.K. Mahapatra is here. It is the BOS team, Board of Studies BOS team. And earlier we used to take longer time to get the approval from the BOS clearance. Now, when we submit the thesis, maximum 15 days or 20 days to get the clearance, particularly for the reviewer list from the HBNA office. This is only for chemistry. I think I also hear that the similar things are happening in biology, and there are issues in physics. Hope that will be sorted out shortly. Hope things will be streamlined for the other stream also. But thank you, Professor Maiti, Professor Kannan, Professor P.D. Professor Mahapatra for helping us, and of course my colleague is also part of the BOS team. Professor Himanshu Biswal, we are all be working together and make sure that things are in the right direction. So far I addressed some of the points. Now we are sitting on the other side of the table sometimes. So sometimes the requirement also be more. Okay, there are requirements as the faculty affairs section. We are part of it. Now there are requirements coming from the institute. Recently, which we have completed the review meeting for the individual schools, and there are comments received from various schools. And one of the important comment about from all the schools, which they have mentioned that number of PhD students allotting for the assistant professor, reader or associate or professor level. So as of right now, we have four students for the assistant professor reader of, associate professor 6, and professor 8. And most of our colleagues always come back and fire us because we are sitting on the other side of the table and you are not coming forward and help us. And the one comment which always mentioned that the order should be either reverse or order should be somewhere the other way round. Means assistant professor should get 8 students, of course associate professor 8, and the professor will be 4 because the professors are mostly running around here and there and taking care of the institute. That is one suggestion which they have given. Hope the HBNI committee may kindly consider this request. Yeah, there is the second requirement. There is called a subsistence allowance. This subsistence allowance, I would like to highlight a bit about the subsistence allowance, where the students, those who join in the PhD program, those who are getting the institute fellowship, they will get a 5-year scholarship. Similarly, we also have in addition to the institute fellowship, we also have the students from CSR fellowship, where the CSR student get funding from the CSR, and both the people, institute fellow as well as the CSR people get the funding up to 5 year, absolutely no problem. They get funding. Now, the problem goes to the 6th-year student, where the 6th-year institute student get the subsistence allowance, and there is the problem with the CSR students, whether they will get the allowance or not. And the CSR student always comes and complains that we are not getting any support from the institute. At least why don't you consider those 1 year, whatever the subsistence allowance which you are giving to the institute student, the same amount, why don't you give it to us? Of course, we have put it back, this proposal to BOG, and our BOG suggested that HBNI can, whatever the policy adopted in HBNI, you follow the policy in HBNI. Of course, we will formally write this information to HBNI so that part will be taken care of, and our CSR student will also get the subsistence allowance. Now there is one more issue which is mainly we discussed so many times about the contingency grant of 20,000 rupees, where the PhD student get the contingency grant. That out of 20,000 rupees, the rule says mainly used it for the consumer computer, purchasing computer or computer peripherals or the books, and we cannot use that rule for the purchasing consumables. Where the rule is very clear, which we cannot change the rule. And the only possibility, of course, the order came from HBNA, and our dean also, based on that order, which he has implemented that rule. And now the request comes from all the faculties that they have to make use of this 20,000 rupees. So we will be in touch with the HBNA so that consumable word can be included in the order, so that we can make effective use of that 20,000 rupees. And now, so far, and there is one more from the faculty affairs section. There is now there is the issue comes with the student for getting the doctorate degree certificate. So earlier it is only sometime in June, all the students get the degree certificate, whether the PhD student finish the PhD program sometime in August. Of course, he will get the professional certificate immediately. But getting the degree certificate, they have to wait up to sometime in July. And where this degree certificate is really essential because they have to get the postdoctoral position. And we were also in touch with the HBNA. Hope at least they will consider the case, and instead of yearly once, and they make it to yearly twice, or even yearly 4 times also, it is fine with us. And I hope they will consider our request. And so far I talk about the faculty affairs part. Now I coming back to the department because I am part of the chemistry department. where the faculty will not allow me if I don't mention this point before going to the things, before going to the department meeting. And as part of the BOS, we always have the issue of publishing 3 papers. That is compulsory for 3 papers to get the PhD degree in HBNI. That is, that rule made it somewhere in 2016. Earlier it was 2, and the rule changed to 2016. Now 3 papers are compulsory. And my colleagues in the department meeting always tells that the colleagues, those who are sitting in the board of studies, never come forward and help us. And they openly made the statement. So the requirement now here is either we can go back to the original rule of instead of 3, we can make it to 2, or on par with the other school, make it to 1. That will. The problem here is the publishing premature data. They don't want to do it. They wanted to publish a very good quality paper. For that, they wanted to keep the results pending. And finally, they will not be in a position to publish 3 papers. The requirement here is make it to 2 or make it to 1. That will also be very comfortable for on par with the other schools. That these are our requests, and I hope this will be effectively considered by the HBNI team. Of course, this is the right forum to discuss those points, so which I have mentioned all these points here. And I will also come back during the validity meeting. Hopefully, I will because I have to run around for all the other meetings. But definitely, I will come back to validity meeting. Hope to hear some positive information from the HBNI team. And finally, I would like to thank Director Naisar. Even in his busy schedule, he has kindly agreed our invitation and mentioned that he will be part of this inaugural function. And I also would like to take this opportunity to thank our convener and co-convener for tirelessly working for the last 1 month along with our colleagues and make sure that all the arrangements are arranged properly and make sure that on that they have arranged all the things. And thank all the colleagues involved in the audio video visual system and student volunteers for their efforts put in. I also take this opportunity to thank all the sponsors, not only from the plan project, which we have also got some support from the sponsors. I wholeheartedly thank them for their generous funding. Finally, as we don't have the dedicated guest house, for this dedicated guest house, which we have also had a meeting with the BOG, and BOG now kindly agreed to construct a 100-seater auditorium, hopefully, 100-seater guest house. So hopefully that will be constructed. It will maybe 2 years or 3 years down the line. Hopefully we'll be in a position to construct the guest house. And as of right now, we don't have the dedicated guest house. We have accommodated all our colleagues in the quarters. If any shortcomings are there, kindly inform us so that we'll try to address those issues as quickly as possible. Thank you very much for all of you, and I hope this meeting will be successful.
With this, we conclude this inaugural session. I thank once again all the dignitaries on the dais, and we'll go for a tea break now. We'll assemble at 10:45. I have one announcement to make. The poster boards are ready. So all the students who are presenting posters, they are requested to put up their posters, all the posters. But today only 1 through 25 will be evaluated. But you are supposed to give all the posters today. Okay. So we'll come back at 10:45, sir. Thank you. I go. You can delete those. Yeah. Or you put it outside. Yes. No, it's on the same place. Like top stuff. No. Top right? No, okay. Different time. People. PowerPoint is a PowerPoint. Once again, can I just let you say this is the slide? Okay. You just take this is for the computer. I said. Can I just go back a day? If it, yeah, this is the morning of the. I'll just come. I'll just fix this. It works. This one is better. Can you look at the slides? That's
Which brings us a conclusion.
Maybe just skip this whole thing. Maybe others can edit it.
Delete the other thing. Next question.
Return to the delete.
एक बार और question दे दो. It's fine. Hmm.
Yes.
Full screen.
I'll be using it.
Take.
I'll be using it.
Okay, actually. Okay. Yeah. Actually, which I did remember.
Thank you very much. Okay.
Yeah. Ida. Windows setting, right? Ah, the WebEx. Right, so.
Because too much crowding. Already 200, already 200. Then that's
the amount of presentation work. I'm one. Like so. Okay. Okay. I think that I've done. I presented. Yeah, I can change. Yeah, it's coming on the file. Share again. Share the entire screen. Okay. Light bulb. Not after laptop. Laptop. Right, because you told me to hide it. Yeah. So, but I have to share it. Yeah. Yeah. There. Yeah, I am excited with it. It's the screen sharing stuff. It's sharing.
Just one.
Welcome back. It is time that we start our first academic session. This session will be chaired by Dr. Malay Sarkar of SCS Niger. Dr. Sarkar has obtained his PhD degree from the University of Hyderabad in the year 2007. He joined Niger in 2009. He is one of the first few faculties who joined Niger in the SCS department. Currently, Dr. Sarkar is an associate professor in SCS. His research interests include developing novel nanoscale hybrid materials as efficient light harvesting system. Also, he is interested in studying the interface of nanomaterials in presence of biomolecules. With this short introduction, I now request Dr. Malay Sarkar to please take over and chair this session.
Thank you, Arindam, for the nice introduction. And let me also thank the organizer for giving me this opportunity to chair this session. So, a very good morning to all, and a warm welcome to all of you to this technical session. So, as you know, there are 4 talks lined up in this session. The first one is the keynote lecture, and the other 3 are invited lectures. The keynote lecture will be delivered by Professor Sundar Gopal Ghosh from IIT Madras. The duration for this lecture is 1 hour. So I request the distinguished speaker to at least give 10 minutes time for the discussion. So it's an honor for me to introduce Professor Ghosh to this audience. Professor Ghosh obtained his BSc and MSc from University of Calcutta. He then received his PhD from IIT Bombay in 1998. Then he moved to the University of Notre Dame, USA for doing postdoc with Professor Thomas Feltner. After the postdoctoral stint, he joined the Department of Chemistry at IIT Madras in 2005. His research interests include transition metal boron compounds and their application in catalysis and small molecule activation. As on date, he supervised 27 PhD students and published over 260 scientific publications in international academic journals. For his contribution in chemical sciences, he was awarded with various awards, to name a few: CRSI Bronze Medal, Institute Research Development Award, IRDA Award, Professor Priyodaranjan Roy Memorial Award, etc. He is also an elected Fellow of Indian Academy of Sciences and Fellow of National Academy of Sciences. With this, I invite Professor Ghosh to deliver the keynote address on structural paradigms in metalloborane chemistry. Sir, the stage is yours. Put it here. Small note.
Okay, good morning and welcome to my talk. Before I begin, I would like to thank this entire organizing committee of the HBNI, in particular the Saranapa, for the invitation to share some of the results that I've been doing in IIT Madras. This is one of my very favorite places. I keep coming to this institution for various reasons. And one of the main reasons is like a good food here in Bhubaneswar, and meeting many of my friends, colleagues who are in this institution, whom I know for a long time. Okay, so what I'm going to do today for another 40 to 45 minutes, just show you my journey from 2005 that I started at IIT Madras. That includes different structural paradigms in boron chemistry. And I'll show you some of them. And in particular, I'll be talking some of the very interesting molecules that you see some of them over here. in which you all know the benzene, and it's been target for several years to have a benzene-like structure with all 6 boron. And there are other elements also, like boron. People have been trying to make it. One of the reasons why people are interested to make this molecule, so this is one of them. This is not my molecule. This is one of the molecules I took it from Stephanie Denon, who is the chief editor of Inorganic Chemistry. And this molecule, this you could see that there are 6 bismuth, but it's in a trigonal Prism geometry having 3 ruthenium CP ring. And this shows some fantastic aromaticity. I'm not going to talk about this because this is not my molecule. However, there's some connection with this, with some of the group 13 elements as well as the heavier elements. So before I go into my talk, I would just like to show you some of the importance of the boron compounds. Can someone help me? Yeah. Not it is not connected. Not this. Should go down from here, right? It's okay. Can I use this? Thank you. I don't know. Yeah, it is. Thanks. Okay, sorry about the interruptions. Okay, so I'm going to drive you some slides that would give you the importance of several boron molecules that people have been engaged making them for various reasons. You know that since the boron became active, which all these things started in 1950s when all this pentaboron making started. But after that, a lot of research, in particular, like in this molecule, the hydrogen storage material for the amine boron complexes. Then you have this molecule is a fantastic material for boron neutron capture therapy. And then you have your borons in medicine, boron nitride, boron borides, borosilicate glass. And this is another very important molecule made by Christopher Reid in Riverside, in which he had chlorinated all this boron in a carborane that turned out to be a fantastic super acids. and it was reported some 2 decades back. And then this is a very recent development on the borofin chemistry, that same as what you see with your carbon analog. And this turned out to be another very interesting molecules in terms of its property. But nonetheless, other than that, the graphene that shows a lot of properties, this molecule has a hexagonal hole in the middle, and that can give a different properties in terms of the applications is concerned. The only problem with this molecule is that you need to make this in a bulk quantity, which is not happening till date. Then this is another interesting molecule for many of you to be knowing, that magnesium boride, which is known for a long time. However, it turned out to be an exciting superconductor that was found in 2001. And as you see, all these properties of this material. And there are many others, but I don't want to go through all those details. But the recognition on boron chemistry, it started since its beginning of the Alfred Stock. And it started with E.R.E. Williams, who made all those things which is available in your textbook now these days, orthocarbonane, paracarbonane, metacarbonane and all. So he is one of the pioneers in this. And then you all know hydroboration reaction by H.C. Brown, who got the Nobel Prize also on the hydroboration chemistry. Mingo's, many of you will be reading the Wades-Mingo's rule in your textbook. Then you have your Suzuki, who was also associated with H.C. Brown, got the Nobel Prize in 2010. And this is the Wades, and this is the Lipscomb, who also got the Nobel Prize for the structural illustration of the borate anion. Woodward Hoffman was very much associated with the boron chemistry in terms of the Woodward Hoffman rule with isolable analogy. You must be knowing this gentleman in IISc Bangalore for his discovery on the MNO rule, which many of the rules developed by Ken Waits and the Mingos that cannot predict what was some way supported by his MNO rule. This is one of the very young scientists in Germany whom I was associated in Humboldt. He made the first time a BB triple bond in boron chemistry. So there are many more are there. I didn't have any space to talk about it or list it. This is one thing, I really like this periodic table. This is stolen from the Lipscomb website. So I'm going to show you some chemistry, keeping in mind the boron and all the different transition metals, starting from your early transition metal of the titanium all the way up to cobalt and nickel. Okay, as you have seen that boron being next to carbon in the periodic table, it shows a lot of interesting properties that goes with that of carbon. So as you see here, the molecules that is like a borane, boryl, boride, borylene, these are all available in your carbon family. Similarly, in the aluminum chemistry, you do not see that much of structural diversity as you see with boron. And this is one of the reasons boron can offer a varieties of bonding that people have utilized, particularly with the behavior of, like 3-center 2-electron bonding and so on and so forth. So it has all different types of bonding, starting with this is a dihydroborate, and this is a dihydroborate, this is augustic interaction, all those so on and so forth. So we had a recently accounts on this 2021, and that talks about all the various molecules that is listed in this act. Okay, earlier when the boron chemistry started, it was all started with a preformed borate anions. So there was no particular reason that you could develop the boron chemistry, and like the other element in particular, boron also mimic the carbon, and all the molecules that is listed here, see, this is ethylene. It has an analog with a boron. This is a 3-carbon, this is a 4-carbon, this is a 5-carbon, this is a 8-carbon. So this is a typical mimic in the classical organometallic molecules that is been done with the boron compound. And one of the very important molecules that people had used to develop this boron chemistry was the pentaboron. Pentaboron, you all know that this is one of the molecules the US Air Force wanted to make it in a long time when the United States and Russia, they're having a Cold War. And that time, US Air Force wanted to make this pentaboron in quantities so that they can use this as a rocket fuel. However, for various reasons, this did not work, and you all know why it did not work, because it formed a B2O3 and the H2O. That reacts again to give the boric acid, and this program was completely failed. So what happened? So they made a huge amount of the pentaborans. As you could see here, this is the pentaboran storage site at the California base. And they had to destroy the entire pentaboran they had synthesized. I was very much that time in USA when the program was still on, and they had to kill this, and they wanted to call people who are actively involved in the boron chemistry, and they asked the labs if you can use this pentaboron, you can take it as a gift. However, you have to take the entire cylinder. You cannot give it in a small quantities. So that was a problem. You don't want to keep an explosive chemical in the lab. So none of them actually borrowed, so they had to kill it. And it was, I think, 1999 or 2000, they had to destroy all this. Okay, with this, I just need to move on to the chemistry that we develop in our laboratory. And these are all the different starting materials that we make, or some of them we buy it from different vendors that's available in India. Many of the molecules you cannot get it because it has to be, like come from outside. And so this is a forbidden chemical. And they are mostly a bimetallic or monometallic chlorides or hydrides. And making this molecule is extremely difficult, in particular the weather in Chennai, because it has a lot of air and moisture that will kill your molecule. Nonetheless, we had some success because of some of the very good students. And what we do once we have this starting material, we simply, as I told you earlier, that the people used to make this pentaboron as the starting material. So we had to come up with some different reagent. And what you observe that the lithium borohydride or the sodium borohydride, it could be a fantastic material to develop further chemistry on that. So we do a lithium borohydride, take a cyclopentadienyl metal chloride. We treat this with lithium borohydride. It's a fast metathesis reaction. It goes to lithium chloride and it makes the polyborohydride complexes. Now this molecule is extremely unstable. What happens? It releases boron and it gets this metal hydride, which is not your desired product, because you want to have a boron in that transition metal. And another pathway, it releases hydrogen and get this metal boron complex. So we had success using this strategy. And here I'm going to show you some of the research interests that we have in our laboratory. This is one area where we make a different metal clusters molecule, both with a transition metal early and the late. So the interesting part, if you look into the late transition metal, as the d orbitals are completely or almost filled, you do not need enough electrons to get the structures. However, if you look into the early transition metal area, it has a very few number of d electrons. What happens? It has to be fulfilled by the hydrogens. As you see, there are so many hydrogens are there to fulfill the electron counting of those transition metal. And because of that, these molecules are extremely unstable, and you cannot deal this molecule if you have air moisture in your system. Then this is another area where we develop a simple, like utilizing the bonding diversity of the boron that can offer with the transition metal. So we have a different like silane activation, boron activation, and we do a lot of hydroboration reaction for the synthesis of organoboron species. Then we have, this is one of the silane activation, and this is recently we have got something with the phosphine activation also using PH2Cl. Many of them are listed here. The Dalton, we have all the hydroboration reaction. This is recently review. These are all review, and you can go through them for details of this reactivity. This is one of the very new area that we have developed in collaboration with IIT Bombay, Arnav Datta. What happens, as you know, that your nickel Fe or the iron, the nitrogenous molecules, they can release hydrogen, and one of the intermediates for the hydrogen release is the metal H metal, that the bridging hydride. So we had, by accident, we had developed some molecule after we get the first molecule with the manganese and the cobalt. That turned out to be a very fantastic molecule for the release of hydrogen. So this appeared as the front cover in organometallics. It has not been appeared yet. But what we are going to work with the collaboration at IIT Bombay is that we will be developing a lot of molecules here. As you see that these molecules are extremely important in terms of their the property, in particular the electrochemical hydrogen generation, so on and so forth. Okay, so this is another area we are also interested in. One of the molecules that I had shown you earlier, this is one of the review by Stephanie Denon, and this is some molecules in which you have a trimetallic clusters. That shows a sigma and pi aromaticity and the trimetallic clusters. In this case that I have listed here, the sigma aromaticity observed with the gold 3, zinc 3, and the thorium trimetallic cluster, and the pi aromaticity observed with the gallium 3 and the PD3 molecules. So in this connection, we had made some clusters in which you have a tantalum, tantalum, tantalum trimetallic cluster that also shows some kind of sigma aromaticity. Not as good as the others reported, but we can see some aromaticity with this molecule. Okay, so now I want to show you some of the very interesting molecules, starting with your first one, in which you have one of the boron got stabilized. This is called the borylene. Borylene, you know that it's extremely unstable. It's very, very difficult to isolate. There are a lot of people working. I had listed all these people here who are involved directly or indirectly. That Hartwig, the Holger Braunschweig, Todd Marder, Simon Roldes, many of them, and in which you see this is the borylene, the BH, it has a different structural varieties. This is the terminal borylene that you all see, it is the carbene, Fischer carbene or the shock carbene. Then you have your terminal, they have a doubly bridge, triply bridge, base stabilized, T-shape, semi-bridge, so on and so forth. So you also wanted to make a borylene complexes that could be stabilized in the coordination pair of transition metal. Now, one of the very good approach we took, that was the isolable analogy. We had this molecule made some time back. You see there are two boron. So we thought, is it possible that we can get replaced with the isolable FeCO3 fragment? Indeed, when you do the reaction with the metal carbonyl, what happens? It can simply take one of the BH with the isolable metal carbonyl fragment, and we have made a series of molecules. We have recently made a coordination chemistry review. See, one of the good thing about this, the COVID, was we could write a lot of review articles because the people are not involved in the lab. So we had made at least 8 or 9 review articles during this COVID time. So that was one way very fruitful that we could list entire the work that we had done in IIT Madras. Okay, so the next one, I want to move from one boron, the 2 boron molecule. So this is one molecule that is a diboron B2H6, in which one of the BHB got replaced with FeCP CO2 fragment. And this is one of the molecules made by Sheldon Shore, who was also involved in the pentaborane that US Air Force making, because he was very much into pentaborane, and he recently passed away from Ohio State University at the age of 93. So this molecule, as you see that, so we wanted to see, is it possible that we can make this with a different transition metal? So we treated with a pentaborane metal analog with a benzothiazole ligand. I'm not shown that chemistry part, but I just wanted to show you the structure in which you see that this is a diborane in which the metal is Cp star is replaced by one of the hydrogens. So that way you can get, this is the first structurally characterized neutral ruthenium diborane 6 analog, and the other properties are all more or less similar to that of this molecule. So the next one which I wanted to show you is with the same diborane molecule, but with a different transition metal. We have seen it with the late transition metal. Now I'll slowly switch how it behaves if from go to that late to all the way to the early transition metal up to titanium. This is one of the molecules was available made by Simon Rollrich in Oxford. This is the diborane. We wanted to remove this chlorine and see whether it can be a diborane 4. Indeed, when you do the reaction with the CO gas and we get a diborane 4 molecule, this molecule was extremely unstable. As you could see that at the room temperature, there is no NMR signal. However, if you lower the signal up to minus 80 or so, you could see all this signal slowly comes out. And this is the X-ray structure. She got it after a lot of struggle with the molybdenum. So in this molecule, the BB bond distance of this is 1.7 angstrom. Now, this molecule is exactly similar to the molecule that is made by F.A. Cotton. Many of must be knowing of F.A. Cotton's textbook. Although these days, after the 6th edition and Cotton also not there, no more edition happened. Not many people follow this F.A. Cotton textbook though these days. Nonetheless, he made this molecule in 1978. This is the acetylene molecule. And the molecule that I had shown just now, this is exactly same as of this acetylene. So this you can consider as a true mimicking of this organometallic species. So we wanted to see whether this B2H4 is a true mimic of the acetylene or not, giving 4 electrons to the metal center. Indeed, it does 4 electrons. I'm not going the theoretical part, which we did with Jemis. Now, once we have this B2H4, as you know that B2H4 could have all these different isomers, and except this CS symmetry, all the other diboranes are known structurally. So this was one of the diborane was missing. Now, after the isolation of this, now we could see that all the 4 isomers now available structurally with a transition metal. Now, once we had the diborane, we wanted to see whether some of the hydrogens can be replaced with a metal carbonyl using the isoelectronic isolable analogy. We treated with tungsten CO4, which is equivalent to 2 hydrogen. And indeed, when you do the reaction and we get this molecule, if I show you the structure, you will probably connect it. Now, if you see the diborane 4, which is a bond distance of 1.7, the moment you take 2 hydrogens, it's basically become a BB double bond. And you see the bond distance become 1.5. So that means it's a typically diborane to diborylene. And we have all those molecules structurally characterized with tungsten as well as with the molybdenum. Okay, so this is one of the very, like a classical examples of a diborane chemistry. You all have seen diborane, which is typically known as a non-classical structure. All the molecules so far you read in your textbook, these are all non-classical, in which you have a BHB bond. But there are no examples known in which you have a BH3, BH3, no bridging hydrogen. So we wanted to see if something molecule can be synthesized. And in that connection, okay, as I said that you see all these molecules, you have a BHB. So they are typical examples of B2H5 minus, in which you have a non-classical structure. And these are all those people, including one of our example, 2014 we made. So we wanted to see, as I said again, that we wanted to move to the early transition metal. So we treated this tantalum Cl4 Cp star with a boron reagent, which we have developed in our laboratory. What we see here is that it's a diboron in which you have a B2H6. And initially, when we got this structure, we thought got this molecule and recorded the NMR, we thought probably this is the B2H6 having a BHB bond. But if this is the case, you cannot have a chemical shift difference of the boron NMR of around 50 ppm difference. So then we send this one for the publications. And one of the reviewers pointed out that you cannot have this molecule where you have 11 BNMR of 50 ppm chemical shift difference. So he spoke to James and he did a fantastic calculation. It took long time to figure it out because we are not able to do anything about this molecule because there was no way we could put the other hydrogen in this molecule. So we got the structure and it was after a long struggle. And what we observed that one of the hydrogens, that is a tantalum H tantalum, observed in this and a B2H5 in which you have no BHB. Now with this structure, we calculation and everything done and fantastically it matched. The reason why we missed it and the student also is typically the metal H or metal comes in the off-field region. And the signal, one of the signals which always student, when I used to ask, so this is impurities, don't worry, it keeps coming. Then we did the calculation and we found that this peak is actually this one. And now you see this, all the calculation and all done by James is the most stable one in which you have a tantalum is tantalum, and that very well goes with the theoretical calculation and also with the X-ray structure. So this is the one I was talking about. So we, in the same year, Douglas Stephen, many of you will be knowing about Douglas Stephen, who is famous for the frustrated Louis pair, inventor of that. So he also made a molecule in which you see this is a B2H5 cation. What we published, that was B2H5 anion, a classical one. This is a diboron cation, and it appeared in the same year, 2019. And as you see here, this is the B2H5 in which one of the hydrogens is replaced by the mesitylene. This is the first structurally characterized B2H5 plus. So now one of his colleagues wrote to me that now I can use both the B2H5 cation and the B2H5 anion in his class. Okay, so once we had this, we wanted to see whether this B2H5 can be treated with a metal carbonyl, can remove some of the hydrogens. And what happens in this case, it does not go with the replacement of this two hydrogen replacement. Instead, it simply coordinate with one of the borons of this diboron and it form a coordination complex. And this is the X-ray structure. As you clearly see, this is the diboron and molybdenum is coordinated with one of the boron. Now, this is the 11B NMR of the starting material of the diboron, and once it coordinates with the molybdenum, it goes to the downfield signal. Now, if you clearly look into the diboron, so this hydrogen, when we did some calculation, we found that this also switched between this tantalum and this tantalum. And we did some calculation, as I said, and we did the low temperature NMR. And when you do the low temperature NMR, this is the NMR of the signal at the low field.
and it clearly resolves into 3 peaks when you lower the temperature to -70. So this is a very clear examples of how nicely molybdenum is switching between these two tantalum metals. Okay, so as I said that this is the molecule that was there in my the title at page, the B2H6 molecule. This is a dream for many chemists. Always wanted to have a B6. I made this B6H6 molecule some long time back when I was in US. However, the B6H6, the parent one, was never been made. So this had been a dream to all the boron chemists to make it. And after a lot of, like a debate calculation on this molecule, what it turned out to be, you cannot stabilize B6H6 unless you have this mechanism of making this molecule as a reverse sandwich of this using this vanadium or the tantalum. So the vanadium and tantalum, this is one of the most difficult, the precursor to synthesize. However, lately, last few years back, we made this tantalum Cl3Cp star analog, and using that, we treated with a lithium borohydride. And what we see here is the B6H6 ring, which is sandwiched between 2Cp titanium. And all those NMRs and everything you just asked me is a crystal clear. There's no it's very self-explanatory. I don't have to explain anything. This is a single boron. This is the HSQC for the metal HB and the BH terminal. It's very clear. Low temperature, there is no fluctuality involved at all. And this is the molecule, the B6 molecule that's sandwiched between the two titanium. This appeared just last year. So theoretical calculation again, what we observed that we have a different kind of electron counting rule that talks about your Wade's rule, Mingo's rule, Jemis MNO, and to calculate this a sandwich molecule, we have a different electron counting. What they do is that when you have a triple decker sandwich species, you should have a 30 or 34 valence electron count. If you have the electron lower than that, what will happen? It will become a puckered ring. And exactly we observe the same thing with our B6H6 also. And one of the reasons that it gets puckered is that the DG square orbital actually very nicely, it can interact with the plane of this B6H6 ring, and that can make this titanium-titanium bond a kind of stronger, which squeeze this, and eventually the results into a bit puckered from the planarity. Okay, so this is one molecule that I was talking about. This is an extremely important molecule. So Stephanie Denon was in IIT Madras just a couple of weeks back. So we are talking to her, and I was showing my molecule B6H6. Then she only mentioned that we have recently published one paper in Nature Chemistry in which you have a Bismuth 6 with a trigonal prism geometry that shows a pi aromaticity. Now, I'll just quickly tell you what is this different sigma, pi, and the phi aromaticity. So the sigma aromaticity, if you consider this C4 ring in which the angular dependence is a part of a S-type atomic orbital, and the pi type you all know that is the benzene type of planar cycle, and the phi one in which she observed in which you have the angular dependent part is an off of FZ cube atomic orbital. So with this, we do collaborate with her. We had sent some of our early transition metal precursor to see, in this case, as you see here, this is a ruthenium CP. We wanted to see whether a similar kind of molecule can be synthesized using a titanium or vanadium or the tantalum that might show a different aromaticity altogether if these are synthesized. Okay, so this is another interesting molecule. If you, again, it's a textbook material. If you look into your textbook, that B7H7, you will not find much chemistry there. One of the reasons this molecule was not there is that it's very, very unstable. The moment it forms, immediately it goes to B8 molecule. And this is the history why it is not listed in the textbook. It starts with the Frederick Hawthorne in 1959, and it goes with the Lipscomb, and as you see all those things, I'm not going in details. But one of the things, it was mentioned that in 1967, the B7H7 is very, very unstable. It's partially characterized, but it was proven to be very, very difficult. So we are interested to make this. One of the projects that we had, it was a zirconium. And again, with the lithium borohydride, we get a triborane analog. Other than this triborane, when you change the reaction conditions, it leads to the formation of some a molecule in which this is the typical NMR. And we have the mass of this. It very clearly goes with a B7H7, in which you have a two early transition metal kind of pendant stabilize this. So this is the first molecule where the B7H7 is stabilized and gives a complete support to have a neutral one. So this is a very nice results. We wanted to go beyond B7, and the next molecule, it was the B8 one, and B8H82 minus is another molecule in which we don't have a clear structural clarity. It's still a mystery in terms of when it comes to the solution. And that's why I didn't see that there are a lot of studies, particularly most of them are theoretical studies. What is the exact structure? Why you do not need 2 electrons to satisfy the Mingo's or the Wade's rule? So we did the same strategy, and one of the things with the B8 molecules is known the D2D, C2V, and D4D. In solution state, the existence of dodecahedron, which is the B8 one, is a D2D structure, is this, is still a mystery. Both the theoretical and experimental chemists, the dynamic NMR behavior of the from these studies, it shows that it's a bicap trigonal prism and the square antiprism. So first time we have shown that in the X-ray structure, both in the solid state and in the solution, it has the same kind of structure, that is a dodecahedral one. So this is this gives some clarity what earlier both from the theoretical study as well as experimental was not sure whether it's a trigonal prism or the dodecahedral geometry. So this study shows that some extent this is the one, the dodecahedral one is the structure both exist in solution as well as in the solid state. So this is summary of this study. As you see here, that all these boranes are known, which is the B6H6, this is the B8, this is the B10, this is the B11, and this is, of course, the icosahedral B12. So we wanted to see whether this molecule can be trapped between these two transition metals. So we are working on this area also to see some other clusters, in particular, the clusters which are beyond icosahedron or more than 12 vertices of boron. Okay, this is the one I was talking about. This is the icosahedral geometry. These are all listed in the textbook, particularly when it comes to the boron chemistry. And these are the studies by Lipscomb during his Nobel Prize time. He predicted that it's not only the icosahedral B12, H12, 2- is stable. There are other counterpart also possible to synthesize if you have a proper synthetic method. And this is the one, the lowest energy. This is called the icosahedral sink. And of course, this is the reason why you get always B12, or if you consider it's a carborane, it's a B10C2. So this geometry, B16, this is called the square crown geometry. This is one of the geometries that was very much predicted with a cobalt CP analog. So we are into this game. We made this molecule, but as you could see here, this is only 12 boron, and in which you have a metal-metal strong bonding that makes the cluster extremely oblato, and it's a very, very electron deficient molecule, and this is one of the reasons why this molecule does not follow any of the electron counting rule that's known till date in the including Jemis MNO. However, this is a theoretical study predicted by all these boron chemists. And what it says is that if you can replace the axial one with a metal CP having a diffused orbital that can coordinate with your 6 boron atom and stabilize this. And this was one of the approach also adapted earlier by Friedrich Hawthorne in 1971, and he made this molecule, but that was only with the metal and carbon and the boron. It was not a pure boron clusters. So again, the game was on. People wanted to make it. So we are also into this game. We made this first time a 16 vertex cluster that was reported in 2013. And later on, as it was predicted by Lipscomb that it can synthesize this with the cobalt, we made this, but in this case, what we get here, it's not, although it's a very huge number of boron and the metal, but it's a kind of fused cluster. It's not a pure cluster. These are the 3 geometries. This was made by us in 2013. And these 2 made by my good friend in Hong Kong, that is a carborane. So this one, you see, this is a B14C2. This is the first stable carborane synthesized with a 16 vertex. This was reported in Nature Communication in 2021. All right. Now, if you ask me what is the geometry of this, of the 16 vertex that you have synthesized, so this is the molecule. So if you take a simple tetrahedron geometry and you chop all the 4 vertices, what you generate is a hexagonal face. So you generate 4 hexagonal faces. And as I said that now in these 4 hexagonal faces, if you have a diffused metal CP ring that can simply coordinate, or you can cap the 6 face and make this molecule. So it is known as tetracap truncated. So this is a truncated tetrahedron, tetracap truncated tetrahedron. So this geometry is different from the geometry that Lipscomb proposed in 1970s. And this is actually goes with the one that is made by Zoe Z in Hong Kong. Now, whenever, like one of the very important exercise that I always ask my students is whenever you get any molecule, do the electron counting. And the electron counting of this fused cluster was very difficult, but we have some student who got a properly trained, and I also always in touch with Mingos and others to calculate this kind of difficult electron counting. Now, as you see here, I'm not going in details, but it's a bit complicated, but it very nicely matches both Mingo's rule and Jemis MNO. All right, so this is one that I was talking about, how he made the first 16 vertex carbon compound. What he has taken is that you take a 14, 15, and if you take with excess of sodium THF and T2 with the H boron Br2 SME2, it simply cap this and you can get this 16 vertex carbonate. So this molecule was very much into the news because this is the one that gives exact structure that was proposed by the Lipscomb. Okay, along with the formation of the titanium B6 that I have shown, that shows a reverse sandwich B6 molecule, almost planar ring. This is another molecule in which you have this one, your icosahedral, and here you have a B8, a octaboron got fused. And this is the molecule, the 16 vertex oblato hypoclusters. And this molecule turned out to be the parent of 19 vertex. So you can consider this is the first time a cluster having a parent of 19. So far, in any textbook, you find a single case clusters known till date is 16. You have earlier icosahedral that is very well known in the textbook, that is a B12. Then later it was 2003, it was almost like 60 years later, the 13 vertex, and then it started 13, 14, 15, and then it stuck at 16. We made this molecule at 2013. Then almost 10 years later, Zoezy made the 16 vertex with a carborane. Now this is one. Now we can consider this is a 19 vertex parent, almost the 3 vertices more than what is known till date today. So again, we have done a calculation, and this molecule was under different reaction conditions. This is a 16 vertex. Now in this molecule, as I told you that many of the molecules that is synthesized or available in your literature or in the textbook, they don't follow Mingo's, but somewhere we tried to fix this with the Jamis amino, and it does obey that rule with these clusters. Okay, with this, I'm going to summarize my talk. What I had tried to give you some glimpse of a different structural paradigms, like in bone chemistry. One of the main research areas that that is running in our laboratory is that a clusters, metal clusters with a polyhedron boron geometry. And this is one of the very important molecule I have shown, B7. This is the 16 vertex. Now, whether it can be expanded beyond 16, we do not know. We are working this molecule with a theoretician and see whether this can be considered as a parent of 19 vertex. These are the first time molecules that I had shown you that shows a classical diborane, and this is the coordination with the molybdenum. This is a very new area that we have developed with the heterometallic bridge chalcogenide hydride complexes that turned out to be a fantastic material, or you can consider this as an intermediate in many of the hydrogenation process of the nitrogenase. And these are the 2 important molecules. This is the B6, in which you have almost a planar B6 ring first time. This is the B6H66 minus. So you can consider that as an analog of the benzene. And this is one thing which I just touched upon of some of the hydroboration reaction of a bis dihydro. You see this is 2 hydrogen on this side and the 2 hydrogen on this side, and you have a ruthenium. So this is a bis dihydro species. That is a fantastic material for many of the hydroboration reaction that I didn't cover today. With this, I would like to thank my group actually who made the major work. Some of the earlier talk I talked today, it was a Bijan Mandal who is doing a Humboldt, and Ranjit Bagh and Kaushik, now he is also in Humboldt fellow. Geeta Rani, who made all those, Diborane, who is in IC Bangalore, Bose in Jain University, Yuvraj, who worked on some of those borylene stabilized tetrahedral complexes. He just got an offer from IIT Palakkad. And 2 of my very favorite students, Saurabh Kaur, who made the first B6 molecule, and Anagha, who made the vanadium analog. My collaborator, E.D. Jamis, always I know him for almost 25 years, been very helpful in terms of any of the problem that we find in predicting or like getting some support in terms of the geometry. Laiseng Wan, Brown University for the B7 calculation. Arnab Datta, whom I'm working now with the materials, with the hydrogenation. And Babu Varghese, who really helped me in terms of the extra structure. All the time, what extra structure we get in this kind of molecule is having a lot of disorder. So he is retired now and he lives happily in Kerala. But now he's still helping me, and he used that money for the charity purpose. It was so nice of him. Still be in touch, and the Sudha Devi is also in IIT Madras, now taken charge of the Babu Varghese, helping us with the extra structure. All the funding agencies that DST, IIT Madras, CPPRA, CSR, CRB for helping with a good fund to do both fundamental chemistry and the application of this different boron molecules that we synthesize in our laboratory. So with this, I would like to stop, and I'll be very happy to take questions. Thank you very much for your time.
Is the floor open for discussion? Maybe you can identify yourself before asking question. Yes.
Hi, I am Vidro from School of Chemical Science, Mysore. I have two quick questions. First of all, exciting talk. I am referring to the molecule with the hydride bridge between two tantalum centers, also with the B2H5 unit. And as we expect, this hydride should come in the upfield range, right? But you didn't observe that. Why is it?
We debated a lot why it is. That is one of the reasons, like we missed it for almost a year to get the structure finally, and finally did some calculation. So we don't have a very clear explanation for that. But typically in the tantalum, like unlike like in the same series like vanadium or the niobium, that gives around like -2, -1, -3. But tantalum in particular, it comes little downfield region. We don't have a clear answer for this first part of your question.
Next quick questions, like a lot of exciting molecules, exciting electronic features, etc. But are there any real use of this molecule?
So that's what I told you, that thanks to all this funding agency for supporting and doing fundamental research. So this is a lot of the things that we do is a textbook chemistry. But lately, because the funding agency also now rejecting the proposal, so I have to come up with some application. So we started lately doing last, I would say 7, 8 years. So using that, I have not shown you, like a catalytic cyclic alkyne cyclotrimerization, hydroboration, making an organoboron molecule. The one that I had recently shown, that came in the organometallic front page, in which you have a heterometallic bridged hydride that turned out to be a fantastic material. Now we are working on how we can change this chalcogen, starting with the most of the molecule that is reported till date is with a sulfur. So we did with the selenium, and that is giving a better result. So these are the small thing we are working, but this is a new thing, because earlier my interest, I did PhD in Fischer carbon chemistry in IIT Bombay, and I did postdoc for more than 5 years, and I changed my interest completely into boron chemistry. And when it started, my interest was always to make a beautiful molecule clusters. But lately, I started getting into a molecular boron chemistry where you have a diversity in the bonding of this boron.
Sir, I'm Vasudev Rao. Your lecture was indeed very interesting for me. I didn't have any query, but after listening to the previous question, I have a comment. He asked a question about whether there will be any use for these molecules. I am triggered by that. And I want to mention that there's a great connectivity with nuclear reactor systems, because boron happens to be an excellent neutron absorber. And out of the two boron isotopes, boron 10 is the one which is better absorbing. But to make enriched boron compounds for use in reactors, it is a very big challenge. And because enriched boron compounds are obtained as boric acid.
Right.
How to convert that to boron carbide through a soft chemistry route has been always a challenge. So I used to always think I had a collaboration with one of the students of H.C. Brown also, he was in Chennai. Whether it is possible to make hydroboranes or metalloboranes finally which could be converted to boron carbide through pyrolysis or some route. This is what we were discussing. So some of these compounds can serve as intermediates for making boron carbide starting from boric acid. I don't have the answer of how it can be done, but that is a very exciting possibility of use later.
Yeah, I agree with you, sir, that the only problem, like most of the molecule, we always tag with a transition metal. And this could be, like the spoil. Yes. And that may not be useful. And these all exciting molecule, if you don't have the metal and they are not very stable, or we do not know what exactly they are. So this is a very challenging area. Like the one my friend made know that the B16, the B14 and C2. But these molecule again to make them, like in quantities, it will be a big challenge. But as you said, this can be explored in which you have boron and carbon as the.
Also, metallic borides, for that matter, europium boride and hafnium boride, and several borides have also been considered as important materials for nuclear reactors.
Yeah, the hafnium BH4
Yes.
oxides, and these are all borate, the coordination complexes.
Yeah, I am Tapan Ghanti from BRC, Bhagat Research Center. Excellent talk, particularly this Watt-Mingo's rule and electron counting rule, those who are familiar and that how magic works
Yeah.
with electron counting. So really excellent talk. About 19 maximum vertices you talk, that is for metalloboron, right? Otherwise, B40 cluster that also exists with 40 vertices. That is experimentally
B14.
B40, 40.
So these.
That is pure boron cluster.
Yeah, so these are kind of, like, these are not a case clusters. They are not a case cluster. So, like many of the things proposed, most of the borophene or fullerene like structures and all. So they are not, what I'm talking about, a single cage.
Metalloboron.
Single cage, it could be a carborane or it could be metalloboron, but single cage clusters where have a defined geometry that only 16 known till date.
No, B40, that is also, it is observed experimentally, that is single cage only. That is, I don't remember, 2015 Nature Communication or Nature Chemistry, that paper appeared.
No, I know that. I
Yeah,
think this
so
Lysen
Lysen
Wang is the
right,
one.
right, Lysen
I know that. I was there. So he told. So these are, we don't consider, this is true. That's
Yeah,
the B40.
pure boron.
Right.
Yeah,
So they are kind of, these are all matrix isolation.
Yeah. And one more, which is not really question, comment, just for your information, that B12, H12, you mentioned, B12, H12, 2 minus. So B12, CN12, 2 minus, that is also identified. And then that is negatively charged B12, CN11 minus, but it acts as a super electrophile. So that is PANS 2019, that paper appeared. So
B12?
B12, CN11 minus, negatively charged, but it acts as a super electrophile. It was spontaneously binds with argon gas. That experimentally it is demonstrated and appeared in PANS.
Okay.
So that you may be interested with that paper.
Sure. Thank you.
Okay, thank you.
Sir, I'm Ramnathan from IGCAR Kalpakam. Excellent lecture, sir. Actually, I have a question with respect to the sigma type aromaticity. But in the case of pi type aromaticity, the delocalization is very, very important and it should follow the Huckel's rule also. But in sigma type aromaticity, this kind of cyclic interaction is possible.
You're actually asking a wrong person. So I'm sorry. As I told you, this is something which I just learned recently from the Stephanie Denan because he got the phi aromaticity, sigma aromaticity. So we also wanted to check theoretically whether that shows something or not. But that turned out to be, like the sigma aromaticity in which you have the is kind of S type of orbital. But other details and all, in particular, general to have knowledge, I do not know that I should comment on it.
Okay, sir. Because even in the case of cyclohexane,
Yeah.
because even in the case of cyclohexane, this kind of anti-periplanarity requirement is already present. And that, because the delocalization should happen, but normally hyperconjugative interaction is present.
Of course, delocalization has to be there.
Because pi electrons can delocalize, but sigma electrons are localized already. And if there is a room for delocalization, that can happen, right? And if there is a cyclic interaction possible, then definitely it should be very similar to pi type aromaticity. Thank you, sir.
Is there any other question? Okay, so if not, let's thank Professor Ghosh for the wonderful. I also request Professor Ghosh to be here. On behalf of organizing committee, it's my pleasure to present him a moment. Come.
Thank you.
Okay, now we move on to the invited lecture series. So the duration for these lectures is 30 minutes. So I request all the speakers to kindly keep at least 5 minutes time for the discussion. So I'd like to also make one announcement that, we had some interaction due to the WebEx. So we have now just stopped the WebEx and we are trying to fix it. As soon as it is fixed, we'll get back to that. Okay. The first talk will be given by Professor A.C. Vasikuttan from BRC Mumbai. AC Professor Vasikuttan obtained his MSc in chemistry from University of Calicut, Kerala in 1989 and joined BRC Mumbai in 1991. After his PhD from the University of Mumbai in 1998, he joined as a JSPS postdoctoral fellow at Osaka University, Japan, and he stayed there till 2001. He is currently acting as the outstanding scientist in radiation and photochemistry division BRC and professor in HBNI Mumbai. Professor Vasikuttan's research interests include the excited state molecular dynamics and to probe the intricacies of non-covalent interaction in suprabiomolecular system. He has more than 100 publications in high-impact international journals. For his scientific contribution, he was awarded with many awards such as Homi Bhabha Science and Technology Award and the Scientific and Technical Excellence Award from Department of Atomic Energy, bronze medals from Chemical Research Society of India, Japanese Photochemistry Association Lectureship Award, and Professor S.C. Mehta Award from the Indian Chemical Society. Professor Vasikuttan is also a fellow of National Academy of Sciences, India, and the Maharashtra Academy of Sciences. With this, I invite Professor Vasikuttan to deliver his lecture on functionalized supramolecular reactions. Slide.
Thank you, Professor Malai, for your kind words. At the outset, I would like to thank the organizers, especially organizers from NICER and HBNI for giving me this platform to speak for this short presentation. I belongs to Radiation and Photochemistry Division, which belongs to the chemistry group. We have several divisions under chemistry group with the different mandates, and we will have a few presentations from all these three: electrical chemistry, chemistry division, and radiation photochemistry. My colleagues will be presenting different aspects belonging to these divisions. And since my division deals with radiation and photochemistry, and many people are not aware of what actually radiation chemistry says about. So this term, this yellow part, the photochemistry is known to almost all the people, and so much work and on all the department. Photochemistry is a part of research area, but if you, it's a part of the electromagnetic spectrum. So people work in radio waves, microwaves, infrared, UV visible. So many activities are on, but you will see less activities in other departments other than DA, less activities involved in the high energy radiation. So when you deal with electron EV photons, that the photons energy is in electron volt, you excite specifically the molecules which are in the solution or in solid state, which have that photon energy, which can absorb that photon energy, and those whole Jablonski diagram kind of activities, photophysical properties involving excited state dynamics, intersystem crossing, triplet state, all those parameters comes into picture. But what happens when you move into a higher energy domain of electromagnetic radiation, that is the energies in the order of mega electron volt, million electron volt, MeV. Whether it will see the particular molecule, because it does not have any energy levels to absorb. So when this MEV and photons or high energy particles move through your solvent or your sample system, what it sees the whole energy is dumped into the solvent system mainly, or the molecule which it interacts. When photochemistry deals with exactly the solid molecules which are present in the solvent, where the solvent, the ionizing radiations deal with the solvent molecule or the interacting medium. And if it is water molecule, if we are dealing with a water solution, what you will have? you will produce a lot of radical ions in the system. So when you deal with a radiation chemistry part, you are initially generating these radicals, that is hydroxyl radicals, electron, H2O, all these ROS, reactive oxygen species in the system, and which will deal with your subsequent, the reaction subsequent molecules, or your molecule looking at an antioxidant or drug molecule, whatever solute you are adding, these are the primary species which see interacting. So these reactants are very important. You can see these primary radicals which are formed in radiolysis. That means high energy radiation. So that are important in biology because your metabolism also a lot of free radicals are generated, and those, how do you study those free radicals? Because you can generate by this method, you can take this compound and it may react exclusively with one of the radical by changing the conditions. So you have a lot of areas working in this area, drugs and antioxidants, water, structural materials for nuclear reactors, nanoparticles you can make using this electron, reducing electron, you can make nanoparticles, food and agricultural polymer. So these are different areas, and my colleagues work in gas phase photochemistry, chemical dynamics and kinetics, femtochemistry, where all ultra-fast facilities are available, supramolecular photochemistry, where we contribute little bit, nanoscience, photophysical studies on organic chromophoric dyes, and also radiation chemistry, fundamental studies on radiation chemical processes, antioxidant and radio protection. Polymer chemistry, radiation and photochemical process for back-end technology for the nuclear fuel cycle, and dielectric barrier discharge chemistry. So there are so many activities in each division like this. So we will be presenting a snapshot of some of the activities. Coming to my area of presentation today, that is functionalized supramolecular assemblies platform for unlimited opportunities. Why supramolecular chemistry is so important? Rather the way they are little bit simple in handling, but at the same time you have unlimited opportunities and which can derive several technological advantages by controlling their interaction. So you can see this supramolecular chemistry is derived from, inspired from the biological, most of the DNA molecules or proteins, which are naturally use this kind of interaction. That is, all these interactions are textbook interactions, that is electrostatic interaction, hydrogen bonding, van der Waals pi interaction, hydrophobic. So the power of supramolecular chemistry is from these non-covalent interactions, which we can use for many stimuli responsive activities. So in myself and my few colleagues work both look at the fundamental studies on just molecular assemblies. We use synthetic assemblies like cucurbituryl, calixarin, and cyclodextrin, and use a probe molecule, which may be a drug molecule, which may be a dye molecule, which may be a metal ion or oxide, and it see how the property can be changed usefully. And we also look at other parts, the biological template like DNAs and proteins, where specific templates are produced like G-quadruplex DNAs or the different folding topologies in insulin, its fibrillation or BSA protein. So for today's lecture, I thought I will go to the synthetic part, where these are the main very classical molecules, host molecules, cyclodextrin, calixarin, and cucurbituryl. So I will focus some of the studies with cucurbituryl, which is a relatively new kind of molecules, which has got a cavitant structure like this, with the size and dimensions are noted here. The beauty is that it has got a symmetric portals with the negatively charged carbonyl groups, depending upon the number of carbonyl groups, CB7, CB8, like that. That means each portal has got 7 carbonyl groups if you are taking CB7. And at the same time, the peripheral can activate a slightly cationic charge. So you have a hollow molecule with the 2 negative charge at either portal, and peripheral a carbon positively charged center. So using these several applications, several publications have come, several applications have come, several systems have been developed in molecular sensors, drug delivery, vehicles, catalysis, extraction and separation. So we will go to some of the beauty of this molecule. I just want to mention this is the basic idea in using supramolecular assembly or non-covalent interaction. The gas molecules, you have a host molecule, the huge host molecule, which is normally benign in terms of your photochemical excitation or even sometimes radiation stability, etc. But you are interested in the gas molecules, which you can place in any way, depending if you can modulate, if you are a good synthetic chemist, you can modulate, you can modify your gas molecule with different attachments or functional group so that your molecule goes and sit inside the cavity if the size and other parameters are appropriate. So you will have a partial or full encapsulation in the cavity, or it can sit at the top, can cover at the portal end, which will not go inside. That the activity will be the information or the photophysical property or any other property. I listed this property, it will be totally different if the gas molecule attached at this peripheral side, because it has to be a negatively charged so that it attacks at the positively charged the peripheral area. So you can have several activities in photophysical properties, excited state, its lifetime, all those properties can be tuned. Structural features, you can get different morphological patterns when you have a complexation with the different host molecules. You can have stimuli responsive properties for on-off sensors, various sensing molecules like this. I will show some of these things. This assembly formation, it changes redox properties largely because your electronic properties of the gas molecule is totally changed in presence of the host molecule. So the redox behavior is changed. The solubility changes drastically. A insoluble compound can be made soluble by incorporating into the host molecules, which is even now used for drug delivery, like cyclodextrin is very well used in drug delivery applications. And another important is proteolytic equilibrium. Many of the dyes and drug molecules which are active, they work at a certain pH condition because the protonated form may be active. Sometimes the neutral form may be active. So because of this, our physiological pH 7.4, even though the dye is more reactive, because of the equilibrium, you will not be able to work in the pH condition. So using this encapsulation using a host molecule, I have put it this general host molecule, you can tune the proteolytic equilibrium to a higher or lower side. So at that particular pH, you get 100% of the required form. So these are some of the activities we do in this kind of area. So I don't know how much time I will have. So I will try to touch at least three of these topics, if possible, move further. And this is a little earlier paper in 2010. So if we have a dye which is totally non-fluorescent, that is thioflavin T, which has got fast torsional relaxation of the order of femtosecond excited state lifetime, and you have a cucurbitural cavity CB7, which is benign or neutral or does not have much photophysical parameters. But what we did by all these photophysical studies, all other parameters, we stabilized this kind of structure, that is a 1:2. That means two host molecule holding this dye, and this dye eventually what happened? It uptakes a lot of metal ions. It uptakes a lot of metal ions and become highly fluorescent. So from a non-fluorescent molecules, we have made a fluorescent molecule which is which can sense a particular metal ion and become highly fluorescent. And soon, so it has got application from protected drug delivery, fluorescent on-off sensor, uptake of metabolite, and this is a very interesting application people suggested. That is, it can act as a nanoreactor because at molecular level you are concentrating the metal ions, or otherwise you have 1:1 interaction of metal ions with any dry molecule, and where metal enzyme kind of reactions are there, you can tune this metal ion. If you can go to a transition metal ions at the reaction center, you are having a high concentration of metal ion. So these kind of applications are coming up by using this simple host gas kind of interactions. And another application is for the separation of specific metal ions. So as I mentioned, when the portal region is negatively charged, it attracts cationic metal ions. Whether the peripheral side, which is cationic center, whether it can stabilize any metal ions. So this work we did with Professor Madhav Malya, who will be also presenting later in this symposium. So the idea is there is a need of technetium 99M technetium, which is a radio tracer. And technetium does not exist in nature. It is a daughter product of molybdenum. So once you activate molybdenum by neutron irradiation, the 99 molybdenum undergoes beta decay to give this 99M technetium, which has got a half-life of only 6 hours. So this technetium decays, the T half is 6 hours. It decays by emitting 141 kV gamma. And if you, this is used in medical diagnostic for imaging. So this gamma can be used for imaging. So it gets out the body very quickly. So the problem is also you have these parent molecules, which is activated molybdenum, which has got around 66 hours of half-life. So your interest is to separate technetium 99 exclusively from this parent molybdenum, which both exist in solution. Because you have at pH 4 to 6, if you have a molybdenum, the activated molybdenum, it will have in the heptamolybdate form like this, MO7 or 24, with 6 negative charges. This is where our interest came in, and we contacted Dr. Madhav Malya for his support. And this molybdenum goes on producing this technetium, that is TCO for single minus. So we thought of taking advantage of this difference for a separation challenge, and so by supramolecular approach. So what we did, we have a CB7 kind of host molecule, and this suppose it is activated molybdenum at pH 6, which is a heptamolybdate. So when we mixed this and this, we got a white precipitate, clear white precipitate. It suddenly very quickly settled. So we analyzed this part, and we found that it is nothing but the complex of CB7, which is complexing with the heptamolybdate. Okay, if you want to separation, we don't know whether it is useful for separation. So what we did, we analyzed the supernatant liquidant, and we saw that there is pure TCO4 minus. It's very simple. And what you do, you just keep. So this established like this. We did all these characterization techniques to establish that it precipitates like this, and TCO4 minus does not interact with this one. And all what is required, you can just keep this precipitate separated and keep it for another 1 day. The technetium will generate in situ. Then again you wash, the TCO4 will come in the work. So this cycle goes on. That is what medical field, this technetium generator works with alumina right now. So this Madhav has done all this characteristic for radiochemical purity, radionuclide purity, elution efficiency, all those things. So this kind of approach. So what we are trying now is to do more on this to make it more usable, means more medically useful for different host molecules. This is with CB7 we have done. We have CB5, CB6, and CB10, all those hierarchical molecules we have, so that we are looking for a hero. So another part is on perilene diamide dyes. Malay, just tell me few minutes, maybe. Yeah. So this is current voltage. It's a simple dye is a very well used chromophore, that is perilene diamide chromophore, very stable. And depending upon the substitution, this is phenylalanine tyrosine, or any substitution, the property changes a lot. A lot of people use this the core molecule for different derivatization. So but if you look at the photophysical, just fluorescence spectrum, if you take the dye, you can see the black color or reddish brown. There is no fluorescence from this dye, just because it gets aggregated in solution. Okay, so photophysical properties are, people just leave like this. So we just add a classical beta cyclodust in few micromolar. You can see solution becomes highly fluorescent. Now, we characterized all the properties, the absorption, fluorescence, all circular dichroism, because these are chiral molecules. You can see what we found out, that the beta cyclodextrin stabilizes the dye in their monomeric form because it gets encapsulated with the N group, so that aggregation properties are lost. So if so, what happens? What is the advantage of that other than getting a highly fluorescent molecule? So when we use the morphology of this molecule, we write the molecule and look at SM, AFM and F, all the pictures. If you look at the dye alone, this here, you can see only lumps in the film what you are made. But if you have the complex dye with the beta cyclodextrin complex, you can see there is a particular pattern. And you can see the fluorescence microbe, this pattern. It is not only the cyclodextrin getting patternized, it contains the dye itself. You can see very bright dye. So then we moved further one step ahead, whether you can still use this kind of sheet-like morphology for any other application. We contacted our Dr. Padma Madam, who is doing theoretical physics at TPD. This kind of activities for IV scan. So she helped us in doing the IV scan. So she made this kind of arrangement where two gold electrodes are there. So you put your complex in between, that is maybe around 25 micron size, and characterize the current voltage graph. So what this shows, it after a certain voltage, it cut off. That is called negative differential resistance. So NDR behavior is useful for semiconductor like activities or on-off switch or circuit breaker systems. So these are the organic electronics molecules which are used for this kind of activities. So clearly we got NDR region. That means after a certain voltage, it drops down. So it is like a circuit breaker. It can act if you can tune in this region. So we have completed this sequence and all this. So one not naturally people ask, since it is organic molecule, whether it is stable. So we did the same scan with several scans, forward and backward scan. We could reproduce, and even after 6 months, the same thing which we just put in the stored in the desiccator, we could reproduce the same data after 6 months. So that was the beauty of this complex. Even though it is non-covalent complex, all this stability and other things are highly reproduced. How much time I have? 2 minutes. So this is, maybe I can just flash it, similar molecule, that is the naphthalene diamide molecules. So this here we have cucurbituryl, and again so there's a difference of 2 macrocycles, that is CB7 and CB8, only one size, only the difference. You can see a lot of photophysical changes, the fluorescence spectrum like this and the stoichiometry like this, and the same pattern. If you look at CB8, you have a huge emission coming, which is called a X-hammer emission. Again, you see the pattern here, pattern is different. Here it is the rice-shaped pattern is developing, and here it is a lump, means if there is no host molecule. So we did further experiment, and when you expose to radiation, you can see the solution becomes colored. It generates the radicals. It generates transient radicals which used, and we characterize by all several methods, which I will not go to the details, lifetime, everything we characterize. And this transient radical we are used for in situ production of gold nanoparticles. Means we are created a complex, and that complex gives the transient radical, and the transient radical reduces the metal gold nanoparticle into gold nanoparticle. But if you don't use this macrocycle, there is no nanoparticle, there is no color, nothing. So this one short time span of the transient radical can be used for a gate, a time gate for doing any chemical reaction, or a reaction where you need a short time, a pulse of radical, reducing radical for your reaction. And this maybe I'll just show the catalytic activity what you recently did. And same thing for hydrogen release storage. The aminoboron is well one. I'll just flash it. You can stabilize the product, the ammonia, and this one, the hydrogen get released. using that, we got a huge enhancement in the hydrogen release properties, and we characterized all those things recently, and we are working on this with further hydrogen storage material. So these simple activities of introducing non-covalent interactions are very useful. So this biological part I will not go, because we are used for inhibition of fibrils and disintegration of fibrils, same thing. The macrocyclic concept just to inhibit the natural folding of proteins and other things by using macrocyclic encapsulation. So also this proteolytic equilibrium, I saw that huge change in the proteolytic equilibrium when introduced, which will enhance the antibacterial properties of the drugs. So these are some of the things I just flash now. So I'll stop here because Malay Sarkar is on the stage. And I must thank all these people, Dr. Jyotirmay Mohanty, who is the pillar and the strength behind all these studies. And these are the people who has contributed here and there and all that for the papers. And all my co-workers who are not listed here, colleagues and mentors, and my senior colleagues sitting here. And at the last, not the least, my research center, Baba Atomic Research Center, for favoring me for all these activities. And thank you all for your patience here. Thank you.
Now the floor is open for discussion.
Hi, Professor Basi Gupta. It's an
Yeah,
exciting talk. So I have just one question. So you have shown that this perilin with beta cyclodextrin, and it shows some unusual morphology.
Yeah. That
so, its length is around 200 micrometers.
Micron size.
So what is the actual structure? Because I know
we did not go into those details. We did not go to those details, but we went to the other application parameters. This structure is a micron structure. It is maybe the aggregation. It is getting patternized due to the end complexation. So otherwise, it aggregates as a lump. So we don't know how we can project it in a fashion or something that means deaggregate or we cannot do that.
Okay.
We are not into the details. Maybe theoretically, if something is possible, we can do that.
Dr. Ghosh, you can give it to.
Myself, Juhur Mondal. I'm from the same division as the speaker, PRC, Radiation and Photochemistry Division. So my question is regarding that non-covalent interactions, which is basically various kinds of maybe iron dipole interaction, hydrogen bond. So did you go into the details of those interactions, for example, when you are changing from metal ion to some solute organic molecules? So whether
we normally go for a more or less stronger interaction, because when we need a stimuli responsive interaction, you have already an interaction. So we look for an interaction which can eject that interaction, means a competitive binder kind of interaction.
Yeah, but the specifics
but the strength,
of those interactions.
No, specifically means
highly heterogeneous. For example, you have the possibility of complexation.
Because it is not only one kind of interaction. It is interaction from, if it is in the cavity, it has got interaction from the portal side. It has got interaction from the hydrophobic side. So a lot of interaction.
Yeah. Do you think that there is a possibility, and we can go deeper into that? And
yes. There are theoretical people are doing, because this kind of cavities are used for gas sensors. Means certain gases are written, and use a competitive binder so that it comes out. Several applications have come.
Thank you.
Okay, maybe
Yes,
last question.
Professor
Ghosh.
In Boden.
Yeah.
So typically, most of the people, they use the metal catalyst.
Yeah, there is the advantage. There is no metal catalyst here. We wanted to avoid metal catalyst.
How it works, I mean,
yeah, that is the reaction is aminoborane dissociating into 3 hydrogen and NH4 plus. And this cucurbituarial cavity can hold the NH4 plus into it. So that gives a more. So we have calculated the activation energy also. It gets lowered very largely. So we are working with other molecules. So this is metal-free catalysis we have done. We have very simple setup we have done it.
It's a very nice one. I mean,
Yeah,
you can quantify the evolution of the hydrogen.
Yeah, we are doing with nanoparticle and those kind of things are going on now. Thank you.
Okay, so let's stop here. If you have any question, you can still ask Professor Basic.
Yeah, I'm here.
Yeah, during lunch time. So let's thank Professor Basic for a wonderful lecture.
Yeah.
It's my pleasure to actually present this moment on behalf of organizing committee to Professor Basic. Okay, so the next lecture will be given by Professor Dulal Senapati from SINP, Kolkata. So Professor Senapati did his master's from Jadavpur University, Calcutta in 1998. Then he did his PhD in 2004 from IIT Bangalore. After that, in 2005, he moved to Georgia Institute of Technology, USA as a postdoctoral fellow and worked there till 2008. Between 2008 and 2012, he worked as a visiting scientist in MRL UCSB, Santa Barbara, and as research associate in Jackson State University, USA. In 2013, he joined SINP as associate professor E. Professor Senapati works in a diverse area of material chemistry. His current research interests include anisotropic nanomaterial assembly, force field microscopy, alcohol and air fuel cell, nanoantibiotics, regulation of cellular differentiation programs. With this, I invite Professor Senapati to share his thoughts on the innovative ideas in developing nanoscale materials for energy, sensing, and therapeutics. Professor Senapati.
Good afternoon, everyone. Thanks to Dr. Sarkar for the nice introduction. And it's my pleasure to be here in Nicer. So this is my first time. I'm coming from a very crowded place to a nice place here. I can breathe nicely here. So uh, just my previous speaker, so he just introduced the subject of nanomaterials. Maybe I'll go into little bit details, and hopefully by 20 minutes or 25 minutes, I'll be able to finish my lecture. So the okay. So okay, so the title of my talk is like innovative ideas in developing nanoscale materials for energy sensing and therapeutics. Okay, so yeah, I work in a diverse field. So this is, but whatever I work, so this starts from actually the synthesizing those nanomaterials. So but we make materials with a target, okay, not like we just mix the A and B and get something C. So those are like for optical sensing, catalytic sensing, energy production, solar energy, and therapeutics. So each one actually is based on some essential criteria. Okay, so like for optical sensing, definitely it should have a high extinction coefficient, plasmon tunability, and electromagnetic field enhancement. Similarly, like catalytic sensing, it should be enriched with defect sites, low overpotential, high tolerance, greater stability. And like that, like for therapeutics, so materials should be smaller enough to go inside the cell, okay, or to remove out from the cell. Okay, there should be sharper in shape for photothermal activity. Okay, they are suitable surface for selective modification, efficient electron phonon coupling, or they should be non-toxic in nature. And of course, for medicinal applications, they have to be cost effective. So let me just quickly, I should go like, what are the general synthesis we use, which are not very exotic synthetic methods. So those I categorize into two types. Like one is top-down approach, which the physicists generally adopt this process, and the chemist we take this step, which is we call as bottom up. Okay, so the physicist basically starts from actually like a bulk material, slices down and come into even to the atomic levels. Okay, but where the chemist generally starts from atoms, combine them, make molecules, supramolecules, or even the bigger particles, okay, structural materials. So this we generally in the chemistry we adopt like how we make the nanomaterials. So those are either by single step synthesis or multi-step synthesis. In single step synthesis, we put like metal precursor, surfactant, stabilizing agent, solvent, reducing agent all together, and then heat it, or by photochemically we can make them. But in multi-step synthesis, we first make seeds. We use those seeds to develop much bigger particle with different size and shapes. So that could be like nano templating. We make a nano materials and use that as template to make a much bigger materials. Or also we can make like multi-step layering assemblies, like layer after layer after layer, we can make them. Okay. So those are very easily we can in general synthesis, how we can make them. We just simply vary their molar ratios between the metal precursor and the surfactant. And as we increase the molar ratio, gradually we go from 1:10 to 1:0.3. So the particle sizes are actually bigger and bigger and bigger. Okay. Similarly, like we can make in a seeding method, first we make a small materials and then we use that as seed and then make the next step. Again that as seed and make the next step. So by that way also we can tune. As you can see, like they not only their sizes, but at the same times their plasmon also moves from like 500 to 800 nanometer very easily. Okay. We can use some physical conditions like viscosity. So the viscosity, if we keep on increase the viscosity, the diffusion of the metal ions or the reduced metals, so they also gets hindered. And then in a particular fashion, they arrange. So by that way, just simply by changing the viscosity or increasing the viscosity, you see how it's becoming like an anisotropic materials. Okay, it's like how it happens. You can see like gold reacts with CTAB, it's an organic molecule, cetyl trimethyl ammonium bromide, and then with silver nitrate when it reacts, so it's basically silver chloride it generates. So that silver chloride, which is insoluble, it's block the high energy facets and the low energy facets grows. It's like Arunachal Pradesh girls, they put rings in the neck. So the neck cannot grow in this side way. So it has only freedom to grow in the front way. So that's why the necks are much longer. And then that's what they are more beautiful who has much longer neck. Okay, so it's the same thing in the science also we can adopt. Okay. And this blocking, specific blocking, we can actually achieve if we adopt like a nano wire formation. So like this is a pure metallic nanowires, like silver nanowires, we can make even up to bigger, like 60 micron. Okay, so 50 nanometer diameter, but 60 micron long. So these are like almost like another version of like carbon nanotubes. So you can see like at the first we make them those seeds. And so once we make the seed, then those seeds actually combined, okay, much bigger nucleation center we make. And then those nucleation center and those seeds with the reduced atom, they queue up in a fashion of like a long thread with knots. And that's the way these wires actually grown. Okay, by just simply varying. So if you see the previous slide, so here we don't use silver nitrate or anything. Instead, actually, we use only sodium chloride. The sodium chloride reacts with silver nitrate and gives the silver chloride. So that silver chloride finally it's block the facets and give the much longer structure. You can see how just simply by varying the sodium chloride concentration, we can vary their shapes from 500 nanometer to 30 micron. Okay, with a nice selectivity. So not only that, actually, like simply by varying the viscosity of the surfactant, we can actually replicate like bud to bloom, like how a flower actually starts from bud and then gradually it's bloom to the flower and even to the much developed flowers. Okay, so like each step actually we can replicate, and those are so nice actually. Those are all are single size and single shape. And so here the difference is like these nanomaterials actually we use as the template, and based on these nanomaterials we grow these overgrown shapes. So those are much bigger shapes. So those are in the micron level, and also like these nano plates we use as the template to grow the much bigger nano plates. Not only that, by exploring the micelles, if we use hydroquinone, so hydroquinone, the pH in the acidic range. So if we increase the concentration of hydroquinone, so hydroquinone, as we increase the concentration, the pH is actually gradually reducing. Once it's reduced, so that reduced pH change the shape of these micelles. And inside those nanoparticles, so their shapes also changes. So by that also we can change their shape. So here we successfully, we can actually develop like the flower shape nanomaterials. So by using different parameters, okay, controlling different physical conditions, chemical conditions. So in SINP, we can make all those shapes. So I can say those things as the nano collections of my lab. Okay, so like we can make like whatever geometry you can think, we can make them, we can develop them, and also like all are isolated and easily characterized. Okay, and what we do, like once we develop, so we use for different experiments, like we can do all sort of photophysics, we can go for sensing catalysis, we can go for therapeutics, and then apply in different fields. But in this lecture, I will be only talking about few exotic synthetic methodology. So first one is actually starts with, like I'll show only three different types of nanomaterial synthesis. So one is like resultant inward imbalance seeding force. So this one we are actually exploring currently. Anuradha and Monorama, these two actually exploring this subject a little more. So it's how it works. It's basically like the seed we make. That seed is suitable for nanocubes, and the growth method is also like the similar growth method. Like we take a surfactant CTAB, we use gold chloride, silver nitrate to generate in situ silver chloride, and then we use HCl that also makes to help the silver chloride, and then we reduce it by ascorbic acid, and then once we add the seed, so then it makes different structure. So the difference is here the amount of seed we use actually is much less. Okay, you can see like amount of seed is less than 1 microliter. Okay, and maximum we can go for like 10 microliter. Okay, and this gives like the structures, like when we use like 10 microliter seed, it becomes like a concave cubes. When we use 1 microliter, these are like a star, and when it's less than 1 microliter, so the structures are broken. Okay, so how it works? This slide actually. Okay, so the idea is here. So you see, like when there are huge number of seeds, so the distance between seeds are much less. Okay, now these seeds are suitable to orient the gold atoms in a cubical fashion. Okay, now when these seeds are very close to each other, so these seeds actually nearby gold atoms, they internally they attract. Okay, so we call as an internal force, and but it has also effect to this nearby seed surrounded gold atom, so that is external. Okay, when these two are in balance, okay, because they are close to each other, so then actually it makes, so that means the internal force and the outer force, so these two are same, so then they make actually the cubical pattern. Now once actually we increase the gap between these seeds, so then what will happen? Okay, so here actually the gap is little bit larger. Okay, and this circle actually shows this seeding force. Okay, so since they are actually apart from each other, so the inward force is more compared to the outward force. So that's why the plane actually curved. Okay, and once we actually increase further the distance between the seeds, so you will see only the inward force is effective, but the outward force is not effective. And we can okay, so these slides are little, so you see the gap is much bigger. So only the inward force is effective, which makes them a curved structure and gives the structure as star patterns. Okay. So how it works actually, so geometrically we can understand like how actually, so as the angle reduce, so we can get actually much sharper tips. Okay. So by the same way, actually, we can actually, we are making actually different shapes also. So those are with those sharper tips. Those are starts from a spherical particle and then these tips are actually growing. So those actually shows actually highly catalytic activity, and we use for them actually for the sensing of analytes like serotonin and kynurenine. So those are like neuroanalytes we can easily detect. I will not be discussing about this in details. Okay. So the next synthetic method actually what we adopt actually. So this one actually the multi-layer nanomaterials. So what we make? We make gold inside silver layer, and that we use as the seed to make actually gold layer outside this, and then silver layer outside this, and then finally gold layer out of this. Okay. So how we make? We make like first we make actually these two are small two gold seed and surrounded by a silver. So we call this as the nanoparticle 1. And then we use this as the seed to grow a gold outside of this, which we call as the nanoparticle 2. Okay. And then we use this as the seed to grow the silver layer outside of this. Now here the thing is like the silver, generally we cannot actually reduce it by ascorbic acid. So what we use actually to increase actually or reduce the activation energy, we use the heating method. Okay. So it's a nice smooth surface actually comes of silver. Again, we use this as the seed to grow outer layer of gold. Okay. So by that way, actually, we can make several structures of these. As you can see, those structures, like for these are NP2 and NP4, which has actually gold outside. As you know from the redox potential, once you put the gold out of the silver layer, so they actually start leaching. So the diameter from the elemental mapping, it shows actually they are actually mixed metal material. But in case of silver outer layer, so they have a clearly defined outer silver layer and inner gold layer. So these are the elemental mapping of the silver outer layer, and this is for the inner gold. So the gold is much smaller, but silver is a much bigger. So they also show actually highly catalytic activity, and not only that, by using same thing seeding like gold and then gold layering layer after layer, we can make also this type of materials, and silver also we can make them. So they also show actually the in fuel cell applications. I will not be speaking on that. So the specific activity of this NP3 especially, which has actually the outer surface layer, has the much bigger activity, and that's because of its oxophilicity effect of silver compared to gold. And the third thing, so I would like actually to tell like this. I worked on also the surface enhanced Raman spectroscopy. So the surface enhanced Raman spectroscopy, we saw the like once in any sort of dye, it's attached onto the surface of the nanoparticle. It's generally it gets chemical enhancement or its electromagnetic enhancement. So these two enhancement actually stems from the enhanced local field due to the electromagnetic field, and also the enhanced field offered by the plasmonic material. So these two plasmonics, so that's actually offered the surface factor of G. So if we take actually the intensity, which is actually G to the power 4, so that counts for like 10 to the power 6 enhancement. But most of the times you will see ACRS enhancement, we could get actually 10 to the power 10 to 10 to the power 11 enhancement. So that one with this normal model, actually we cannot explain. So how we go to these things to explain? So explain is like you think about a dye molecule sitting between two nanoparticles, and then we are exciting by an electromagnetic radiation, and this electric field is towards this arrow. So then what will do? So it will, this growing front of the electromagnetic field will induce a negative charge here. That's because of the electric field, which will generate a opposite charge here. So that again induce a negative charge here and then positive charge here. So now if a die is sitting here, so this will feel like a sitting in between a capacitor. Okay. And that capacitor field, so capacitive field, it depends on 1 by d to the power 8. Okay. And due to this small distance, which is less than 1 nanometer, this capacitive field is huge. But if we allow this electric field perpendicular, then actually this capacitive field doesn't occur. But inspired by this, actually we made several materials now. So where the nanoparticles are absorbed, this thiolated compounds, which has one end is negatively charged or positively charged, whatever. But these are so nicely covered, they don't make even aggregations. So these materials are easy for the preservation, for delivery and other things. But you think about like when we apply the electromagnetic field like these directions or even this direction, so it gives a capacitor here. So like positive and negative. Similarly, for the negatively charged ligands, this side it will give a positive and negative. So this capacitor actually enhances the field so high that we can actually reach up to an electromagnetic enhancement of like 10 to the power 11 to 10 to the power 12. So in spite of that, like we make all these materials where these tips are so close to each other, it's like about like 1 to 2 nanometers. And if a die is sitting on this between these two tips, so they get enhancement due to this the capacitive field. Okay, and also like we have examined like those thiolated the aromatic compounds like thiobenzenes, okay, like 4 martepto, the benzoic acid, okay, or 4 amino benzoic acids. So those molecules specially actually gives the very big enhancement and due to that capacitive force. Okay, we also make few materials like several number of gold atoms encased into a single cell, and outside is actually negatively charged. And then if we put a positively charged dye like rhodamine 6G in between these two, so they get actually the capacitive field effect and gives the huge Raman enhancement. So yeah, so that's what like I think I have finished it by 20 minutes. So those are the few things actually in the synthesis, but beyond that, actually we work lot more on fuel cells, high energy, high resolution microscopy, and development and of nanomaterials for the fabrications and other things. But I have not touched with this. And this is our SINP, as mentioned by Dr. Saranappa at the beginning. Like we are actually 3 there in the chemical sciences. So my field actually spans from like spectroscopy, dynamics, and nanomaterials applications both in energy as well as in the medicine. And my colleague Padmaja Prasad Mishra, so who works on single molecule spectroscopy, and Professor Muntu Hajra, who works in the environment and molecular dynamics. So and so most of these works are done by these students. I have a very small group of 4 students, so that's what our limitations. I cannot take more than 4. And also I'm thankful to DAE, DRDO, and SINP for all sort of funding and also few collaborations with Russia and as well as in USA. And thank you very much for your kind attention.
Thank you, Professor Senapati, for finishing on time. Now the floor is open for discussion.
Hello, nice talk. I have a question. I'm Satpati from BRC. In your nanoparticle where you charge positive one side and
Yes.
negative one side. So, I don't know what application they are looking at, but it's conducting nanoparticle current.
You are talking about this?
Yeah. So what I wonder is they will self-discharge.
They will?
They will self-discharge. They are conducting nanoparticle.
Yeah, that in that application you can do, of course, but in our case, actually, we look for like a photochemical activities. Okay, so we look for the application in the spectroscopy mainly in surface and Raman spectroscopy, so that we can apply them for the sensing.
And I have one more point. You
Yes.
have chronoamps for sensing, correct? Chronoamps. You have.
Chronoamperometry, yes.
So your current drops down very sharply the moment you add.
Yes, so
it.
that's
Is it
a
a capacitive loss or is something else going on there?
no. You see, like DPV, differential pulse voltammetry, chronoamperometry, and impedance spectrometry. So these three techniques generally we use. Okay, now DPV is actually is much more sensitive, but that one actually for the equilibrium systems. But when actually the near the electrode, the system is not equilibrium. Keep on there is a fall in the concentration. It's better actually to go for the chronoamperometry.
No, that's fine. But
But
the current
it's
drops down very fast after you add.
yes, after that, but again it will pick up.
But you definitely start the solution of that.
No, we don't start it.
Then it will drop down. That's what.
Yeah, but the drop down, but immediately actually it comes back.
Question is related with Dr. Saputi's question only. So this is you are using this electric field is the electric field of the light you are talking, right?
Yes. This is electromagnetic field.
Electromagnetic field.
Yes.
That means the oscillating electric field.
Exactly. So that field
leads
is
to this induced dipole.
Exactly. It's an induced dipole.
But one thing I cannot understand is when you are putting it horizontal field, for example,
okay,
then as there is a oscillation of charge in the horizontal and your probe molecule or whatever other chromophore is there inside, it is coming under a capacitor kind of thing. And when you are saying it is vertically polarized, so naturally below that, the top figure actually, below that some particles are there, quantum dots are there. So there also such kind of capacitance will be.
Yeah, then you see, that's what I told. Like, suppose this is a 20 nanometer particle. So the induced charge difference between this and this is a gap of 20 nanometers. So their capacitive field is 0. Okay, but when actually, but this gap, it's about like 1 nanometers. So that's why the capacitive field is huge, because it inversely depends on d to the power 8. Okay, so it depends on how close these particles. You see, the hotspot only you can make when the particles are about to touch, but it's not touching.
Yeah.
So that's why.
But how is it dependent on is it the kind of polarization of the light you are talking here?
Yes, this is a electric field. Okay, so this electric field will induce a negative charge here and positive charge here. But as it's oscillating, it might be changed to again positive to negative.
What my concern is, regardless of its vertical and horizontal polarization, in both cases we will get the enhancement.
No.
If I have understood correctly.
No. That's because here you see I'm talking about the layer, 2 layers, positive layer and negative layer, and the gap is about like 1 nanometers. But here actually the gap is about like 20 nanometers. So that's why it cannot actually induce that capacity.
Okay, we'll discuss more on that.
Yes, sure. Yes.
Hello, I am Madhav from BARC. It's not a hard science question. It's more related to the different size nanoparticles that you have made.
Sure.
So you are looking at energy sensing and therapeutics, right?
Exactly.
Now, do you have any evidence that these properties are related to the size and shape of these nanoparticles?
Oh, yes. So that's what actually we are looking for. Okay. So all depends on, you see, like therapeutics. First of all, therapeutics, to do a good therapeutics, you need a much smaller particle and much sharper shapes, like a tip which has a end diameter is like 1 nanometer or something. I have shown few because I have gone so fast actually. So you see, if the tip size is about 1 nanometer, so that due to this electron phonon coupling, the amount of energy it deposits on the tip of this shape, which can generate about like 5,000 Kelvin. So that actually is a huge actually for the therapeutics applications. So that's why actually constantly we are making those sharper shape molecules.
Okay, so Dulal, I have one question. Basically, you have made some excellent anisotropic noble metal particles, and you showed that these hotspots can be used as a search. So first question is that basically this among those anisotropic particles, which one you found the best?
So
or is there any dependence?
Let me again quickly go back, okay? The problem. Okay, so, you see, like for anything, for binding on the surface, okay, if your surfactant concentration on the surface is much less, so then Raman activity actually goes very high, okay? So, I don't know, like few shapes we make actually it's without surfactant, okay? Very small molecules like ascorbic acid we make. So those molecules actually gives a huge Raman, okay? So generally like we try to make structures doesn't use much surfactants. Like CTAB is a bad surfactant, good surfactant for stabilization, but bad surfactant for ACRS because it's makes like a plastic coating outside it. So
thank you. I got your point. So, yeah, so maybe you can stop here because,
The last.
okay, then you can discuss.
okay,
Okay, please.
Very nice talk. I'm Sriramurthy from IGCAR Kalpakam.
Mhm.
So in continuation with Professor Mandal's question,
Mhm.
actually the particles are homogeneously distributed all around.
Yes.
So in that case, it is the interparticle polarization that is you are talking about, that is the capacitance behavior, but not the within the particle because it's a conducting species.
No,
So
you see,
in that case,
for
how it distinguishes?
my case, actually, the frame of reference is actually 2 nanoparticles and the molecule in between these. So that's my frame of reference. Okay, but yes, that dye might be isotropically distributed. Okay, but
Is this
but
horizontal and vertical polarization?
yes, that's because like when we use dye actually in very low concentration, like 10 to the power minus 9 molar, so then it's no more isotropic. Okay, because your nanoparticle concentration is much higher compared to your dye molecule. So it might be isotropic, but it's localized still.
Okay, so let's stop here and then you can, Professor Senapati is here, so you can discuss whatever question you have. So let's thank Professor Senapati for a great lecture.
Thank you, everyone.
And it's my, on behalf of organizing committee, I'll be happy to present a moment. Okay, now we move on to the final lecture, which will be given by, for this session, which will be given by Professor CVS Brahmananda Rao from IGCAR Kalpakkam. So Professor Rao did his graduation in chemistry from Delhi University and post-graduation in chemistry from University of Hyderabad. After that, he joined Park Training School in 1994. After training, he joined radiochemistry laboratory in IGCAR in 1995. He did his PhD from Madras University in the field of organic ligand synthesis and its application for the recovery of actinides. Currently, he is heading the solution chemistry and mass spectrometric studies section in 12 chemistry division at IGCAR. He is also the Dean of Chemical Sciences at IGCAR in HBNI Mumbai. He has over 100 publications in various national and international journals, seminar and symposia. His field of interest includes synthetic organic chemistry, development of alternate extractants for actinide recovery, computational chemistry, and high temperature mass spectrometry. With this, I invite Professor Rao to deliver his talk entitled as Mass Spectrometry, an Innovative Tool for Nuclear Industry. Professor Rao, please.
Yeah, good afternoon to everybody. Thank you, Dr. Sarkar, for the introduction. I come from IGCAR, for the audience who are not sure about the location, because I know a lot of students are there from NICER. This is 70 kilometers from Chennai, which is the place or which is the department mandate is to develop fast reactor program. And there we have a different programs, physics, chemistry, not on life sciences, but on engineering sciences. So there we have at least 25 faculty members who are basically the chemists who are working, who come under the HBNI. And we have around 15 students. Right now the students are less because during the COVID period, we didn't take any students. So that's the thing. But what I will do in the next half an hour is tell about some of the technique, which is very important. Most of you may be knowing about it, but let me be specific that this tool is very important for our department, and a lot of R&D can be done in that field. And secondly, the general areas of what we work at IGCAR, particularly the students, I will dwell on the last 10 minutes. So I will take around 30 minutes. So let us start. Mass spectrometry, inevitable tool. Why is it inevitable tool? I think most of our department people know it, but for the people who are not who are not working in the field, it's a very important tool. Very qualitative and quantitative analysis can be done to a femtoscale. Here, when I say spectrometry, I am not getting into the areas of organic spectroscopy or Dr. Dosh, who is working on inorganic clusters. For them, it's very important to go to find out the base peak, the mass peak, which is because once you create a molecule, you have to identify it. Organic chemist gets into IR, NMR, and mass spec is one tool which is important to get the structure ultimately. Same thing for the inorganic chemist. For our department, the more important is the isotopes. It's not the molecules we are interested in, it's the atoms we're interested in. That's what I will dwell in next few slides. Its applications are many areas. When you say mass spectrometry, general techniques, but it has applications in geology, biosciences, material science. When I say mass spectrometry, it covers the molecules and the atoms. So I'm talking about the molecules. Of course, for organic chemists, is an inevitable tool. For a geologist, it's a very important tool because they try to do something called dating of the rocks. For them, the ratio of potassium, lead, they are very important. So there is the isotope which is important. It's not the molecules. That's what I want to stress. So very important applications, forensic sciences. I'll not get into all of them. Archaeology and nuclear industry. That's what I'm going to dwell. What is its importance? Of course, you can see based on the number of Nobel Prizes won in the last 100 years. What does it measure? It measures the mass better than any other technique. The best method to do that gives information about the structure and the isotopes. Structures will talk about the molecules, isotopes will talk about the atoms. Areas of things, now we can find out the molecular structures of proteins by using mass spectrometer. That has gone from atom to big molecule level. So the last 100 years, almost it was discovered, the mass spectrometer, and I'll show you about that. In the last 100 years, one area which has developed leaps and bounds is mass spectrometry. Its applications in the biology are immense. We'll see those areas if possible. So started all with this gentleman, E/M ratio of which we have studied in our class 10th or 12th. So where he determined the E/M ratio of an electron, and then this was the basis for the development of mass spectrometry. And in fact, he discovered two of the isotopes of neon way back in 1930. So this was the beginning of the mass spectrometry. His student, John Aston, went on to give the first idea about how exactly the mass spectrometer should be by by passing through a parallel electric and magnetic field. That's the principle on which it works. You have a magnetic field and electrical field, and based on the charge particle, you maneuver them and to get the mass of the material. So he got the Nobel Prize in 1922 for that. As I told you, what you require, the particle has to be charged. So the first thing and first and foremost is your particle should be charged. It can be a molecule, it can be an atom. And then if it's a molecule, you get the possible structures. Of course, you have to use other techniques along with that. And for us, as I told you, it's isotopes. We all know what are isotopes. Isotopes, as the name suggests, is an atom can have different number of, same atom can have same number of protons. An atom has the protons, but they also have the number of the neutrons can be different. So that makes the same position in the periodic table. Therefore, the name has come from there, which was coined by Soddy in the long ago. So what does the mass spectrometer contain? It is true for any mass spectrometer. I'm just giving a very generic structure. You have a sample inlet, you have an ion source. So the moment you have a sample, it has to be converted into ions. Without ions, you can't do anything. So there should be a method to produce ions. Then you have an analyzer. You have to separate those ions based on the mass, and then you detect. That's the simple principle, although it looks very simple. You'll see it's not as by this. Okay, fine. This is how the block diagram looks. So you produce ions by some method. You, for example, there are many methods by which you can produce ions. One of them is by electron beam. You make it charged, pass through the magnetic field. It separates based on the magnetic field, and then you detect by using a detector. So this is how a simple block diagram for any mass spectrometer, irrespective of what you are measuring it. It all started, it was discovered almost in 1920s. The fundamental things are known, but its application, its usage came only after, during the Manhattan period. So Manhattan is the project which was started in 1938. The uranium fission was discovered. The moment it was discovered, they wanted to use it for some application. And the first application was how to stop the World War. And therefore, they were interested to identify whether this uranium can be used for any, in fact, that point of time, it was more of a destructive purpose it was used. So they identified this gentleman, his name is Albert Near. He was given the task by his professor by name John Dunning to identify, is it possible to separate these isotopes? Uranium is an isotope we are talking about. Uranium is the metal which the fission was discovered, and they wanted to separate 235 and 38. So this was so he was given the challenging task of separating them, and till that point of view, after the mass spectrometry was, the principles discovered, nothing much has happened. So he was given the job of separating them by some method, and he used this mass spectrometric method as almost a preparatory tool to separate them, and that was the biggest challenging task, and they could do that. So they went on to separate initially. I will show you what type of machines they used to separate this 235 and 238, and they understood that 235 is the one which is important. So they did something called separations. The mass separation of 3 units, that is 235 and 238, just imagine, is so difficult. But using the same principle of mass spectrometry, they developed something called huge machines. It's called coltrons. The name coltrons have come from, it was developed at California University using the cyclotron philosophy. The name has come from there. So Lawrence had developed cyclotrons, and he was the one who was a machine builder. So he used to build bigger and bigger machines. And the moment they realized that at that point of time, there was desperation to separate it, and that was the only method they could think was by going based on, that means make a huge mass spectrometers, separate as much as possible. Just imagine from microgram level to kilogram level separations they did by this method. So this was one of the pioneering work at those days. Of course, we have better methods now. This was the plant. They had a huge plants located at US at that point of time. The purpose was to separate uranium-235 from the uranium-235 is called the fissile material. Fissile material is a material which can undergo fission by using thermal neutrons. So that was what they were interested in, and this way they developed large quantities. And in fact, the first bomb which was used on Hiroshima was based on this method. So mass spectrometry has its genesis long before what we really understand. What about the present applications? Present applications are in nuclear fuel cycle. For completion, let me tell you, the nuclear reactors which we have in India almost produces 3% of the energy, and most of it comes from nuclear reactors. So there are different types of the material. The fissile material is basically 235 present in natural uranium. India uses PHW reactors, which are basically natural uranium based. So therefore, what is the method? So uranium has to be extracted. It is available in nature. You remove it. You separate the material from the rest of the impurities. Then purify it. Then if you require enrichment, the one separation of 235 from 238 is called enrichment. And that is what you have to develop. Of course, we don't get into that areas. And then you fabricate the fuel, put in the reactor. All these things, this is called the front end of the fuel cycle. Everywhere, most of the time, you have to characterize the uranium because we are interested in one of the isotope of the uranium. I'm not talking about the molecules here, I'm talking about the atoms. So 235 has to be characterized. We require a mass spectrometer. So at every stage, although naturally it is 0.71%, is almost fixed. Once it goes to the reactor, the content is no longer same. Once you take the fuel, put in the reactor, the fuel undergoes something called fission. We call it as a burn-up of the fuel. You take the fuel out, then you have to characterize how much amount of uranium is left over. That's what you do again with mass spectrometer. So mass spectrometer is used throughout the fuel cycle in some form or the other. So therefore, it's a very important tool in that way. So as I told you, in the World War, they developed this as a quick tools for production of 235 in the pure form, which was ultimately used on Hiroshima. What are the other places? One is in the fuel cycle, very important. You have to identify the isotopes. Nuclear material accounting. The most important material in the nuclear reactor is uranium and plutonium. You put uranium, you also produce plutonium. The beauty of this is something like you have a car, You put a fuel, after driving for, let us say, few kilometers, you also produce more petrol. So something like that. You produce more fuel in a reactor. So you have to characterize those isotopes. You get plutonium, which is a man-made element, and that you have to characterize. So therefore, uranium and plutonium has to be accounted at every stage in the nuclear fuel cycle. Again, there we require mass spectrometer. Safeguards. Some of the countries, IAEA says you are not supposed to use, you are not supposed to produce high enriched material because that can have a destructive applications. So safeguards, people, how do you find out? You can find out by using mass spectrometer because that's uranium 235, 238, a clear-cut picture. You can separate very comfortably by different techniques in the mass spectrometer itself. Environmental monitoring, very important. What happens if something goes into environment? What is the distribution? The surface soils have a very complex molecules. How is the chemistry dictated? Again, if you want to find out, people use mass spectrometry. Forensics is another area. I'll not get into that. So what is the requirement? What we have is something called a TIMS thermal ionization mass spectrometer. Very important tool, as I told you, for identifying the. So it does same thing. You have a sampler, a magnetic field. You separate it out. You analyze. You estimate. So for organic chemist, you'll see different methods. Most of you may be familiar. MALDI is very important for big molecules. You use MALDI. For us, we get into thermal ionization. What do you require? What you do is, as the name suggests, you have to heat to high temperatures, take a sample, put on a surface, which itself has a higher melting point. So normally we use tantalum, rhenium, tungsten, platinum as a support. Put the sample, heat it to high temperatures. You will get, because of electron release, they bombard with the sample, you produce ions. Once you produce ions, pass through the magnetic field, it will separate based on the, you have to play with your, what do you call, current and magnetic field. Based on this, we can, of course, this is still the very primitive method. I have told you there are many advanced techniques in this. Then you have a Faraday cup. These things has to be analyzed by using a Faraday cup, which will give the, then that has to be amplified by using a multiplier. So therefore, each mass number, I can, what do you call, I can establish each mass number, and based on the quality, you can, qualitative is very easy. Quantitative is slightly difficult, which we have to do by different methods. This is how a simple technique. We have this instrument. Although this is important, now BRC developing instruments which we can use on our own. So therefore, we don't have to depend on external agencies for this. This is the instrument which is bought from UK. Take the sample, put it on that. Of course, the whole thing, the whole mass spectrometer is on in a vacuum. So you have to maintain 10⁻⁶ torrs of minimum pressure. And then you, although it looks simple to start with, each sample is a challenge in itself because all of them are radioactive. What you are interested in uranium, plutonium, or the fission products. Those things has to be separated, and then you analyze by using mass spectrometer. So going up to ppm level, ppb level is very easy in this area. So what do we estimate? As I told you, accounting is important. Composition, plutonium and uranium, how much is produced, very important. You get, that is signature of a reactor, plutonium from a fast reactor, from a thermal reactor, from a research reactor, each has its own signature. That has to be analyzed, that has to be quantified. It is done by using mass spectrometer. Burn up. Take the sample, put in the reactor. Unlike oil-fed or a coal-fed reactor, we don't burn completely. We burn part of it. So what is left over? Uranium with 0.7%, maybe end up with 0.3%. So, but that 0.3% has to be estimated. That's called depleted uranium. That has to be quantified. So that also we do that. And how much is the burn up? How do you burn? What do you mean by burn up? How much you have burned it? And that is again estimated based on some of the fission products we have. There is something called a marker for a given fission. That markers we measure by using mass spectrometer, and then we estimate how much is the burn up in the reactor. Enrichment, of course, Dr. Ghosh was talking about boron. Boron is very important for us because that's the way you control the control plots. If you want to stop a reactor, you have to use a boron carbide. So you have to estimate. Boron 10 is one of the isotope which has a high absorption cross section. What does that mean? It absorbs a lot of neutrons. So if you want to make a reactor shut down, you have to use boron rods. So you want to estimate, because how much time I can keep this boron in the reactor? Can I keep it forever? No. It has to be taken out. You have to separate it out, estimate how much is the boron. Then we start with 80%, it will deplete over a period of time. So that has to be estimated. So each is a challenging, and boron is a difficult material to handle. That's what I wanted to ask Dr. Ghosh. It's not easy when you have to prepare those compounds, very difficult to manage. But here boron is a very hard material. It's very difficult to handle, to make it dissolve in a solution, put in the sample, that it's a challenge sometimes. So we have developed techniques for that. And that itself is an R&D. So each sample is an R&D for us. We have to how to estimate it properly and get the numbers correctly. So this is how we typically do it. You get a dissolver solution. What is a dissolver solution? Take the fuel, dissolve in nitric acid, that solution called dissolved solution. Then you separate what you want, and from there you estimate each of them. So this is how you do on a routine basis. This is how a typical graphs look. Nature gives a beautiful, what do you call, what the isotopes are available in nature are not available in the nuclear reactor and vice versa, majority of the cases. You take the 118 elements in the periodic table, we have around 250 stable isotopes, and we have 2,500 unstable isotopes. Most of the unstable isotopes you can see here. So it's a beautiful thing. Only thing is sometimes separation is difficult. Characterization is sometimes because the half-lives may be as low as microseconds. You can't estimate those things. So that makes it very challenging. But the one which are long-lived, we can study them, separate them. These are some of the isotopes which are not available. We can see some of the things I shown in cesium here. Similarly, strontium, you can see that there is no match of the mass number. What is available in nature may not be available in the reactor and vice versa. Similarly, neodymium, very important. Using this, I can find out what is the burn up of the fuel in the reactor. Some of these uranium, plutonium, just for completion, to see how it looks. Analytical do, this is the support we do. We estimate different samples which comes from throughout the department. And although it looks a routine tool, but it is a very classical tool to do R&D in itself, because each sample is a challenge in itself. Let me come to the second part. This is about, can I use mass spectrometry as an R&D tool? It looks like a routine tool. There is something called, this is a tool which is called Knudsen fusion mass spectrometer. It's a, you understand what is the fusion. You take a material in a closed container with an orifice on the top and heat it. You get the vapor of that material. You have a very small orifice. The calculations are there, how much should be done so that the equilibrium is maintained. And if you remove those vapors and scoop it and pass into a mass spectrometer, you understand the behavior of the material. Now, why should I know that? Any material at high temperature, behavior is not going to be the same or similar. Let us say I want to do a material property at 2000 degrees Celsius. How do you estimate that? There are not many techniques by which I can identify that. What are the species which are coming at, let us say, 2000 degrees Celsius or 1500 degrees Celsius? This is a great technique. So what you do is take the sample. I'll not get into that. What I will, yeah. So what I do is take the sample, put in a cell, it's called a Knudsen cell, and heat it to high temperature. And then through that orifice, you get some vapors of that equilibrium, whatever the material you take, and you get an equilibrium. I'll show some of the examples. And that you take it out, pass to the mass spectrometer. Mass spectrometer will give you the base peak. You have to get the quantitative information. So based on that means what you measure, basically based on the amount you can measure the pressures, partial pressures. Using those partial pressures, I can get delta H, which is basically the enthalpy of the reaction at that temperature. So it's very, very useful tool. Using enthalpy, once I know enthalpy, I have heat capacity data, I can get delta H, delta G, all the information about that material at that particular temperature. So very important technique, very ideal technique to understand. Of course, this is using this we have developed indigenously by our own design. We have developed this inactive. That is this sample I can only use for inactive samples. I can study most of the materials. Mostly we study alloys. I'll give you examples of that by using that. So we also have active ones, particularly for uranium, plutonium. For those studies, we use active system, which is all in the glow box, maintained at a negative temperature, negative pressure, so that nothing comes from inside. So this is in-house developed systems. Now we are also procured one of them. We are collaborating on those lines. So it has a material, something like, I'll not go into details. It has a container, as I told you, a Knudsen cell. You have to heat it to high temperature. The paraphernalia is all given there. And the Knudsen cells, as you see, there are small cells. You put a very small quantity, milligram quantity is sufficient, and you understand its behavior at the high temperature. That's something very interesting. It's actually, the system is of one of its kind. Not many people have in India itself. Somebody approached, they wanted to study the activity of element in a given system. So there is something called high entropy alloys. So they give the sample, they want to study the activity of each of these elements at high temperature. That's one of the studies we are studying right now, we are working on. So some of the systems we are studying, I'll not get into details. The first one is the fuel for the fast reactors in future. Second is, has it applications in pyro reprocessing. It's again a method of separating uranium, plutonium using molten salts. And some of the other systems. This is how it works. So what you do basically is, I was telling you, ascertain the neutral species that comes from mass spectrometer, determine the partial pressures. Once you know the partial pressures at the temperature, you know, you can do many things. You can go back to a Clausius-Clapeyron equation. You can get understanding of most of the thermodynamic properties. Now, the most biggest challenge is how to get that partial pressure. That's what is the challenge. and then you can evaluate the reaction enthalpies, all these things. So I'll not go into details, as I told you this, just to give the overall understanding of how a mass spectrometry as a tool, if it is connected to a good idea. Of course, this idea is almost 100 years old. Application only is coming in the last 20, 30 years. So using the second law, we can estimate delta H of a reaction. What are the reactions at that temperature? So this is a very, very ideal tool for understanding the behavior at high temperature. Similarly, another study on gadolinium we have done. So you can choose the phase field which you are interested in, take it out, then plot. Basically, you are plotting log P versus 1 by T. That's what you do. And then based on that, you can get enthalpy of the reactions at that temperature. But of course, each experiment takes quite some time. Almost to complete one set experiments will take almost 2 to 3 months. So that's a tough part of that. So some of the data we compare with other systems. Okay, what are the other areas we work in Kalpakam? I'll just quickly go through. One of the areas as this is the which I was studying. Dr. Vazira was my mentor those days, where when he was at IGCAR. So we used to develop different molecules for various applications. So TBP is one of the important molecules. A simple molecules, ideally made for DAE or Department of Atomic Energy, because it can be used for many applications, starting from nuclear, the front end to the back end. But when it comes to fast reactors, what are fast reactors? The reactors where we don't use a moderator. The neutron is at high energy. It undergoes fission. It has some advantages. There you can breed, and therefore we don't want it to moderate. So therefore, in a fast reactor, when you want to develop, ultimately we have to do separations of uranium and plutonium. TBP is not a very ideal candidate. It can do many jobs, but not the perfect candidate. So we developed many molecules. Some of the molecules are given here. Ultimately, what is the purpose of these molecules? To prepare them, characterize them, understand whether they can be better than TBP for separations of uranium and plutonium. So that's what we study. A lot of thesis, a lot of students have worked on this. It's a very challenging because synthesis is easy, but once you synthesize and characterize, your quantity requirement is quite high, and therefore, when you have to scaling up, that's really a problem. So therefore, these are some of the systems which you have studied. I'll not get into deep. Recently, we have worked on phosphoramides. This is one of the student PhD just completed. This is another molecule. Actually, so it's something between an amides and a phosphates. It gives some interesting information about the behavior of the molecule of extraction of these molecules with uranium and plutonium. So therefore, once you study, we have to really study in the large scale. That for that we have something called mixer settlers. Whatever you study in the test tube, ultimately if it has to be used in a plant, it has to be tested in some other system like this. So we use different fuels and different molecules to understand its behavior. Ultimately, yes, we understand really? No, you know that if a metal is there, you have a metal complex formation. What about the understanding at the molecular level? So we do some critical studies on them. A lot of challenging task in this particular to estimate the geometry of the ligands, metal complexes. We have a theoretical group to the students who are working on these molecules. So whatever experiments we do, we corroborate with the theoretical job. So some of the studies we are working on the applied theoretical aspects to see what is the role of the structure and the dispersion forces on the extraction behavior. Some of the data, if you want to really understand the molecular level, when you load, because the whole extraction of TBP happens by solvent extraction. Solvent extraction involves two phases, aqueous phase and organic phase. With the organic phase includes a diluent. What happens is sometimes when you load beyond the required level, there is a splitting of the organic phase. And therefore, to understand that behavior, we have to go to a better understanding. And SANS is one technique where you use neutrons from research reactor at BRC to understand that. So for some of the students are working on the SANS data, whatever we generate all the materials, molecules, prepare, go to BRC, get the data, get it analyzed, and then use a better understanding of the behavior of these molecules when you load at higher concentration. The new area we are working on is called metal organic framework, something like inorganic systems, but something between a fusion between organic and inorganic. Its application is huge. A lot of people are working on many areas. Particularly luminescence, I see a lot of papers. Recent times on hydrogen absorption. But our understanding again is to understand, can I use it as a molecule for preferential removal of one element over the other? So we are working on it. There is one or two students working on their thesis on this. But still our task of using at higher acidity is still a long way to go because they all work in the PhD region. It's good for the student work, but really application point of view in the department, we have a long way to go for MOFs. Spectroscopy, Dr. Ramanathan, Dr. Other colleagues are here to explain this. I will not get into that. This is a hardcore basic research. Whatever I've been talking about is all applied research. We do more of application to the department. And in that process, we also get We also do some basic research, but this is a good amount of basic understanding of the molecular interaction, which Dr. Ramanathan and Satyendra Kumar will explain you when you come to the next. I think tomorrow or day after they have a class. Quite a few, they are voracious publishers, and very good. Lot of students are working in this area. This is one area where we can collaborate because it's a very unique kind of facility. He'll talking about parahydrogen. He'll explain in the next his presentation. One of the areas which we were interested recently is the production of strontium 89. Bone cancer, the worst pain is the bone pain, they say. Maybe the tooth pain is equivalent to that. But the cancer patients, the only way to say, give them soothing is to give some of these radioisotopes. There are other isotopes, but we at IGCAR started a program because this reaction can be done only in a fast reactors. It's called NP reactions. You use yttrium and produce strontium, then we do separations. This work is in progress, where we trying to see whether you can make it a scale up. One of the group is working actively on that. If you can produce that, it will be a good indigenous substitution for the imported strontium. Some of the other areas where we worked, last few slides, on the back end of the fuel cycle, where the waste generated at the end of the day has to be immobilized. And there are different ways of doing it. One of them is glass. So borosilicate glass, iron phosphate glass is the research which we are carrying on. At some point of time, this waste has to be immobilized. I was saying it. It has to be whatever material is best. So quite a good amount of work is going on in this field, and quite a few students are working in this. The development of matrices for immobilization of radioisotopes. Again, a lot of basic research to understand the behavior of the glass at high temperature with different radioisotopes. One important area which IGCAR is known is for sensors. Last almost 30-40 years, we have developed many types of sensors, including for nitrogen, hydrogen, ammonia, chlorine. Recently, its application in nuclear reactors is huge. But people also are now there's a demand for outside. Now there is recently there was an agreement with an industry to produce hydrogen sensors, which we want to indigenize and make it cheaper. It has applications in many industries. Of course, sensors has applications for our own department in many areas. What about some of the other areas? People work on pyrotic graphite coating. This comes in the in one of the group which works for various applications, graphene oxide-based composite coatings, superhydrophobic coatings, nanoparticles. They work mostly for avoiding corrosion. So corrosion is a big field in IGCAR because to understand its behavior. So what are the methods by which you can avoid? So these are some of the areas which we work there. The last slide tells about what are the areas. We have also developed something called indigenous calorimeter, which can, if it develops, it will be a very cheaper substitute for the available in the market. KH, this is for plutonium assay. Neutron activation analysis for assay, development of analytical methods based on need. ICP, LIPS, these are the chemical characterization. Ultimately, we work on the fuels, therefore the methods by which you can characterize them. Soldier activity for microscope preparation is one of the area which we're working on. Hydrogen meters for reactors, very important area. As I was saying, it's very important for them to estimate. That tells you about the leak of sodium in the reactor. Electrocatalyst for fuel cells, sodium technology for fast reactors. Sodium is a coolant, so its technology is very important. The science, technology, and its behavior all are important. All is taken care of there. Molten salts. So my colleague Dr. Kumarasan will talk about the molten salts are very important, and it has a huge applications. He'll be dwelling on one of the lectures in the last day or tomorrow, I think. Thank you. Thank you for your attention. Sorry for taking the extra time.
So due to shortage of time, maybe we can take one question. And then Professor Rao is here, so we can discuss during that time. Please. Any question? Okay, so I have Professor Rao one general question. Separating
You're talking about the see, the amount of quantities we handle is very small. It's a more of an analytical tool, as I was saying. Take in milligram scale. It's all these analysis, all this handling is done in a glow box or a fume hood, where there is no direct interaction. That means you handle it very carefully, put a sample into the system. So therefore, the amount we handle is far less. Therefore, there is no issue of safety. But of course, you have to handle it carefully. But when you go to a larger scales, of course, the scales are completely different. When you go for enrichment plant or when you handle high burn up fuel solutions, there you have to be very careful of how you handle it. Yeah, yeah, that, no, that means whatever is required. So one is the distance, time, all those things you have to plan.
Okay, so let's stop here. So let's thank Professor Rao for a wonderful lecture. On behalf of organizing committee, it's my pleasure to present a memo to Professor Rao. So let's thank all the speakers for this session for giving wonderful lectures. And now I hand over mic to Dr. Arindam.
Thank you, Molay. May I call Dr. Sarnappa to present Dr. Molay a small token of appreciation? Thank you, Sarnappa. So we'll break for lunch now, but before that, we have to make few announcements. One is that immediately after the lunch, we'll have our first poster sessions. Poster number 1 through 25 will be evaluated today. The poster session, the evaluation committee will be chaired by Professor P.A. Hassan from BARC, and other members in the evaluation committee would be Dr. C.S. Purohit, Dr. Sudhi Burman, and Dr. Vishnu Prasad Biswal from NISER. By 2:45, we'll try to start it. We are slightly delayed. The second thing is that about the lunch, all outstation delegates and outstation students, the NISER faculty members, they are all taking lunch in the cafeteria here. Due to the space constraints, the rest of them has to go to the community center. There will be a bus waiting for you outside, which will take you to the community center and drop you back. So we'll meet here. We'll try to meet here by 2:45 when the poster session starts, and let's see how it goes. So we have about an hour for lunch. Thank you. Don't worry.
Yeah.
Okay, you can see it regularly then.
Cool, yeah? So, okay. Then it's fine. Paste out. Perfect. Where this one was give feedback to it. And you don't know? No, no, I know. If you are standing here, otherwise nothing. Okay, you can close it. Now I understood. But it means,
Good afternoon, everyone. Welcome back to this second session we're starting. This session is going to be chaired by Professor P.D. Naik, the officiating Vice Chancellor and Dean of HBNI. Professor P.D. Naik joined BARC from the 27th batch of training school in the chemistry on the date 1st of August 1984 after obtaining his PhD degree from Mumbai University. He is a former distinguished scientist of BAE and an associate director of chemistry group in the BARC. In the last 35 years, he has been working in the area of chemical physics to understand microscopic aspects of chemical reactions, employing various spectroscopic tools. He has developed several state-of-art experimental facilities at the BARC. He worked as a visiting scientist for about 2 years at the Institute of Physical Chemistry, University of Heidelberg, Germany, and then as a visiting scientist at NOAA Boulder, Colorado. He is president of the Indian Society of Electroanalytical Chemistry and former president of the Indian Society of Radiation and Photochemical Sciences. His research interest includes chemical dynamics, kinetics, atmospheric chemistry, interfaces, and laser-based chemical instrumentation. He has made very important and substantial contribution to understanding chemical reactions at the microscopic level and in the development of various sophisticated experimental facilities indigenously. He is a recipient of the Homi Bhabha Award for Science and Technology given by DAE India and a fellow of the National Academy of Sciences India. With a short note, I would like to request Professor Naik to please take over this session and share. Thank you.
First of all, let me thank the organizers of NICER for inviting me to chair this session. We have two talks, one from HBNI, Professor P.T.K. Maiti, and other from NICER, Nasu Biswa. In fact, what we have decided, although it's half an hour talk, I would request, if possible, 25 minutes is fine, but if we can complete it by 20 minutes and keep more time for interactions, which is required for this type of meeting, then it will be very nice so that many questions can be taken and students also can get their queries or other doubts clear. First talk is by Professor D.K. Maiti. He is going to talk on theoretical and computation techniques towards deeper understanding and prediction. Professor D.K. Maiti joined BARC in 1990 as a scientific officer from BARC Training School. He is presently senior professor at HBNI, outstanding scientist at DE. He issued his PhD in 1995 from ISCS Calcutta. Then he worked in a postdoctoral research in the area of reaction dynamics at Henley Eyring Centers for Theoretical Chemistry of University of Utah, USA. After his return, in fact, we used to sit together in the same room. We used to share the same room in at BARC at that time. He extensively worked on weekly bound organism radical cations, especially in the area of, in fact, he has published many papers on two-center three-electron bounding systems. And mean is that always he tried theoretical things. In fact, we also worked in some of the type of, we used to do the parts and he used to do theory. He always tried to associate with the experimental group. At that time, Harimon was there, was doing the experiment, and Mighty also doing some experiment at that time and also the theory. That way I also requested, because it is a good, because it gives you a satisfaction that whatever experiment, theoretical calculations we are doing, it is matching with the experiment results. And that may be giving the more satisfaction, just calculating something and without his verification by experimental results. He has published more than 125 general papers, 4 book chapters. In fact, he is teaching for last 30 years in BRT school, Power Center for Science Education at Nagar. He also taken some classes in CBS, CBD, Mumbai University Center. In fact, he's also doing the training in Indian delegation team for International Chemistry Olympiad. And he is representing as a mentor and head mentor of Indian delegation team for International Chemistry Olympiad in 2007, held at Moscow State University, Russia, and again in 2008 in Hungary. He has got many awards. The Fellow of the National Academy of Science, India, the recipient of D. Omi Baba Science and Technology Award, HBNI Distinguished Faculty Award, and bronze medal from Chemical Research Society of India. In academic wise, he is associated with the University of the faculty, and afterwards in 2013 onwards, he is associated with the HBNI as an associate dean and worked extensively in academic counseling, board of studies, also invited for council of management. Apart from that, he is a member of academic council of Jawaharlal Nehru University, Mumbai University, and NICER also. With this brief introduction, I welcome Professor D.K. Maiti to deliver his talk. Professor Maiti, please.
Okay, good afternoon. Thank you, Professor Naik. In fact, let me tell you that I did the experiments for first 7 years after joining BARC. So that's how am really close to, I can understand their language, so experimentalist language. Probably that's the reason I can communicate very efficiently with the experimentalists. Though I was interested from the very beginning in theoretical chemistry. I started my PhD in ICS and completed there itself in the theoretical chemistry only. Anyway, so I'll be talking about, since time has been lost, I'll go quickly. I'll be talking about theoretical and computational techniques towards deeper understanding and prediction. Okay. So since a lot of students are there, I'll just quickly pass through what are the different techniques available under this domain. So there are, you can basically categorize into 4: electronic structure calculation. Electronic structure calculation that describes the motion of electrons and produces energy surface. Because of fixed nuclear coordinate, we solve electronic Schrodinger equation. So as a result, we get surface. And molecular dynamics that describes the motion of atoms within the molecule and surrounding solvent. Of course, statistical mechanics, which provides from microscopic to connect microscopic property to macroscopic property, and that by providing the framework for studying large collection of molecules, and tells us how to average our positions and velocities and to properly simulate the laboratory distribution of molecules. And of course, one can develop formalism and analytical technique to predict or connect different properties of molecular systems. Okay. And typically in electronic structure calculations, what we do, basically you need to have a molecular geometry input,
and that may be through chemical intuition. The best chemical intuition you can do, you can reach quickly to the most stable structure and find out. And eventually we apply Born-Oppenheimer approximation, solve Schrodinger equation, electronic, that is wave function equations, and of course from density also we can calculate, which is eventually foundation of the density control theory. And we get such a reaction surface where there will be many minima, like in a surface there are deeper and shallow holes. So we always try to search for the deepest hole, so that refers to the most stable structure. So naturally we need to optimize the geometrical parameter. So there are different techniques you can do that by, or simply random, you have to scan the whole surface as much as possible so that you don't miss any particular conformer which is the most stable one. So that's the basic thing. Once you know the structure and you get the wave function, so you can do all sorts of molecular property calculations and orbital picture, etc. You can get it. That's how we get much deeper interaction for all those systems. So I'll take just few examples, small examples, which is easily communicable to the students also as well. And one such thing is hydration at molecular level. We from the school level, we know if we add acid to a water molecule, immediately it ionizes. In fact, we did acid-base titrations, and we are very particular. If you can recall your school days, higher secondary, or even first year BSc experiments, from burette, we used to very carefully just add 1 drop of liquid there, so that the exact color change happens. And we say that we have got the correct endpoint. But if you go to the molecular level, you think of that 1 drop means approximately it is 0.05 ml, which has Avogadro number of molecules. So eventually, if we call it is a very small, we are talking about only 1 drop, nothing but it's a bulk phenomena. What happens at the molecular level phenomena? If we try to understand that part, so we have to understand this, that in water medium, water is hydrogenated, hydrogen bonded system. So if you add any acid or any molecule in that sense, it has to break certain hydrogen bonds, and it has to accommodate that extra solute added. So there are processes like in a typical acid thing, it forms the immediate solvent water molecules, they reorient and form contact ion pair, where the just dissociation of this charge separated states is observed, and then finally it forms the 2 parts separated, so separated ion pair. So one can ask that how many water molecules are needed to form a contact ion pair, or can one predict the pK of an acid from this? Because pK is a bulk phenomena, and we are talking here very at molecular level phenomena, how many basic water molecules are needed to break that. Okay, if you finally if you calculate the correct kind of geometry, then you calculate the, say suppose this is the acid and these are the water molecules surrounding this. Here I have shown the structure. You see just three water molecules. This trichloroacetic acid, this OH bond is broken and it has gone to the nearest water molecule. So this contact ion formation is formed. Like this is minus and this part is plus. So that contact ion formation, if you take the energy of this interaction of the solvent molecules with these, if you calculate and if you plot, then one can find out at a particular, like for this acid, if you see at level 6 with 6 water molecules, it gets dissociated, or 6 onwards. And with that, so if you calculate the interaction energy, one can find out exactly what is the minimum number of water molecules required to form a contact ion pair a particular acid. So this search is often become very difficult when the number of water molecules are large and the cluster size is bigger. So there are other techniques. One can do atom center density matrix propagation based on MD kind of simulation, where you can generate low energy equilibrium structure. Then of course, with that structure, you can cut off and select certain input structure and do fine calculations for this kind of generations of contact ion pair. So if I plot the bond dissociation curve, eventually what happens here, if you think of this way, the acid, this OH bond is breaking and this another OH bond is forming. So it is eventually a double well potential. Of course, depending on the strength of this bond and this bond, the potential, well, how much deeper will be that will be different, but eventually you form a double potential. Here I have shown if you see the just relative energy of at different distance of this wedge distance, the energy is kind of up to say 6, you find this kind of potential where you go just cross this contact ion formation, it goes to the next potential. So even what does it mean? That means that barrier of this two potential that diminishes with adding the solvent water molecules. So that's how this kind of dissociation happens and formation of contact ion pair takes place. Okay, and if you do, we have done a series of calculations and we have plotted here. See the with how many water molecules needed to form this contact ion pair and their pK value, we can find this kind of a linear relation. This linear relation suggests that the bulk parameter like pK you can calculate from molecular level information in a non-thermodynamic route, because eventually we are solving Schrodinger equations which is at 0 temperature and 0 pressure. So it's isolated molecular system, and you can in fact calculate the pK, and you can predict for acids where the pK calculation is difficult or rather impossible, you can find out the pK of these. And this, whatever I presented, a series of calculations are there. The student published many papers, but intentionally I have not referred those papers, and I have given this one. The theses are probably many of you don't know. All the theses published by HBNI students are available on HBNI site. You can search, you can go there, even search by name or title, certain topic if you can give, you can get that whole thesis. So the full work is available for all the students or the faculty members, whoever is interested. Like this work, whatever I talked about, Parvati did in our during her PhD work, and it is available in the HBNI website. Similarly, I'll go to another topic quickly. This is bulk detachment energy. Again, there are experiments, beautiful experiments in the molecular beam kind of experiments, and molecular beam experiments are done typically at low pressure and very low temperature, which is very nicely you can collaborate, you can corroborate with the results of quantum mechanical calculations, because that is kind of 0 pressure and 0 K temperature. Here it is shown that if you see with the different kind of cluster size of sulfate ion, if you go for say 20 onwards or 18 onwards, they are slowly started showing the bulk behavior. So it's a question one can ask that at which number of water molecules you can have the bulk feature available from the molecular level feature. That means how you can connect, at what size you can, at what size you can connect molecular level properties to bulk level properties. So there are many people have, based on this experimental data, they have tried to extrapolate and what is the final, bulk detachment energy of the systems of the such anionic species. And but how good is this extrapolation method? We tried to check it, and we find they are not. With the experimental data, it can go up to error up to 57% of error. So we modified this kind of extrapolation procedure based on a semi-grand canonical ensemble developed, and we came out with this kind of relations where if this is the finite for the finite size particular cluster, whatever the VDE ionization energy, and this is for the bulk, where the number of solvent molecules is infinite, solvent water molecules is infinite. It may be water or any other solvent, and then these are the two parameters where sigma is nothing but charge and the solute to solvent volume ratio. With that, we came out with this relation, and after plotting, if you see series of systems, the error is within 10%. So this kind of development was also we did for one system. Now that's what it is concluded, that the microscopic theory is developed to connect bulk VD to and VD of small finite size cluster. And as I showed, the error is less than 10%. Again, this thesis is also available in HBNI site. Okay. Very recently, another one of my students, who was working on neutral and radical cations of chalcogen systems. and chalcogen based in helicene system. And in fact, we are searching for a system where near infrared device application, you can find applications in near infrared devices. So we found that such system where it is a planar up to say almost 6 rings, then on 7 ring, like Thia 7 helicene I have shown here, they lose the planarity, and for this kind of system, it has even experimentally verified that the radical cation of this system is stable up to almost 15 minutes at room temperature, and it is very slow dimerization for in DCM solvent. UV visible spectra show the strong NIR peaks, so it can be suitable for NIR device. Similarly, we applied for this such thing from Thia to Seleno to Tellurium system, and in fact, we calculate the band gaps also, and a lot of data, experimental data, theoretical data at different level and very sophisticated are available. But we are waiting if anybody, probably this part is I'm opening, if anybody is interested, we can collaborate, any experimentalist, especially for selenium or tellurium systems, where a lot of theoretical data is there, and it can really be very interesting project to work on. And again, the whole work is available in a thesis, which is in HBNI website, one can find out. Okay. And very recently, we have done also, try to look for a deep, kind of new deep eutectic solvent, DES, with desired properties. And we, in this, probably many of you know that the DES is an eutectic mixture of Lewis and Bronsted acid and bases that contain a variety of anionic and cationic species. And of course, their general formula is like this, where, this is cationic species, X is Lewis base, maybe mostly it is halide anion, and then a Lewis Bronsted acid with number is the stoichiometric number. And specifically, we were looking for type 3 mixture of quaternary salt, and where it is a mixture of quaternary salt and a hydrogen bond donor, that kind of DES. And we, for the screening, we took so many systems like choline in the cationic system, choline, and then which is nothing but and then of course tetrapropyl ammonium, which is TPA, and tetrabutyl ammonium in the anion part, chloride, bromide, chloride, acetate, nitrate, hydrogen donor side in acid, and of course amide also. And out of all those, so combination, as you can think of, these 3 into 5, so 15 into these. So all possible systems can be from all these possible combination, we can find one particular DES which will be the best suited as per our desired properties for radiation and thermal stable DES. So we choose 3 molecular properties, which is homolumo gap, ionization potential, and electron affinity. And we did a benchmark study, and that at what level these methods, which method particular will be best suited for such calculations. And we calculated homolumo energy gap, ionization potential, and electron, electron affinity. Based on that, we found the choline acetate is the best suited for hydrogen bond acceptor, and for hydrogen bond donor, malonic acid is the best suited. With that, we tried to see even, computationally, we tried to see the phase diagram of this system, and we find 1:2 for 1:2 system. This will form deep eutectic point at -40° centigrade, and then we try to find out what, for 1:2 complexes, what are the interaction energy, how the stability is coming. We analyzed all those parts, and we find that for 1:2 complex of choline acetate and malonic acid is very stable compared to the common one, which is reline, 1:2 choline, chloride and urea. In place of chloride and urea, we have gone to acetate and malonic acid. This particular should be the best suited. With that, we did the experiment. Even it was done like 100, for the radiation stability, we did with say 100 kilogram gamma irradiation, and we found what are the gaseous product with that analyzed. We found hydrogen, carbon monoxide, methane, and carbon dioxide is forming in this, which is much lower than that of choline case, raline system. And physical properties also, if you think of the new DS, is much better than like, viscosity is much lower, and then temperature range also, it is much -75 to room temperature, it is liquid phase. And so all property wise, this particular new choline acetate and malonic acid combination new DS is the best suited for radiation and thermal stable system we are choosing. Okay, so this DS is synthesized and properties are validated. Whatever we predicted, we found that is it. This has gone to part of the thesis of Lavani Das. Again, that thesis is available on the HBNI website. Okay. So after we got the speakers from BRC, I found that there is no speaker from theory side, and BRC has a very strong theory group. So I thought of quickly I just collected slides from different theory group from BARC, and I will quickly go so that just so display their expertise and different kind of area what area they are working. So this is in the multi-scale modeling and computation simulations. They are working on like this is theoretical chemistry section under chemistry group, nuclear material and fuel cycle, soft condensed matter. In the nuclear material and fuel cycle, they are working towards damages in nuclear structural material, absorption of and extraction of heavy metal ions using functionalized nanomaterial, absorption and diffusion of actinide ions in water clay material, effect of fission products on nuclear fuels. In soft condensed matter, pattern formation on C60 surface, domain formation in room temperature ionic liquid, ionic accumulation of water orientation, air water and alcohol water interfaces, fluid behavior and dynamics in and around carbonaceous nanomaterial. And not only that, they are also working in the area of energy and environment, where water splitting and photovoltaic, like development of novel photocatalysts for water catalysts. Mostly these are purely computational work, hydrogen storage and carbon dioxide capture. And in the area of bio-inspired research, hydration of bioorganic molecules and protein denaturations, protein drug interactions, just to understand how a drug molecule accomplishes its task interacting with protein molecules, as well as there are people who are extensively working on theory and methodology development, like accurate computation of negative ion resonance states, development of relativistic methods and implementation. And he has, Dr. Nayak, he has also contributed to Dirac code, which is the code for relativistic calculations based on his methodology development. And there are groups who are working in cluster chemistry. They are working on fundamental studies in metal cluster to know structure, bonding, and reactivity, and on different kind of applications also, like nanocatalysis on carbon oxidation, on platinum 10, on alumina surface, graphene like tin nanoseed on gold surface, as well as hydrogen storage on the nanotube based on boron carbon nanotube, as well as sulfur SO3 decomposition on platinum cluster dispersed systems, and other group who is basically working from kind of engineering. They are connecting molecular level properties to engineering systems even through bottom-up approach. They are working on molecular engineering to design and testing molecules with desired properties, behavior, interactions in order to assemble better materials, systems, and processes. Molecular engineering covers computation tools. They are also working in the experiment and characterization methods. So their research area is like energy material, solvent extraction and isotope separation, permeation and storage of hydrogen isotopes, glass formations, membrane desalination, and of course they have done on adsorption for ion exchange. And they are applying like quantum mechanical methods and ab initio MD simulations, classical MD simulation, statistical mechanics, and of course experiments. So all sorts of expertise, in fact, available in BARC, and whatever first 3 points I was talking from my research group, whatever we have done. So I think this covers from BRC side and our side for entire work. And as this can be summarized, that molecules to materials and multi-scale modeling and simulation, entire domain people are working in the interdisciplinary basic research at the interface between chemistry, physics, material science, chemical engineering, and biology. material related like nanomaterial, energy related, hydrogen energy, waste management, ligand design, dynamics in condensed space, soft matter under nano confinement, experiment driven theoretical studies, biology inspired theoretical studies, of course, curiosity driven research also. So development of new theoretical formalism, modeling and simulation. So entire domain, there are experts available in BRC, and so if anybody is interested to collaborate with them, they can contact directly. I'll just tell that this particular slide was given by Professor Musharraf Ali, who is in the chemical engineering division. This was given by Professor Mojumdar, who is in chemistry division, and these two slides were given by Professor Niharendu Chaudhary, who is in theoretical chemistry section of chemistry division, chemistry group. So that makes complete my presentation. I hope I have conveyed what kind of work is being carried out at BRC as you in a in few slides. Thank you very much.
Thank you, Professor Maiti, and he completed in a much earlier than expected. And thanks for covering the work of theoretical chemistry section. Previously, it was intermediate section. Now, he mentioned various types of theoretical work is carried out in that section. And they have expertise in various domain areas, you might have mentioned. And they are very helpful, and most experimental persons here, if they want to take, or even a theoretical, if they want to have some joint programs with them, it will be very highly welcome. Because this is an interaction meeting, and it is better to cover all the expertise available at HBNI at different CIOCs of HBNI. And I thank Dr. Maiti, apart from his own work, he given enough time for others' work also. Thank you, Dr. Maiti. And talk is open for discussion.
Yeah, please.
You are talking about this, I think the third presentation, your work, you mentioned about the DES. You are talking about one new DES, where you said that this boiling point is, at room temperature.
Stability range is much higher. Yeah.
But the viscosity is still,
no, it is lower than Relin, but of course it is not as per expected. It should be much lower.
And what is the exact application of this DES you are talking about?
No, see, we are looking for this DES where the final next step is we should see that extraction behavior of actinides or other. That part we have not done yet. That's the first thing. This has been published also. The first thing was designing the new DES, okay, which is radiation stable as well as thermal more stable, because as you can see the temperature.
So if it is the extraction you are talking, then it should be water immiscible.
Yeah.
So this is a water immiscible DES, whatever you are talking about.
Water immiscible, it remains, I think only 1%. You can remove water up to 99%. We tried.
Whether it forms two phases with,
No.
So that, so then extraction cannot be done. If it is miscible, I mean, it's the phase disengagement should be much fast. You want to use for a separation, basically two phase
that needs more experiment. But basically, Laboni was doing the experiments.
Yeah.
Mostly it is a.
No, I understand your viewpoint.
Yeah. Next aspect is yes.
But the other thing people look for in the DES is a dissolution. So there you don't need a water immiscible type of thing. So for dissolution also the viscosity should be much lower. Otherwise, the mass transfer will be slow. It will take very long
dissolution time. Also, one student now she's working on the kind of, eventually she will work on DES for the dissolution. That is different aspect. We are looking into it. She has just started in ionic liquid. Now slowly move to the DES. That part, yes, that we have kept in mind.
And the radiation chemistry data you have been 100 EV data, that is for actual experimental data?
Yeah, actual experiment.
Okay, thank you very much.
Just to see the radiation stability. And in all cases, whatever the gaseous product formed, that was much less than Relin, which is commonly known as the DES, most acceptable DES.
And if there are no more queries and other things, again, let us thank Prof. Maiti for Yes, and next speaker is from NICER, School of Chemical Sciences. My good friend Himanshu Biswal. He is going to talk on non-covalent interactions with carbon, experimental challenges, and apart from the academic work and other things, he's also involved in many outreach programs. He had developed for the college and school many softwares so that they can feel the experimental power of spectroscopy and other things. Coming to Himanshu Biswal, he is Associate Professor of Chemistry at School of Chemical Sciences, NICER. He received his MSc degree from Department of Chemistry, Utkal University in 2002. And he did his PhD with Professor Sanjay Vategaonkar from TIAFA. In May 2009, he completed his work. Then he moved first year done to postdoc. One is Paris, France, and second one is with postdoctoral research with CNRS postdoctoral fellowship, and with Professor Michael Notz. And second postdoc, he worked on 2D electron spectroscopy of photosynthetic reaction centers with Professor Jennifer Ogilvy at University of Michigan, USA. He joined NICER School of Chemical Sciences in April 2012. He involved in building scientific instruments. I know how difficult it is, and he has beautifully set up the things and doing various work on hydrogen bonding in selenium, sulfur, and other things, PET things. He started, in fact, he is the pioneer. He has started during his PhD work at TIAFA, sulfur hydrogen bond, and this is well recognized work. Many of you might have seen at NICER is set up. This is itself a great achievement. His current research interests include observations and isomerizations of peptides, computational landscape of flexible biomolecules in jet-cooled conditions, where we can get temperature around. I don't know, in his case, around very low temperature, we can cool in a jet cool under supersonic jet condition. Is mainly doing the work on sulfur, selenium, carbon-centered hydrogen bonds, and their role in structure and functions of biomolecules. And biomolecules are very important in hydrogen bond, although it is work which is very fundamental, it is having very high connectivity with the biochemistry of our systems. With the introduction, I request Professor Himanshu Biswal to deliver his talk.
Okay, so thank you, Professor Naik, for the introduction. Organizers like HBNI for giving me the opportunity to present my voice. So what, before presenting this one, non-covalent interaction with carbon, I briefly tell what we are doing at NICER. So we are looking at mostly the research theme is non-covalent interactions, hydrogen bonding, and the non-covalent interactions with the less electronegative atoms, such as sulfur, selenium, tellurium, polonium, and okay, in silicon also. So this one, so today what I'll be talking about this one, the non-covalent interaction with carbon. So we have a lot of work done for sulfur and selenium. The time permits, I'll briefly go through this one. We have started looking at how to apply those non-covalent interactions to understand and the biomolecular structure, maybe some applications for stabilizing the proteins, the DNA for the storage purposes. Then the excited state dynamics, photodynamic therapy, photosynthesizers. Again, so the theme is sulfur and selenium hydrogen bonding. We have applied those there to those systems. We started looking at how the non-covalent interactions, mostly the hydrogen bonding, is crucial for designing the catalyst. It's not new. I'm not telling it's new. We were trying to give a spectroscopic view, molecular spectroscopic view, how the hydrogen bonding is crucial for the clean water on water catalysis. This one we just started. The instrument has just arrived and we're building up. So we want to do the parallel recognition and parallel transport. And the parallel recognition, if you look at, this is the one anesthetic ketamine. So the D form of the ketamine is active, the L form is not. So there is nothing changed. The only change is here, the NH and this one. It's again, it's an effect of non-covalent interaction. We are trying to address it. How is it going and binding to the particular site of the protein or some other drug site. For that, actually, to do this type of study at the molecular level, you need to build the instruments. It's not the conventional spectroscopy methods available at your hand, at your reach. You can use them. You need to build those sophisticated instruments whenever you want to do some special experiments. If time permits, I'll cover this part a bit and this part. Okay, so non-covalent interaction, there are many of interactions. Chemists actually try to remember the interactions in different names, like the organic name reactions. So these are named after donor atoms. So we call this is hydrogen bonding. The lone pair is going to the sigma star orbital or antibody sigma orbital of OH bond. This is called hydrogen bonding. Everybody knows it. This is called nitrogen bonding because this phosphorus group is called nitrogen and it's called nitrogen bonding. Then you have halogen bonding, chalcogen bonding, carbon bonding, and the halogen bonding. So I'll emphasize this one again. So why we are interested to look at the less electronegative atoms? So there are many reasons. A few of the reasons I'll tell actually. If you look at this is taken from a biochemist book. And if you look at the just notes in proteins, DNA, you have a hydrogen bonding and the hydrogen bond donor and oxygen will be the acceptor or the nitrogen will be the acceptor. There are very few reports where you can find the sulfur to be the hydrogen bond acceptor. Again, they call this is a hydrophobic core. You have plenty of carbon atoms and this carbon actually repel or water or something. And that's why it is called hydrophobic. So is it possible? There are many CO stuff in here, so there is possibility of this type of interaction, and this interaction is called carbon bond. Okay, so this is not only that the textbook, this recent IPAC definition also says the X will be more electronegative and you should have a hydrogen bond, then the X should be more electronegative than the hydrogen. Similarly, Y also should have lone pair of electrons or it should have some pi electrons. So we have few cases I'll present where this X can be electropositive and the Y can be sigma positive. This is again another stuff. Mostly this plot actually done in a long back, maybe when I was started doing my PhD. And this one is because of the available data, and people are thinking only the electronegativity is the important essential factor to have a very strong hydrogen bond. That's not true. So while considering those, always we forget about the polarizability. If you go along the group, the polarizability increases. Going down the group, along the row, the polarizability increases. and down the group the collaterality increases. Okay, so we need to consider both of them to tell from a strong hydrogen bond or the weak hydrogen bond. This again recently it was celebrated. The whole purpose of telling this one, there are a lot of work has been done in sulfur in last 20 years, but still it is elusive. I mean to say here, so you can have a dimer, very small dimer like this one. You can have a this hydrogen bond, sulfur hydrogen bond. You can have sulfur hydrogen bond in proteins, and this is one of the examples where it regulates the activity of reduction and reduction through this hydrogen bond. Okay. So as I said, you can have, they always say X and Y are electronegative. We have shown actually, so this can be metal, it can be iron or anything else. It's no more oxygen or nitrogen. It can be anything. Okay, so we have done a lot of work to establish that both theoretically and experimentally. And this is the spectrum we have recorded mostly in TIFR. We didn't have facility at NICER, recently we built it. And we proved that it's, if you compare, there are many different type of hydrogen bond acceptors. And we compared the sulfur, oxygen, and selenium with the pi, and sorry, sulfur, selenium with pi and oxygen. And you can find that the sulfur is a strong hydrogen bond acceptor. Selenium is a little weak, but it can form hydrogen bonds. Okay, so recently we showed it theoretically. Maybe somebody will prove it experimentally. Polonium can form hydrogen bonds also. Okay, so there are a lot of difficulties to record the spectrum. It looks nice. In one plot I have put it, but it took almost 10 years to record this spectrum. So to record one spectrum, maybe it takes about 6 months to have a nice spectrum. Okay, so coming back, why hydrophobic bond? Then why we are interested for the carbon center non-covalent interactions? We are interested because of the hydrophobic, people call it hydrophobic interaction, hydrophobic bond. There are many different types of definitions are there. This is one of the definitions I want to highlight. So there they say this alpha definition, this is the name arises, this hydrophobic interaction or whatever, it arises from the attribution of the phenomenon to the apparent repulsion between the water and hydrocarbons. However, the name is hydrophobic because of this one. However, the phenomenon ought to be attributed to the effect of hydrocarbon-like groups on water reflection. It is the hydrocarbon groups, how it changes the water structures or water interaction that leads to the hydrophobic interaction. Then this paper appeared in 2013, where the first said that this carbon, you have a methanol and water, you can have a hydrogen bond with this one OH group, you can have other interaction. Okay. So this interaction where this oxygen lone pair is going to the sigma star of CO bond, and this interaction is to a carbon bond, and you can have such interactions in proteins, in molecular crystals. There are many other stuff people have studied looked at it. But till today I say that no experimental proof. We tried, many people tried, but they didn't succeed. So how do we prove it experimentally? We can do the binding energy calculations, quantum mechanical calculations, then verify it with ITC or NMR experiments or complicated gas phase experiments. You can have electron density between the interacting atoms in quantum mechanical calculation or XRD, then donor acceptor orbital overlap. That information will get the NBO calculation, the IR spectroscopy, the change in chemical shape, change in the vibration frequency. Those you can get, you can calculate or you can find it out from the spectroscopy measurement. So main problem is how to stabilize a dimer, okay, and detect the dimer. This is to do the condensed phase spectroscopy. You will have plenty of molecules. You don't know whether you are forming a dimer, trimer, or tetramer, or you are detecting a dimer, trimer, or tetramer. So you need another spectroscopy, which is called supersonic jet spectroscopy, and some instruments. If I get time, I'll elaborate, or I'll briefly tell that one. This is what a lot of efforts, as I said, was given to establish the carbon bonding experimentally. This is one of the report which appeared in 2015, this solicited NMR. So they said that the carbon bonding between this oxygen and this carbon can be possible, and you can see a downfield shift of this carbon with respect to the monomer. Okay, this is the first experimental evidence in solid state. Then there is one theoretical paper appeared. There could be, they say, there could be a downfield shift as they have observed, but the downfield shift is not small, it should be a huge downfield shift. Okay. Then this paper appeared when we were doing the experiment, and we also submitted at the same time in the JAX paper. The paper was halted there for a long time, and this paper appeared after some days after rejection of our paper. This paper said, okay, that they have given the first experimental proof in solution phase of the carbon bond. What is the experimental proof? They have stabilized some complexes like this, and they have done this is the ITC curve. They have done the NMR measurements, and this is what they are telling. Okay, so remember the solid state NMR said you have a downfield shift, then the gas phase NMR calculation says you will have a huge downfield shift. And this paper, contrary to those, this paper says you will have a huge upfield shift if there is a carbon bond. Okay, 100 ppm upfield shift. I don't find any literature after I searched. I didn't find a single literature where they report 100 ppm of NMR shift for a non-covalent interaction. Anyway, so JAX and the big source, so we cannot go anything. Okay, so this is the summary here. So when you will have this 100 ppm of downfield shift or upfield shift, when you make a acetone to ethanol, right? If you make a double bond, double covalent bond to single covalent bond, you can have this magnitude of shift. And this will not happen with non-covalent interaction. Okay, so what to believe? So we were in troublesome, a paper was rejected. What to believe? Solid, solution, or gas phase data? Solid says small downfield shift, solution says high upfield shift, gas phase says high downfield shift. Whom to believe? The NMR experiment or the cluster, the computation? Where to believe? Hardcore physical chemistry journal or a highly impactful JAX paper? Okay, so there are many stuff. You have to scratch your head, nothing else. Then go back. Then we thought we'll go back, look at this one in more detail, write your own program, and find it out whether such interactions that really exist in the real system, like proteins and biomolecules. We wrote our program in Python to look for the proteins. In reality, we found thousands of such interactions in proteins, and they are there in all the secondary structure of the proteins. We calculated many of them to this one from the protein and took the interacting part and did the calculation. We found these energies can be 30 kilojoule per mole maximum. This paper after this was published in NUChem. Then these are the few stuff I have shown from the protein structures where you have such interactions. Then we thought we have now understood that there are such interactions in proteins. We can model them, take a simple molecules. We took these as the carbon bond donor and this is the acceptor, and we did a lot of calculation to establish that this type of carbon bonding is possible. Then you choose this one, the acetonitrile and NN dimethyl acetamide complex to experimentally establish the carbon bond in solution. We did the calculation or did the experiment, NMR experiment. Okay, so if you look at what we observe actually, we observe no large distilling, it's slightly shielded, this carbon, it's slightly shielded and it doesn't match any of them, neither the gas phase data or the solution phase data. Okay. Then we did some IR calculations also, but the IR was not that convincing to tell this one. Still, this experimental data is there. We could not convince ourselves to publish it. Then we came across this paper. It was just published 2 years back in 2010. They said this is the rotational spectroscopy, and they say they have observed the experimental observations experimental proof they have given for the carbon bonding through the distant spectroscopy. Then we thought we'll take this model and try to do the solution phase experiment and establish the carbon bonding in solution. We did the experiment. What we observed actually, we go on increasing the concentration or either one of them, and what we found, this one, the concentration of tetrahydrofuran go on increasing. This one was downfield shifted. These carbons were downfield shifted, and it goes on increasing. Okay, there was if you have a dimer formation, you will have a saturation after some concentration. Always you will have a sigmoidal. If you are very low, starting from a very low temperature to high temperature, or you will have a half sigmoidal curve. We didn't observe that one. That was again puzzling. There is a shift. It goes on increasing. And what we observe actually, this nitrile group are very sensitive to the polarity of the solvent. Then we calculated the polarity of the solution, basically the dielectric constant, and plotted it has a very similar correlation what we observed. So while doing the titration, adding more and more THF with CL3, we are increasing the dielectric constant, and it leads to the shift in the nitrile NMR peak. Okay, so we rejected those data. Then we thought of we take another resisting. We first did the molecular dynamic simulations to see whether we can have carbon bonds. We didn't observe actually. It has a structure like this. And after doing a lot of analysis, we found that these are not the carbon bond interactions. These are the N pi star interactions. Okay. Anyway, so we did a lot of calculation to establish that these are the N pi star interactions. This system, we did the NMR titration. As I said, you will have a half sigmoidal curve. You will have a saturation. Then we did the temperature dependent NMR titration, concentration dependent NMR titrations. We can find out the free energy of binding, the enthalpy of binding, and the entropy of binding. Anyway, so this one again, we failed to prove that it is a carbon bonding. It is N pi star interaction. Maybe this is our fortune. This one was the first paper to establish N pi star interaction, intermolecular N pi star interaction in solution. This was very recently, 3-4 months back, it was published. Okay, so do we have any consequences of carbon bonding? Okay, so this is one of the paper actually while looking at carbon bonding in proteins. We found this paper in 2015. Why I'm telling this one, the basic understanding sometimes helps others actually on non-specialized from your subject to explain their data correctly. So what they said, so they were doing the photodissociation of carbon monoxide with a laser, femtosecond laser. So the extra energy after the dissociation, the extra energy is dissipated through this molecule from this side to that side. Okay, from here, from this center to here. This one is far away from the center. Okay, and they observe the dissipation or that dissipation leads to the vibration of that part, and the vibration time period for this one was 500 femtosecond. And they explain this one how this energy transfer happens. They explain there are multiple hydrogen bonds, 4 to 5 hydrogen bonds, and that through that hydrogen bond, the energy transfer happens. What we observe carefully looking at the structure, you have this moiety has a carbonyl group which is directly linked to this moiety, the heme moiety. Okay, we did the calculation and find it out what will be the intermolecular vibration frequency for this type of interaction, and we found that it is 75 wave number. If you convert to this time period, it is about 450 femtosecond. So this 500 femtosecond, whatever is coming, is not through the hydrogen bonding, it's through the carbon bonding. We have time. So this one, then we came across this molecule. This is the crystal structure. If this molecule doesn't have any functional group, but it has a nice crystal cracking. We looked at how they are held together. We found that there is a interaction, there is a CH bond, and there is a carbon. This carbon is not the tetrahedral carbon actually, but it is inverted carbon. And this type of interaction was never observed, and in this paper also they have not, oh, sorry, I forgot to cite this paper. They have not mentioned that. We did this analysis. We took a very simple propellant dimer which has inverted carbon. We did the analysis. So it has two properties like the hydrogen bonding and carbon property. The carbon bonding, this is how the carbon bond looks like. This is how the hydrogen bond looks like. It has both the property. If you look at the orbital overlap, so we named it carbohydrogen bond. Okay, so it has a very bad property. Anyway, so this was we named, this we call carbohydrogen bond. Okay. So we did a lot of analysis. In all the cases, whatever I showed, the carbon bond, hydrogen bond, it has one-way transfer of the electrons or overlap. So this one, you have two-way. So in one case, it will be the one part will be the acceptor. In another case, it will be the donor. So that's why if you look at the forward interaction is 7.06 kilojoule per mole, the backward is 4.28, which is 38%. We compare with all other stuff. We didn't find any other interacting, very similar non-covalent interacting system. We didn't observe such type of interaction. Okay, so this one, I'll skip. I'll form this one. This is the paper. So by Francis Ornello, she was the Nobel laureate of 2018. It was published in Science. This paper says, so what they did the mutation. They were synthesizing this inverted carbon-like molecule. In this paper, they say when they mutate, actually, a non-aromatic amino acid with an aromatic amino acid, there is a turnover number increase of 1.5 to 2 times. They said it is because of the pi-pi stacking, it stabilized the intermediates and is thermodynamically favorable. When they mutate, actually, where is when they mutate serine with alanine, they got more than 2.5 times increase in turnover number. So serine and alanine, they have very similar structure. Serine has a side chain which contains an alcohol group. Okay. So then the product is this one. What is happening actually because of the serine forms a carbohydrogen bond with the product and it doesn't allow the product to come out of the enzymatic cavity. If the product will not come out, then the reaction will not proceed. That's what, since it was not there, after doing this one, then we communicated to Professor Ornello, and I thought I was very afraid of communicating. And really, they are humble. They are very so nice, so humble. She replied to me and saying that, thanks for sharing your work. Very glad to see that you used your newly established concept of carbohydrogen bond to explain the mutation effect in our paper. It is very interesting study. Okay, so I'm not claiming that I have explained that one, but there is one direction of one can take. This can lead to explain big science papers. We cannot publish in science. Okay. The thing is coming to the challenges. Okay, we establish computationally. We can predict computationally the spectra. These are the spectra predicted, which I'll try my best to do the experiment and prove it. These are the NMR stuff. These are the, again, carbon and proton NMR and IR. I don't have time actually. In experimentally what we do, come to the what is the bottleneck to doing the experiment. Okay. So what we do in gas phase, we just look at very few things. The band origin. Anything? I'll take 3-4 minutes. So we look at the shift in the band origin from monomer to dimer or hydrogen bond complexes. Or we look at if you have a hydrogen bonding like this, we look at what happens when it is hydrogen, this is the vibration frequency, what happens to the vibration frequency of OH when it forms hydrogen bonding. This is one of the system I want to show all the audience. So this is the paracrystal excitation spectrum, okay, recorded in hexene. The full width half maximum is 1600 wave number, okay. This is the IR spectrum. Again, in hexene, the full width in room temperature. In hexene, in our conventional spectroscopy, the full width have maximum is 310 number. Okay. So what as I mentioned here, what we observe for a dimer, we observe only the band origin comes from here. We observe about 100 to 1000 wave number shift. Or the frequency shift may be 20 to 300. Then there is something called the intermolecular stretching. This one, the sigma, it is 30 to 150. If you have a full width half maximum of 300, how can you see a shift of 20 to 300 wave number? Impossible. Okay. So if you have a shift of 100 to 1000, you have a wave number of 1600 wave number full width half maximum, you can never see. For that, you need a very specialized spectroscopy. We call it spectroscopy. I don't have time. So what I'll tell, what we achieve in this, to explain this one, I don't have time. What we achieve in this one, we can pull down up to 10 to 15 Kelvin. So rotational temperature, we did reduce the spectral bonding and congestion, get high resolution spectrum, and the full width half maximum is about 5 wave number, which is at least 100 times less than the conventional spectroscopy. Okay. I'll show, I'm not telling lies, so I'll show the spectrum we recorded in Niger here in our new spectrometer. This is the excitation spectrum, what we recorded using our TCS, whatever machine we have fluorimeter. And this one, you look at the paracristals here, just a line, paracrystal methanol, another line, paracrystal water. So it doesn't have this one, it has also selectivity. If you compare the full width half maximum, it is 15 to 1600 wave number. This one is 4 to 7 wave number. Okay, you can see what is the resolution we gain. And not only that, we have the selectivity. I can select a monomer, I can select a dimer, I can do both UV and IR spectroscopy. Okay, so there are a lot of challenges. I'll summarize. Non-covalent interaction with carbon is possible. The strength of carbon and carbohydrogen bond within 10 to 40 kilojoule per mole. Okay, so this one needs to be verified with the different spectroscopy. Anyway, so whether you do the computational experiment or the experiment with this one, this is what I don't say, the Richard Feynman says. The test of all knowledge is experiment. Experiment is the sole judge of scientific truth. So let's do some experiment. And I have noted down few of the challenges, and many more challenges are noted down in this two summary of our work, the accounts of chemical research and chemical research. I'm really thankful to all of my students. So most of the works was done by my PhD students here, 5, 6 PhD students, and MSc students. I'm really lucky to have many nice students to work under me, work with me. I'm very thankful to my teachers, collaborators, the financial support from Niger, from DAE, from Inspire Fellowship, ACRB. Thank you.
Thanks, Himanshu, for a nice presentation of your work and other things. And I hope that your experiment setup is ready soon. And you have all the systems now, only your laser systems are the
Yes, laser. And when we fail, that is the hidden tears actually we have. So one Belgium engineer, he gave the laser for last 2.5 years back. He's not coming to install it. So we are handicapped also for many things. We were so for this type of spectroscopy, it is not only money. So you are dependent on so many people, workshop to electrician to vacuum pump guys to many things. Struggling. Anyway, we succeed. 10 years in maybe another 5 years. We'll never give up.
Yes, I can understand. I also worked in a similar area. Setup itself is a really difficult task. But what do you think? What about TFR setup is
Okay, I'll tell them. We don't have a discussion.
Okay, that's fine. The talk is open for discussion. Yes.
Very nice lecture, sir. Actually, how to differentiate carbon bonding from N5 star interactions are actually. In majority of the cases, it looks like it is carbon bonding, but it is simply an N5 star interaction. Any
No,
theoretical tool?
Carbon bonding, if you look at, if I have a CH3F, okay, there is no pi electrons. Okay, then it is possible. If I take a methanol or dimethyl ether and a chloromethane, okay, you can have an interaction dimethyl ether which is pointing towards carbon. There you don't have a pi. That's called the carbon potential. Okay. Mostly, if you look at the objective picture, it goes to the electron. There is overlap between the lone pair of electron and the sigma star or clubs one.
Yeah, actually, that is a sigma hole driven carbon
Exactly.
bond, right?
Yes.
But there is also possibility of pi hole driven carbon
Yes,
bond.
yes.
For example, acetaldehyde dimer.
Sure.
Like we did some experiments and also we did do the computations and we found out like it is exactly similar to the carbon bonding. But still, like we are afraid whether it is really carbon bonding or it is.
Yeah. So, if still they have not defined it properly, maybe there will be will make another alpha committee to define it. So what you were telling, still now we are following, if I go following the geometrical criteria, the donor acceptor, these three atoms, they should be 160 to 180 degree. What you might be observing.
90 degree.
Yes.
90
That's
degree,
a-
but
that could be-
it can be like explained as it's a pi hole driven carbon bonding.
Pi star is also pi hole driven, n pi star.
Okay, okay. And one more thing is like the propylene dimer you were talking about now, sir. That is hydrogen bonding without lone pair of electrons. Like in the case of cyclohexane dimer, like also like we have the similar situation where it is basically a sandwich structure, right? Is it possible to explain as sigma stacking, which is similar to that of a benzene dimer, which is a pi stacked structure?
But what is the binding energy for that
The
one?
binding energy is almost 5 kilocalorie per mole.
5 calorie is huge. It will not be.
Uh, but actually,
It will pull within a 2 kilocalorie maximum.
okay, because cyclohexane dimer structure we studied and we did matrix isolation also. We published saying that it is a sigma stacking because
I know that.
you saw the paper. Okay, yeah, thank you.
Students.
Talk and thanks again for giving the excellent talk and we know about your work all the times and keep it up and this session ends with these two important talks connected to theoretical as well as experimental part. I thank both the speakers, Professor D.K. Maiti and Himanshu Biswal for giving you a nice presentation of their work within the time. Thanks to everyone.
On behalf of the organizers, we thank Professor Naik for chairing this session. May I call Professor Anapat to this present one. I meant to Professor Naik. So we break for snacks for 30 minutes now, and we'll assemble back again around 6:05 for the last session. Thank you. Welcome back to the last session of today. In this session, we have two talks, and this session is going to be chaired by Dr. Tapan Kumar Ghanti, who is currently holding the position of Director, Bioscience Group at the Bhabha Atomic Research Center. He is a professor of Homi Bhabha National Institute and was serving as Dean Academic for the Bharat Chemical Sciences from January 2020 to December 2022. After obtaining his chemistry degree in physical chemistry from the Bardwan University, Dr. Gandhi joined BARC in 1988 to the 32nd batch training school and received Homi Bhabha Award. He obtained his PhD degree in chemistry from Bombay University in 1996 for his work on density functional theory and chemical binding and chemical reactivity on molecular systems. He has spent 2 years, that is in 1997 to 1999, at the chemistry department, Indiana University, USA, as a postdoctoral fellow. His field of research encompasses theoretical and computational chemistry, density functional theory. He is actively involved in theoretical prediction of novel gases and novel gas compounds, design of materials for trapping novel gases, computational investigation of structure and properties of hydrogen bonded systems, supramolecular chemistry, electronic excited states, clusters, and clusters assembled materials. He is also involved in study of structure and bonding in lanthanide and actinide complexes relevant to the nuclear waste management. He is recipient of DAE Scientific and Technical Excellence Award in the year 2009 for his important contribution on the prediction of chemical compounds involving noble gas, noble metal chemical bond. In 2014, he received the Homi Bhabha Science and Technology Award for his work on lanthanide-actinide separation and prediction of actinide encapsulated fullerenes. He is a fellow of Maharashtra Academy of Sciences. He has been elected as a fellow of National Academy of Sciences India in 2014. Dr. Ghanti has co-authored more than 170 papers in peer-reviewed international journals. With this short introduction, now may I request Professor Ghanti to please take over and chair this session.
Thank you, Dr. Arindam, for kind introduction. First, I would like to thank the organizer for giving me this opportunity to chair this session. We have two talks in this session. First one is by Dr. V. Sudarshan. Just to introduce to him, Dr. V. Sudarshan did his MSc in chemistry discipline from IIT Madras and joined chemistry division of BRC in the year 1994. He received his PhD in chemistry from Mumbai University and subsequently worked as a postdoctoral fellow at the University of Victoria, British Columbia, Canada, in the area of structural aspects of luminescence properties of inorganic nanoparticles. He has published more than 200 research papers in peer-reviewed journals and 4 book chapters. He is a recipient of several awards, including Scientific and Technical Excellence Award of Department of Atomic Energy, and then Group Achievement Award, Homi Bhabha Science and Technology Award. He is an elected fellow of National Academy of Sciences, India. Currently, he is working in the areas of hydrogen storage materials, glasses for nuclear applications, and luminescence nanoparticles. Dr. Sudarshan will talk about materials for sustainable lighting and clean energy applications. Dr. Sudarshan, please. 25 minutes presentation followed by 5 minutes discussion. Please restrict to 25 minutes.
For the kind words. The outset, I thank the organizers of both the HBNI and the NISA for giving me this opportunity to stand before you and speak about some of our work, which we have been doing for the last 6-7 years.
method. Okay, let us start. Sorry for the trouble. See, after hearing a lot about spectroscopy, theoretical work, etc., now we are going to hear about some material development. So I have been talking on sustainable lighting, development of materials for sustainable lighting and clean energy application. There are two groups working in this area. One is working with sustainable lighting and another is on clean energy applications, mainly hydrogen storage. So plan of my presentation is like this: what is sustainable energy and what is sustainable energy and what is sustainable lighting and clean energy and materials for sustainable lighting and clean energy. So these are, I will not be covering all the materials, some of the representative materials which are electroluminescents, which are used for making sustainable lighting, I will be discussing. This will be followed by hydrogen storage materials. And then summary of the talk. So we all know electrical energy used for lighting applications very widely. So a lot of lighting is required in the roads, public buildings, government hospitals, or hospitals, or public places like railway station, airports, bus stands, etc. So if you see the survey of DOE, and if you publish this, if you see the published book of R&D opportunities on solid state lighting by DOE 2022, around 20% of the energy, electrical energy, is used for lighting applications. So one of the goals of DOE is that by 2030, reduce that use by 50%. That is, make it 10%. So that this is nothing but energy saving. So we all know saving energy is a very important aspect, because if you can save 1 unit of electricity, it is generally said it is equivalent to creating 2 units of electricity, or it is equivalent to generation of 2 units of electricity. Why? Because a lot of energy is lost in transmission. So if you can save 1 unit, it is equivalent to 2 units of energy. So one approach for saving energy is use energy efficient, cost effective lighting, particularly from powders, not from thin films, because if you make a thin film device, again it will be costly. So if you can make high quality electroluminescent devices, which are nothing but solid state light emitting devices, then we will be definitely saving energy on that, and this can help for a sustainable development of the society. So today morning also there was a talk on, it was mentioned about the sustainable development. In fact, the last year, 2020-22, was declared as the International Year of Basic Sciences for Sustainable Development. So what is the sustainable development? It is nothing but development that meets the needs of the present without compromising the ability of future generations to meet their own needs. So sustainable lighting has an advantage. As I told, there are many advantages. One is the sustainable or the solid state light have advantages like they are digitally controllable, because normal lights are not digitally controllable. Like CFL lamp, it is not digitally controllable. Their intensity can be controlled, their wavelengths can be controlled. And there have normally, if you can have very high lifetime, it will be always better, more than 30,000 hours. So invariably, such solid state light emitting devices have no mercury content, and there is no IR or UV radiation which are harmful to human life. So these type of features enables new lighting capabilities. Like you can have adaptive lighting, you can have environment, controlled environment agriculture. Because if light emitting, okay, if the light is costly, then we cannot have an agriculture based on that. But if the cost of the lighting becomes cheap, then we can definitely go for such a controlled environment agriculture, because we are definitely going to face problems, environment problems or climatic problems, etc. So it is better to go for cheap, cost-effective lighting, so that we can go for such type of agriculture in future. So coming back to another way of saving energy is nothing but in the form of hydrogen. You take hydrogen and store it in a particular material, solid state storage material, then you can transport it to anywhere. Because gaseous way, one cannot transport hydrogen. If you put it in cylinders, it will be cost effective method, because it will become very heavy and it will be not cost effective. Similarly, you cannot liquefy hydrogen, because a lot of energy is liquefied for the liquefaction of hydrogen. So that will not be a cost effective method. So hydrogen, we all know, is a very clean fuel. It generates only water as a byproduct. So one of the hurdles for using hydrogen in commercial scale is nothing but the lack of cost-effective or compact safe storage methods. Due to that only, we are not able to effectively use hydrogen for different applications. Invariably, this also will help for the sustainable development of the society.
is another aspect also for this, because if you transport only electricity, electricity can be transported by transmission through cables or through grid. Correct. So if 100% grid transmission is there, that is not secure for a country, because anybody can disturb the network or create problem to the network, transmitting grid network, and as a result of this, electricity supply gets affected. Once electricity supply gets affected, what happens? A lot of activities become standstill. Many activities come to standstill. So 50% electricity through grid communication and 50% electricity through either battery or through hydrogen gas saving or energy storage devices is always preferable. One cannot have 100% transmission through grid, because that is because our security becomes vulnerable. So there comes the relevance of battery storage versus hydrogen storage. There are a lot of advantages and disadvantages, so which probably we will not discuss. But hydrogen storage is equally good compared to the battery storage. So now coming back to the work which we have been doing on this solid state lighting aspect, we have worked on a variety of materials, which includes many times gallets, germanics. And zinc sulfide, we all know zinc sulfide as an electroluminescent phosphor was discovered by almost around 75 years back in somewhere in 1836. And copper doped zinc sulfide has been, I think, maybe 50 years back, this has been developed. But we do this because we need to characterize our devices. We need to standardize our devices, whether it is working properly or whether we have made a standard device, proper device. So for standardization purpose, we always require the zinc sulfide based material. In addition to this, we have also developed this type of material, gallets and germanium based material. Of course, we have tried a variety of materials, and these two materials show very promising electroluminescence properties. So what electroluminescence I am telling is not the DC electroluminescence. What I am talking is AC electroluminescence, alternating current electroluminescence. No need to convert the DC to AC, AC to DC. We can straight away use the power point from the wall, and then you can light the lamp. So, and another thing is that this is not a thin film device. This is a powder coating device. The powder, as synthesized powder, with the help of a documented technique, is used to make the device. Of course, efficiencies are lower. There are many other points to be addressed. We have got a maximum efficiency of around 3 luminescence watt. We need to go further. So this is the typical configuration. You see here, this is a flexible PET. PET is nothing but polyethylene terephthalate. We have got a conducting ITO. Then we have got phosphor with the help of a suitable binder. Binder can be even castroid. And then we have an insulator BATiO3. And then we have a silver paste. So we apply AC frequency here. So what is happening is there's a capacitive coupling here, because this insulator will act as a capacitor, and there's a capacitive coupling, and this coupling increases the voltage drop across this luminescent material, and this voltage drop is sufficient to excite the charge carriers and get luminescence from this. Now, so as I mentioned, we work on powder electroluminescent material, not thin films, and we require a powder coating device. This is the typical powder coating device we have, and with the help of this device, we coat it on ITO substrate, and we make device based on that. So this is the typical steps involved. We take ITO coated PET substrate, phosphor coating will be there. For example, zinc sulfide phosphor, any other phosphor. Then dry it at some temperature. Then we put barium titanate layer for which is nothing but for capacitive coupling, and this will be followed by silver paste. And then we directly connect to the AC 230 volt power supply. In fact, we can do that, but since we have to be portable, since we have to take it somewhere, the device, so we have made a small power supply. Our electronic colleagues in our division has made a small power supply using 2 batteries. And as I mentioned, it's an AC power supply, so we need to have an inverter here to convert the DC to AC. And then if you connect these crocodile clips to this device, we can get light outputs from the sample. So of course, efficiency is lower, 1 luminescence per watt. We have increased further to 3 luminescence per watt. But there are many other steps. We need to at least go to around 20-25 luminescence watt to have a commercial value. So with this aim, we have explored the other materials. So we have explored a variety of materials, and we came to know that the zinc gallate or gallium-based compounds are promising compounds. The zinc gallate exists in spinel structure, we all know, in which a center gallium is surrounded by 6 oxygen, and the 6 oxygen is, each oxygen is tetrahedrally coordinated with 3 gallium and 1 zinc. So effectively, if you consider gallium here, we have 6 near neighbor oxygen, and 12 gallium as next near neighbors. So if you substitute germanium at the place of gallium, we generate cationic effects, nothing but an adiovalent substitution with cationic effects, and this effect significantly improves the luminescence properties of the bag. For example, if you see here, this is the electroluminescence, which we have recorded with the same portable setup, power supply unit, which we have fabricated. So you see here the line width is quite large for the undoped sample. The moment you dope with germanium 4 plus, what happens? There's a significant reduction in the line width. How we explain this? Because when you have only undoped germanium, undoped zinc gallate, we have a significant emission from the oxygen defects, the electroluminescence created by the oxygen defects in the lattice. The moment you put germanium 4 plus, germanium occupies the gallium site and this generates cation vacancy in the lattice. Then no longer the system is deficient in oxygen because you have excess cation and you see a significant decrease in the line widths. So we also carried out variable voltage to see what is the mechanism. If you change the voltage, the intensity varies in a particular fraction. This is the luminescent intensity from the sample. And this is the luminescent intensity at the 0 voltage, but 0 voltage we cannot have. So we measure at a very low voltage and plot it as a function of the inverse of the square root of the voltage. And if you plot logarithm of the L versus inverse of the square root of the voltage, if you get a straight line, then we say this electroluminescent mechanism is based on a hot carrier induced excitation. When you apply AC voltage, the carriers which are in the interfaces get more and more energy. The carriers become hot and they bombard the luminescent center, and this luminescence from this center leads to the emission of light. So we explain the defect formation based on this two-dimensional picture. You see zinc 2 plus side, O2 minus, and gallium 3 plus side. You can see this side. These are nothing but the vacancies, oxygen vacancies. And this is nothing but the Kroger-Wigg notation of explaining the vacancies. The moment you put germanium, what happens? These oxygen vacancies disappear, and instead of that, you get a lot of cation vacancies. And the decrease in oxygen vacancy leads to the decrease in the line shape, decrease in the line width, and improvement in the. Once the line width decreases, you can get a very bright emission from the sample. In fact, this is the ideal blue color light emitting material with the coordinates, color coordinates 0.15, 0.15, and in fact, with the varying voltage, it remains nearly same. There is no change in the color coordinates indicating the material is quite stable. Of course, blue light emitting materials, a lot of requirements are there because blue light and yellow light use white light. So generation of blue light is quite important for developing white light displays. So moving to the other part of the work which we have been working on is the materials for clean energy applications. As I mentioned earlier, it is basically the development of materials for hydrogen storage applications. Today morning, Dr. Basi could talk about another type of hydrogen storage material. This is ammonia borane. So, but here we work on solid state materials like alloys, like titanium, chromium, vanadium alloy, magnesium hydride alloy, then palladium doped in graphene, then palladium doped in carbon nanotubes. Then this is a metal organic framework called a zeolytic imidazolite framework, a complex of zinc with this imidazolite ligand, and it forms a network. And here the pores of hydrogen can get occupied. But many of them I have discussed, but other than this alloy, many of them store hydrogen at low temperature. For example, if you see metal alloys, they store hydrogen at room temperature and higher temperature. But for materials like graphene, carbon nanotubes, or these metal organic frameworks store hydrogen at a cryogenic temperatures like 120 degrees, 120 Kelvin, 130 Kelvin, 140 Kelvin, etc. They have sufficient hydrogen absorption capacity only at low temperature. So practical applications are limited. And this is a good material, but probably this is an irreversible hydride because once you use it, if you take out the hydrogen, we have to again convert it back to this material. So this is amount energy. So since these two, among these two materials, this is magnesium hydride and this is titanium chromium alloy, this material is found to be quite promising because this absorbs hydrogen at room temperature and around 80 degree onwards, it starts giving hydrogen. So we have gone deep into this and we developed this type of material for storing hydrogen. So you may ask why we have arrived at this material. Because why we have arrived at this materials is there are many materials which form hydrides. But if you see the periodic table, some of the hydrides are very high minus delta H value. See minus 200 kilojoule per mole, minus 210, minus 146, minus 208. That means they form very stable hydrates. It is very, we have to give to very high energy to get hydrogen from that. But there are some hydrates like chromium, manganese, etc. They have very low value, minus 16, minus 19, etc. So means very quickly hydrogen, or if you very easily you can take out hydrogen from that. But if you combine these two hydrates, then we will be able to generate the medium value, in which at a relatively low temperature like 100 degree, you can get hydrogen from that. So with that idea only, we have selected this compound titanium chromium vanadium and started working on. In fact, there is a project in VRT for generating hydrogen by alkaline hydrolysis of water, in which they have entered in collaboration with or entered in MOU with HPCL and all. So there they have generating almost hydrogen by water electrolysis. So this hydrogen need to be stored. Of course, around 18 liters of hydrogen is generated per day. So 8 days, so we generate almost like 144 liters of hydrogen. So this material, which we have prepared almost like a 300 gram of the material, titanium chromium vanadium, by arc melting method, it can store almost like 150 liters of hydrogen. In fact, this material is deployed there for storing hydrogen generated at the heavy water division of Baba Atomic Research Center to store almost like 150 liters of hydrogen. So these are the hydrogen material, the alloy which we have prepared. In fact, this material as such will not store. We have to grind it. We have to grind it into small pieces. Then only it will store hydrogen. So this is the typical setup used for hydrogen storing. So we have a hydrogen cylinder, we have a reservoir, and we have a transducer, and we put small amount of hydrogen here. We dose the reactor with hydrogen. So what is happening here? If you give a small amount, if everything is absorbed, there is no pressure buildup. But slowly, if you increase the amount of hydrogen, what happens? A stage will come, the pressure buildup starts. So if you draw a tangent here and here, the point of intersection gives the hydrogen storage capacity of the material. So this way, we evaluated the hydrogen storage capacity as a 3.8% at room temperature and subatmospheric pressures. And this is the typical photograph of the system we use for hydrogen storage studies. This has been actually fabricated around 25 years back. So another interesting thing is that these are the buttons we get the alloy. The moment you subject to repeated hydrogenation, what happens? The material becomes brittle and it becomes a powder. You can see that before hydrogenation, you see pellets. At the moment you hydrogenate it, you get a very fine powder of this material. So because the material gets embrittle because of hydrogen, and slowly with the repeated cycles, it gets broken into small pieces. So we do also desorption study because it is important that we need to take out the hydrogen. So if you heat it, what happens around 80 degree onwards, the material start giving hydrogen. And at 180 degree, the hydrogen is maximum peak temperature, in which you will get maximum hydrogen temperature, hydrogen output from the material. So we have also tried a different storing hydrogen in different flow rates, and the capacity is found to be around 3.8% only. But that means we can use the material also in the flowing conditions. So after 1 year, after 2 years, etc., also we have tried this system development, system capacity. Of course, it is not exactly 100%. There is a reduction of around 6%, 94%. The material stores, even after 1 year, 94% of its expected value. We have also done some cyclic studies. Up to 50 cycles, there is no problem. Still, the cycling studies are continuing to establish its cyclic stability. So titanium, chromium, vanadium, the capacity is lower, 3.8%. So we investigated further whether we can go for another hydride. So in this regard, we have gone for the magnesium material, magnesium metal. The problem with the magnesium metal is that it absorbs hydrogen only at high temperature. But what we did is we have taken the magnesium metal and then subjected to ball milling, and we have made a nanocrystalline material. So these are nanocrystalline aggregates. Of course, in the size is micrometer, but their crystalline regions are in the size of nanosize dimension. So you can see there's a significant reduction in the activation energy when you go from bulk magnesium to nanocrystalline magnesium. In fact, for the bulk material, the activation energy is around 300 kilojoule per mole. But the moment it becomes ball milled and become nanocrystalline, it's not nanoparticles, it is nanocrystalline, the activation energy reduces to almost like 75.2 kilojoules per mole. So that is also seen in the kinetic stability to plot the time versus reactor fraction. As you increase the temperature, you can see here almost like a 325 degrees centigrade only it is absorbing hydrogen. So higher temperature is required if you are going for a magnesium based material. Of course, the hydrogen storage capacity is higher. but you can only, you have to heat the material for hydrogen absorption. But in the case of Ti to CRV, we are having room temperature absorption and under subatmospheric pressure, the hydrogen absorption is taking place. So with this, I conclude the blue emission, and I'll come back to summary. Blue emission from industrial standards can be obtained from germanium doped zinc galate powder samples. Electroluminescence intensity need to be further improved, and we have to make further large area displays of the size of A4 dimensions. Intermetallic alloys are potential candidates for hydrogen storage. However, their vulnerability towards moisture or oxygen need to be further addressed. With this, I thank you very much.
The topic is open for discussion, question and comments.
Hi, this is Yogendra from NICER. The series hydrogen adsorption normally in the cases you discussed, usually they do in Fiji gypsum. Yes. In this case here, alloy hydride. So they are no longer Fiji gypsum.
Yes, right? There is a metallic bond.
There is a
metallic. Hydrogen diffuses inside and goes to the interstitial sites. Side sites.
Chemigers.
Yes, right.
So obviously the release of hydrogen is going to be very high. So what do you think? Do you think this 80 degree it's too high for any applications? Because you have to need 80 to 100 degrees.
If you see the DOE standards, Department of Energy standards published, they claim it is 150 degrees centigrade can be used for regular applications. Desorption temperature of 150 degrees centigrade. Of course, we are having 180 degree and 80 degree only it is starting. So that advantage is there. But for MOF, they give at room temperature. But the problem is you have to do cryogenic temperature condition. Absorption capacities are quite low.
Yeah, my comment was already triggered by your third bullet in the last slide, where you talked about the gases vulnerability.
Yes, sir.
Yes, I think it's a very serious issue in the sense that it should be addressed by R&D separately, because whatever source generates hydrogen, it's not going to be just very pure hydrogen. It will be mixed with either moisture or a little bit of oxygen. These alloys will have great tendency to pick up oxygen or even get hydrolyzed the moisture. So you may require in between some step for converting that into pure hydrogen before absorption.
Yes.
So that also will have to be additional technology and additional cost.
Yes.
This needs to be factored.
Yes. Yes. In fact, in the BASC heavy water division, they have a hydrogen test facility. There's a purification setup, and after purification only they are giving to these hydrogen.
Things like oxygen can get irreversibly reacted with the chromium and the beneath that. It can get destroyed over a period of time.
Yes.
Because oxides are very stable, particularly for chromium.
Yes.
That needs to be looked at.
Yeah, any more question? Yeah, if there is no more question, let us thank Dr. Sudarshan for a very nice presentation. On behalf of the organizer, it is my pleasure to give a memo to Dr. Sudarshan. Now we move on to the next speaker, Dr. Ashish Satpathy from BRC. He is present working as scientific officer G and head electrochemical methods section of analytical chemistry division BRC. His research interests includes electrochemical investigation of thin films, biomolecules, and semiconductor interfaces, application of ultramicro electrodes and scanning electron microscopy. He has contributed on the R&D of composite material for efficient supercapacitors and electrochemical investigation of materials for supercapacitors. He has investigated electron transfer reaction in homogeneous and microheterogeneous medium using photochemical techniques. He has important contribution on development of analytical methods using voltammetry and developed several electroanalytical methods and applied the methods for the determination of metal ions at trace and ultra-trace level. He has investigated the electrochemical properties of thiocompound, antibiotics, anti-cancer drugs for sensing and interaction studies with proteins and biomolecules. He is teaching electrochemistry in the postgraduate level. Currently, Dr. Satpathy is Secretary of the Scientific Society of Indian Society for Electroanalytical Chemistry, ISESE. Dr. Satpathy is a recipient of the following awards: Young Scientist Award 2008 from DAE, a Fulbright Fellowship to carry out research work with Professor Alan J. Ward, famous professor in electrochemistry in University of Texas, Austin during 2011 to 12. Young Associate of Maharashtra Academy of Sciences 2015 and member of National Academy of Sciences of India in 2018 and fellow of the Maharashtra Academy of Sciences 2020. I invite Professor Satpathy to present its title of his talk is the electrochemicals and spectro-electrochemical tools in probing interfacial processes.
Okay. Good evening, and thank you, sir, for kind words. I hope the students are keeping their attention, as it is difficult for me to do that. So let me talk, little bit of our divisional activity first. Overview of the facilities, because it's an interaction meeting. And of course, I thank the organizer, like BRC part and ISAT part, for giving me this opportunity to speak. So that's our first time giving all the activities in analytical chemistry division. Like we have several spectroscopic techniques to characterize materials. We have nuclear analytical methods. These may be unique in the division. So you can, of course, try for their analytical capabilities. Then chemical method, starting from classical to different sophisticated instrumentation. Then separation science and thermal and electrochemical. And of course, we have an electronic development groups who takes care of the instruments, also do several developmental work. So these are some of the highlights of the works. Like we have certified in-house reference material. Why you call in-house? Because we do not have ISO 35 certification. Otherwise, we can certify that then this in-house what will go, we'll have reference material in that case. But we do rigorous treatment before call it the in-house reference material. And separation of precious and hazardous materials from waste. Then there is a MOU between NTPC and BARC for analysis using NA and DXRF. Then this is this facility is there in Calcutta, and where the excitation for heavy ion and thin layer activation application enriching nuclear database. This facility is associated with analytical distribution BRC. So you definitely can try to utilize this facility for analytical measurements. Then supercapacitor, energy storage, and different sensings, water splitting, generating hydrogen, sensor for nuclear and societal applications. Then absorption properties of different composites from metal ions of nuclear importance under different experimental conditions. Then cutting edge research in analytical method and process developments. So essentially what you can see is we are utilizing chemical sciences for some of the applied part of departmental goal, in addition to some of the curiosity driven research. These are the facilities. In a sense, we have several instrumentation and to characterize materials, and coming from your spectroscopy and then thermal, electrochemical, and things like that. This laboratory, our laboratory is ISO accredited. This is 17025. So which means the data that we generate, that is validated as per NABL accredited accreditation. And but we do not have ISO 35. That's what we cannot certify our reference material. So that's what we call as an in-house reference material. These are different activities of like nuclear analyticals and all, which I have already mentioned. And then in a spectroscopy, certified material, hybrid nanocomposite for water decontamination, then separation of precious hazardous materials. Similarly, separation science, several activities, including some of the thermal measurements of some of the nuclear materials, and also preparation of, departmental requirement on metrics with 100 ppm hydrogen. This particular slide is a typical representation of different materials that were used in absorption of hazardous material. Like this one is for chloride, this is for uranium, this is for arsenic, this is for chromium, and this is for cesium. This is the activities where I personally involved, like methods and processes, instrumentation and sensors, and materials and their processes for energy harvesting and supercapacitors, some of the remediation of toxic metals, inorganic molecules, and we also work on recovery of some of the departmental material like gallium, magnesium, and also developing thin films like cadmium for some medical applications. So, and then we, as a developmental of sensors, like this is the dissolved oxygen sensor which we have developed, and this technology has been published, and of course 4 companies have taken this technology so far. So this is the overview. Now let me come back to what I said, the second part, like interfacial processes using, this is totally focused on electrochemical processes. Now this particular slide I am very much interested to show, just to link between spectroscopy and electrochemistry. When you do spectroscopy, we have 2 states, 2 quantum states, like ground state and excited states. And this is for the students, of course. This is for the beginner. So we get a peak there in absorption peak. But when you do an electrochemistry, it's a classical system. We keep on increasing voltage. Let us say cadmium reduces at minus 0.6 volt. So if you apply minus 0.8 volt, it reduces. If you apply minus 100 volt, then also it will reduce. So what you should get is, if you keep on increasing voltage, the current should have been like this. It should have increased like this. But why you get a peak? Like what we get in spectroscopy, we get a peak here, and when you get a peak, as an analytical scientist, you should be very happy. So from here itself, you transform from your classical electrochemistry to analytical electrochemistry or a voltammetry. So this has happened because you have concentration polarization in the system. Means the rate determining step is mass transfer, not the charge transfer. So after a certain point, you have a mass, the decrease in analyte concentration close to the diffusion layer, not in the entire solution. This is something, a mistake we always do. So there's a decrease in concentration doesn't mean that the bulk concentration decreases, because if you take 100 electrochemical scan, you'll get the same current. That means bulk concentration doesn't decrease, it decreases only at the diffusion layer. So that's probably the starting point of voltammetry, which separates the classical electrochemistry to voltammetry. All right, this is something that is how we have to see what happens when there is an electrochemical oxidation and reduction, how the mass transports, and how the interface looks like, which is very complicated. It's seriously complicated. That's what the same thing you do, something works and sometimes it doesn't work, because it's a surface process, and surface always makes the complication when you do actual processes. All right. So how to investigate those complications and what all we can conclude from the investigation that we do. Let us say get a current. Why we get a current? If we don't get a current, like we apply a potential, we are supposed to get a current. Thermodynamics says we should get this much of current, but we don't get it. So why we don't get it? Or let us say we are getting, why you're getting. So impedance is something what we can really characterize a interface really well. We can see what happens to the interface in terms of its series resistance, what happens to its charge transfer resistance, what are the capacitances, and in fact they are complicated. This is the most simplest one, what an electrochemical interface looks like. And there is a TOEFL. We have used all the TOEFL is another parameter what you can do. TOEFL is nothing. First equation is about Horman equation. There is no polarization here. There is no voltammetry here. It's from a purely diffusion equation. So you got this equation, you polarize it, high positive and high negative, transform to the TOEFL. So TOEFL is something is a transformation. I mean, Butler-Romal, I will say it's a scientific equation. Tuffle is like engineered equation. So you get parameter from a tuffle, and you got a cathodic tuffle slope and analytic tuffle slope. It's alpha or beta or alpha or 1 minus beta. So we can do a lot many things by simply calculating these two parameters. And another one is scanning electrochemical microscope. It is kind of, but we have in fact installed this technique and using this interfacial processes. So that we get images like AFM gives a morphological image, ACM scanning electron microscopy again a morphological image. This can give the image of electrochemical current over the surface. So we have to get your tip close to the surface. So we are close to the diffusion limiting process. I mean, we come close to the diffusion layer, and then that means whatever is coming here without any loss, it reaches the tip and it comes back. So when we scan it over the surface, we can subtract the morphological differences, and after that we can get essentially what is the electrochemical current get over the surface, which part of the catalyst, which part of your sensor substrate is good, giving a better current. We can even image it, and not only imaging, this gives the kinetics, which I'll from this approach plot we can get kinetics, which I will come. Now let me say something about what are the HER. I mean, when you talk about water splitting, either using electrochemical processes or photoelectrochemical processes, either it's an HER or OER. I mean, all the time we talk about, so we are talking on HER or you can go OER. But it is a hydrogen evolution reactions. These are all something Walmer states, which is the charge transfer state is the rate determining state. And you have several states, but this is charge transfer state. The tuffle is supposed to be 120 millivolt. And your tuffle, which has got an adsorption, I mean, like palladium is a good adsorber. So it adsorbs hydrogen and then they combine it. Otherwise again the reaction goes down. And last is Herovsky. So Herovsky is this adsorb hydrogen, and there is again a charge transfer, and then combines gives to hydrogen. So they gave a different tuffle source. So these tuffle source essentially can indicate what the process going on, and this in fact gives us an idea what kind of catalyst surface modification we should do so that we can increase our processes. Similarly, when it comes to oxygen evolution reactions, so this is the interesting part is, like, everybody wants hydrogen out of water, but 90% people work on the anode side, which doesn't generate hydrogen, which generates oxygen, because that is the most difficult state. So everybody wants hydrogen, but they will develop a catalyst for the anode side, because this is extremely complicated processes, and there are there are several, of course, theories, but there are two which can be said that one is this LOM mechanism, another is AEM mechanism. LOM is expected to be better, but if you want your process to be LOM, this is LOM. So why it is happening, the OH, this is generated H plus and OH minus. This OH minus is essentially connected to this oxygen, like metal oxygen bond oxygen. That means this metal has to drag this oxygen. What I get this polarizing power of metal has to be much higher. That only then you have electron density less at the oxygen center, then OH minus can be attached there. So that is how the and tuffle can predict little bit what mechanism going on, in addition to if you can do some in situ IR and all. All right, now come back to the work that we are doing. I mean, graphene oxide, 3D graphene, there's several things we all talk. 3D graphene is essentially somewhat stable. Okay, graphene we work, I mean next day the structure we collapse. So I mean, like, so several of you probably tried. We also did this 3D graphene and loaded some of the noble metals and investigated their electrochemical properties, and we can say that, I mean, PTC has around 30% platinum. So this can be similar activity or metal activity can be achieved by doing somewhere around 10% of this noble metal. But in addition to that, what are some basic investigations that can be obtained is the processes like we have 4 noble metal like silver, gold, and the well-known platinum and palladium. The process is happening where, like, we get a tuffle slope at different temperature and get the enthalpy component and entropy component of those transfer coefficients from the top tuffle. So you got an idea that these processes are essentially, when you talk about platinum and palladium, they're entropy-driven processes, and the other one is an enthalpy-driven process. So you can get this platinum, palladium At a lower temperature, you get a good catalytic activity. This is the one of the inference, including several other inference, what you can draw from this kind of analysis. All right, and then in addition to that, you can definitely, these are all some like conventional electrochemical techniques, but to get the N factor, I mean how many number of electrons that is being transferred. But we need to be very careful when you do this measurement. I mean, how much rotational should give and how we get the data out of it. Otherwise, code syllabus will be messy. I mean, we may get like 30 as in for an hydrogen, which is essentially 2 or maximum 4 electron transfer process. Now, and then another material for the cathode side, molybdenum disulfide that we have tried. And what we wanted to show here is this molybdenum disulfide. We have used ACCM to characterize that, the charge transfer processes. So I want to show that part of it. So this is what the arrangement is. We have a substrate where we modify the catalyst and we bring out the tip close to the surface. I mean, I should say this is the most difficult part because there is no piezo here. It's like almost manually able to see how the current is, and otherwise you will crash land it and the tip will go. So I do not know, this technique has not that way developed because we cannot no way see where we are actually. So this is how, once you get this, then the feedback, that hydrogen comes in and goes and you get a feedback. So this was the feedbacks are. So we have a feedback here. This is called the positive feedback. And we have a positive, 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 then we get a negative because we are polarized in substrate at different potentials. So by fitting these things, there are some complicated equations to fit this approach plots to get the kinetics of the electron transfer processes, which do not have essentially the multi-layer diffusion problem. That's what this technique is useful, because otherwise there are 10 different ways we can get kinetics out of it. This is one of the best because we have removed the complications due to diffusion processes. So we got kinetics, and then finally we have modified our MOS2 using either GO or RGO, a little bit of reduction. So we find RGO is generally supposed to be good because it's a good conductor, but we find GO has given better current and kinetics behavior, and this is what is happening. We have an exchange because we have a functional group at the GO surface, so that exchanges from the solutions to electrode, and your current responses were higher. Now coming to, so far it was like a electrocatalyst. Now you have a photo like PEC, what we generally call. These are the materials. As we said, we have not, like there is many sophisticated, you may be doing research like 10 different material and a lot of complications, but we have used like some of the conventional material that has been used for catalytic applications, and these are all modified to the electrode level, and these are also we have given to engineering divisions for their device fabrications, and they are working on for coming out as a good anode of this. So this was vanadium and iron oxide we have worked, of course, with some modifications. This was vanadium is good. I mean, so that there are some criticism about its conductivity, your diffusion link, you have a photocorrosion, you have a fast hole recombination. So those processes we have tried to investigate what all we can do to best understand how, to improve its properties. So bisphosphonate, of course, we have taken ITO and then modified it with like 5 to 7 times over the surface. SNA2 has been done as a heterojunction because it takes care of the electron, and that is connected to a potentioset which is the sink of electron, and you have a then hole available for the transfer at the solution side. So this is the electrode is, but we have done modifications with molybdenum, and of course other than molybdenum, and when you do this modification, we have done this 1%, 3%, 5%, and 7%. 5% has given reasonably good activity in terms of PEC. Now, why that has happened? This is a chop light voltammetry. I mean, we chop the light at the same time. This is like linear voltammetry with chop light. So we get a SPM5 that has given significantly higher response, and IPC, like I hope you don't know this terminology. So this IPC percentage is, I mean, something 5% to 20%. And that has been reflected from the donor density measurement. This is done from Mott-Schottky analysis. Like this is impedance in presence of light. And we got a donor density which comes out to be this one, which is similar. But what happened is your OCPV, I mean, open surface photovoltaics, that is the factor that improves the catalytic activity when you put molybdenum into it. And this charge transfer and charge transport. I mean, I will just say for the student, charge transfer and charge transport. Charge transfer is like we generate this electron hole at the bulk. Now this hole has to transfer to the solution side. Electron has to transfer to the potentiostat, which is sink. Now, so this you need to do very effectively. Now, the transport means the hole has to go from the bulk to the surface. Now it goes there, and then it has to be, this is transport, and then it has to be transferred to the solution. Like the water molecule has to take that hole and oxidize to generate oxygen. So that this particular, whatever figures that we are saying, this is done with conventional way using sacrificial agent. And I will show you in the next work what we have used is IMPS to calculate these processes. Now, what is saying ACCM? This ACCM is somewhat different than what we have done in MOS2. This is done in presence of light. So whatever kinetics that we get, that is essentially correlated to hole transfer kinetics. I mean, the current that is measured is due to transfer of holes. Though the kinetic constant that we are getting is essentially hole transfer kinetics. So same approach plots were recorded, but under light illumination condition. So that is the driving force. We generate the hole, and that somebody has to take the hole which is present at the tip. Now, through this fitting of the approach plot, we got a effective rate constant for those transfers, and we find that this SBM5 got a transfer coefficient reasonably good, but then SBM7 is also good. I mean, but then SBM7 we found from impedance the resistance goes up when you put a lot of molybdenum in the system. So overall the efficiency 5% molybdenum was better. We also modified the surfaces. So molybdenum essentially improves to some extent the transport, but surface modification was done by cobalt borate. This is borate. BI is, this is the terminology has taken from the literature. So cobalt borate was put on the bismuth. I mean, we have a SNA2 first layer, then molybdenum and bismuth vanadate second, and then co-BI third. And this you could do reproducibly because reproducibility is very important. And after doing, we got their current measurement. Co-BI has given a significant improvement in the charge transfer processes. And that improves, I mean, co-BI is essentially a co-catalyst. It is an electrocatalyst, and bismuth vanadate is a photocatalyst. So we put an electrocatalyst, a thin layer, by doing an electrodeposition method, and that improves the kinetics. And we have got over and above almost 100% improvement in photoelectrochemical current. Right. So and this interfacial hole transfer kinetics again were calculated using ACCM approaches, and we found that this is like a CoVI3, which is like we have used this 100-second deposition that has given a significant improvement in the catalytic activity, and we have done photocharging. Photocharge generates some defects at the catalyst surface of the active catalyst surface that improves the catalytic performance further. Now, what I was saying is previously the transfer coefficient and transport coefficients were measured using conventional and sacrificial agents. Now, this one done with an IMPS measurement. So IMPS is essentially an impedance measurements, but what we have done is electrochemical impedance measurements. It's a sinusoidal voltage signal. Here, the perturbation is sinusoidal light signal at some potential. So when you apply this AC light signal to the surface, it gives the impedance responses. And this impedance response essentially takes care of your rate constant for the electron transfer and recombination, because when the electrons and holes generates at the bulk, it has a recombination component which you do not want, and it's a transfer component, like hole has to get transferred. So this is independently calculate this transfer coefficient, and I mean this recombination rate constant and transfer rate constant independently, because we just subtract one from another. So it is not like this, it's independently measured. So I will say this is a better representation of figures compared to using a sacrificial as agent to determine these two coefficients. So that's what you can see, the recombination. This is for a bismuth vanadate, and we put the 3 layers what we have done before, and this is your recombination rate constant, which with respect to potential, I will say this is remain constant, a little bit goes down, and this is your transfer coefficient, what charge transfer rate constant, so it goes up. And this is with ALD TiO2. So we have an atomic layer deposition system. So as you know that bismuth vanadate again undergo photocorrosion because it is not so stable. That is why it is criticized for. So we put something like 50, 150 and 5 nanometer TiO2 layers to stabilize the surfaces. So with that, we find that it is not only stabilization, there is an improvement in the catalytic performance through improvement in their rate constant of charge transfer. See, what I said saying was is we have a total current. So we have a total current improvement. So they're independent measurement because you have a significant enhancement is their transfer rate constant, but these remain constant. So that is the inference from their independent measurement using IMPS. This one is, of course, and this is I mean modeled through this way, that this is electronic surface specification. This is a whole surface states. So you got a whole surface states. If you have enhanced, if you are able to enhance the surface states for the holes, the lifetime for the hole improves. Your transfer rate of holes will improve. You will get better current. But if you have this more number of bays, so then the electrons also will be coming closer to the surface. So the surface equation of electron and hole will be enhanced. So current further goes down. So this TiO2 at a thin layer level, because TiO2, of course, if you put a thicker layer, it retards the, it only takes the UV light. So the ALD is best suited for that. So this is what we could demonstrate, that using TiO2, we can stabilize the material for more than 2 hours. At the same time, catalytic performance of bismuth vanadate improves significantly. This work is, of course, we have exclusively used ACCM to image. Probably ACCM imaging, I mean, I will say recording is something tough for, like this materials were, prepared by Professor Narayan's group in TFR Hyderabad, and we have used them. These are, cross-linked TiO2 surfaces, and we wanted to see the catalytic performance. Catalytic performance in a sense, the current performance of those surfaces. And we find that using rate constant measurement, using ACCM and also their ACCM imaging, we could see the tracks, those 3D link tracks of currents that could be detected using this measurements. Now, supercapacitors, I'm not speaking. We have a program of developing surfaces and, of course, to some extent device level to demonstrate their activities of different oxide materials which can sustain for somewhat longer time. And also, as I said, we are working on sensors and interaction of molecules using different surfaces, and also sequestration of nitrates, like decomposition of nitrates through electrochemical detection and decomposition of nitrates. And also interactions of some of the biomolecules, like we have done this interaction study using electrochemistry and AFM in combine, using spectroelectrochemistry and AFM. You can see that E. coli and at what dose and what happens to E. coli cells in presence of ciprofloxacins that was measured, and in fact we can see image those surfaces. Yes, this is my last slide, and I thank our authorities, and contribution is essentially done from my students and colleagues. Sudeepa is here presenting one poster. Thank you so much for your attention. I'm sorry I was probably rushing. Thank you.
Yeah, question or comments? Just one or two small questions.
When you are talking about the interface, actually, the electrode surface,
Yes.
what is the thickness you are considering?
Interface.
Yes.
See, the diffusion layer thickness is 100 nanometers. Diffusion layer thickness are generally 100 nanometers. So now, how you can approach? But we cannot approach 100. It's difficult to approach 100 nanometers. The tip is
But for example, the diffusion layer and the strand layer, the electrode surface, and most of the things are happening in liquid media.
Yes.
Have the solvent.
Yes, yes, yes.
So that whatever the, for example, ions and things are at the electrode surface or additional reduction. So it is basically the hydrated ion is getting and attached with the electrode surface.
Yes.
So it is basically one molecular layer.
Yes.
So that is basically.
So let me speak. I understand this.
Yeah.
So I published one paper in organic chemistry where I went up to diffusion layer, but I could not do it in India. Let me tell you, this is a challenge. What you can do is at least 2 diffusion layer thickness, because our laboratory the vibration level is 100. Like this is solution. I mean, not like there's a vacuum. This is solution. You're applying. This is solution. Solution has its own buoyancy. So the best what you can do, based with the acoustic chamber, what you could do in BS laboratory, I will say that we have calculated how far we can go. I mean, there is a model who have done this. These are like 2 to 3 diffusion layer away from the surface. This is the best that we can do. Yes.
300 nanometer.
Yes. Now, that is the best we could do. I mean, it's the best if you can beat the diffusion layer. Like when you can go beyond this, you can just see the dry ions there. Because as for the students, again, it's the bulk, the solutions are hydrated, was the question was. Okay. When it goes to the surface and to take 2 electrons, it cannot go itself along with the solvescent cell, because the solvescent cell has to then, along with these metal ions or anything, the solvescent cell has to gain that stern potential, which is very sharp. This is straight line. You have seen that beyond start line, what kind of potential. So that leave its solvescent cell. So if you can put the tip beyond the solvescent cell, that's the best I can say.
Energy, please discuss after during the dinner time. We are running late. Yeah, one more just short question, if any. Otherwise.
Very good evening. This is regarding titania coating over bismuth vanadate. Was there any interaction of bismuth and titanium? Bismuth titanate is a very.
They have interacted.
Well, the intervention interaction.
Absolutely.
Well, is it any part in increasing the current capacity or current? Something correlated to that?
So actually, during titanium dioxide deposition, temperature was 300 degrees Celsius. The idea is to make a separate film out of this vanadate. But we have seen this. I have given a sample for RBS measurement in triple CM to know that it is not a distinct layer. There is titanium dioxide at 300 degrees Celsius seep through the bismuth vanadate. It's not a distinct layer. Otherwise, what you said is correct. There will be capacitive junction between bismuth vanadate and titanium dioxide, which has not happened if it is a separate layer.
Yeah, because of lack of time, we cannot have any more questions. So let us thank Dr. Saturi for a very wonderful presentation. On behalf of the organizer, it is my pleasure to hand over a moment to. We have come to the end of this session, and once again, I would like to thank the HBNI Central Office as well as HBNI faculties at NICER for giving me this opportunity to chair this session. Thank you very much.
I would like to thank Professor Gandhi for chairing this session. And now, on behalf of the organizers, we would like to give a small memento to him. So this concludes today's. Yeah.
Yeah. Hello, everyone. Yeah. Today, poster session first is over. So the posters 1 to 25 are evaluated by poster session committee led by Professor P.A. Hassan, chairman, and members, Dr. Sudeep Burman, Dr. Vishnu Biswal, and Dr. Malay Sarkar. On behalf of the organizing committee, I am asking Professor P.A. Hassan Bar come to the dais. Would like to do a memento. Yeah. I thank all the poster jury chairman and other members. Now I will hand over to Dr. Arindam Ghosh. Yeah. So today's first day's entire sessions, 3 sessions are over. Now we are concluding day 1, and tomorrow we are assembling here at 9:30 a.m. Okay. So for outside delegates, faculty members, and students, the dinner will be arranged at cafeteria at 8 p.m. Okay. Thank you all. See you tomorrow at 9:15 or 9:30. All right. Thank you.
Because it's not coming that it is, like you said, both the screens are visible. The YouTube thing. The front screen and the next 2 slides are visible, right? That's what I see in YouTube. What do we do?
One small announcement. Tomorrow, first session speakers, if your slides are ready, we can load them now. That would be better, actually, just in case you are ready. Okay, fine. That's fine. That's fine. So we'll collect the slides during dinner then. Santhan, you'll conduct it? Okay, fine. Fine.